We all fail. We all make mistakes. I should put that in there. Shit. I'm gonna have to do that now. But, do I have that here? Blurps? Yes, A. Copy them motherfucking blurps. I really shouldn't have them at the moment, though. I don't want to be stepping on... Oh, shit, do I do that every time? What? Refresh, bitch. Yeah, what's going on, Jugs? Yeah, man. Got the lurk up. Oh, fuck, I forgot to tell you I was lurking. Oh, shit, forgot to let you know I was lurking. Fuck. Fuck of an ass. That's not enough. Going lurky poos. Hey. Oh, are you still there? Oh, Addie's still there? You still there? Going into the lurk mode, Mr. Addy. Crystal 2. Lurky. I think that's everyone. Pain. 20 people to work on. I forgot to do all my alerts before I started up. I don't think anybody's actually in my chat right now. Just, yeah, Jugsy. How you doing, Jugs? They're just firing up, make sure everything is working right. Everything looks like it should be. Yeah. Looks good. Yep, looks good. All looks good. Temperatures, yes, good. It shouldn't be too hard on the system. I'm just watching YouTube, but... Well, wait for a bit of company. I'll get fired up. I'm not playing games today. I got nothing to actually do but watch some astronomy class. Get baked and watch the stars. Hell yeah. I love getting baked and watching the stars. Alright, let's get a good roll. Good nuggies. Good ass nuggies up in here. Oh yeah, I'll turn those streams up a little bit. Make sure it's cranked so I can hear what you hear. This fucking playlist is balling, man. 90% of the tunes on here are good. Then you get every now and then you get a slow tune that's just garbage. Play with this. Weakness is shy away, yeah. Packing bowl, waiting for some company, yeah. Yeah. Ah, fuck. Let's get this bowl rolling. What do y'all say? Is it smoke time? Fuck yeah, it is. Always smoke time, baby. Yeah, you know, wow. Still sub, Judge? Damn. Fuck, I wish I had as much money as you. Just throw subs out there like nothing. Fuck. Fucking guy. You're rich. Fuck. Jealous. This one's for you, Judge. See if you're still there. Cheers, my man. Thick. Thick. Oh, fuck me. The older I get, the harder on my lungs that shit, man. You used to call me old iron lungs, man. Big ass fucking hoot and just nothing. Not a peep. I can't handle it anymore, man. Just can't do it. Age for you, man. Age. I want to get to some fucking astronomy, man. Wait for some company. Actually, I have my viewer count turned on this time. Actually, see if I have company. Usually, I keep that shit turned off. Better to keep it turned off. Just do your thing. Never mind the number. Just do your shit, man. You're not out to fucking make company. You just play games, have a good time. Someone pops by, they pop by. That's good shit. Nobody's allowed to see me do this. One moment. Got it. I'm just kidding. These tunes aren't too bad. Do I unplug this, it goes? Doodaloo. Well, I might as well just hang out until I actually get some company. If I do, might be here for a while. Oh, I don't have my notifications up and shit too. Oh my gosh. So bad. So bad. But where is that? Do I have that in stream starting? My notifications here? Am I missing stuff? Blurps is in. Shoutouts. Do I need shoutouts? Probably a good idea. But hold on to them, yeah. Bring them over. Bring them over to the YouTube. And we'll paste the reference, yes. And we'll have to do this. I'm gonna actually take a recording. Did that for my fish. It kept going commercial, YouTube commercial bullshit, so it's like, fuck it. I ran it and I just recorded it. I'll do that for this one. No commercials that way. I just put 10 minutes in. When did some shit around the house. Light bulbs. Fed plants. All that crap. 10 minutes later, came back. All done. Yeah. I'm here if you want to get started. Shadow Man. Welcome in. Hello, hello, sir. Did you bring your notepad to class today, Mr. Shadow? I'm just kidding, brother. How you doing? Gotta turn that on, I guess.
Astronomy. That
Astronomy!
is the Bad Astronomer. And he'll be your host for this series. After all, he has a PhD in astronomy, has written books and plenty of blogs on the subject, and has worked with NASA.
Let me know if that's
so,
too loud.
Yeah,
I think
you're
it's
in
still
good
a little
hands.
loud.
This series focuses on astronomy, not astrology. So we'll get into actual scientific information rather than who you're most compatible with and what the full moon means for your career.
Yes,
Sure,
astrology, bullshit. Astronomy, good.
and other things we can observe with the naked eye, but
Sorry,
then we'll
people who
expand
believe in
out,
astrology.
looking at planets and
Y'all are
non-planets in our
fucking
solar
crazy.
system, our galaxy, stars, gamma rays, dark matter, dark energy, deep time, which is apparently different than normal time, the Big Bang.
Ooh,
and
deep time.
more.
Never heard of that.
Astronomy may seem overwhelming because it's basically studying the biggest thing there is. It's the science of everything in the freaking physical universe.
It is.
That's why we're here to break it down for you. Learning about our universe and how it works is more than just black holes,
Forgot a pen.
star clusters, and
That's all right.
rightly
You got a good
pronounced
memory.
Uranus. It's about understanding how science
I
and
love this stuff,
technology
Shadow.
allows us to study
I watch
the
this stuff
world
all the
around us
time.
and rethink our place
Turn myself
in it.
down
It's
a
about
little bit.
finding out where we came from and whether there's other life, even other universes out there. It's about expanding our understanding of ourselves and, importantly, our limits. Oh, and did I mention this series ends with a 360-degree virtual tour of the universe? Yeah, that might be worth sticking around to watch. So join Phil in episode 1 to begin this intergalactic journey on Crash Course Astronomy.
Let me know if anything's too loud or too quiet. This is the first go. Ooh, PBS! Hell yeah! Public broadcasting.
Hello and
baby.
welcome to
We have
Crash
the
Course
best
Astronomy.
shit.
I'm your host, Phil Plait, and I'll be taking
low?
you on a guided tour of the entire universe.
The entire universe. I'm gonna crack myself up. Yeah,
Over
he's
the course
done.
of this series, we'll explore planets, stars, black holes,
Fuck, I used to watch
galaxies,
that series too.
subatomic particles, and even the eventual fate of the universe itself. But before we step into space, let's take a step
Netflix
back.
there. What was
I
that
want to
show
talk to you
called?
about science. There are lots of definitions of science,
I can't remember.
but I'll say that it's
But yeah,
a body
he's-
of knowledge
I
and
recognize
a
him
method
too.
of how we learned that knowledge. Science tells us that stuff we think
soon as I
we
saw
know
him, I was like,
may
oh,
not
hell
be
yeah.
perfectly known. It may be partly or entirely wrong. We need to
Head
watch the
into-
universe, see how it behaves, make guesses about why it's doing what it's doing,
that's
and
not
then
what I
try to think
expected
of
to hear
ways
from.
to support or disprove those ideas. That last part is important. Science must be, above all else, honest if we really want to get to the bottom of things. Understanding that our understanding might be wrong is essential, and trying to figure out the ways we may be mistaken is the only way that science can help us find our way to the truth.
This is true. I often
or
think
at
about
least
how
the
much we
nearest
have wrong right
approximation.
now that
Science
we think
learns.
is true.
We meander a bit as we use
Like
it,
we
but
say
in the
things
long
like,
run, we get closer and
this
closer
or that. It doesn't
to
matter what we
understanding
say.
reality. And that is the strength
claim
of
something's
science.
to be true, and then
it's
like
all
100
around
years
us.
down the
Whether
road,
you
it
know
won't
it
be.
or not, you're soaking in science. You're a
flat
primate.
Earth back
you
in the
have
day.
mass.
Everybody thought it.
Mitochondria in your
Now
cells
everybody
are
thinks
generating
that,
energy.
you know, the universe is so
Presumably,
big,
you're breathing
or
oxygen. But astronomy
so
is
old.
different. It's
We
still
might be
science,
completely
of course,
wrong.
but
We might
astronomy
be
puts you in your place. Because of
tens of
astronomy,
trillions of
I know
billions
we're
of years.
standing
Oh,
on a
fucking
sphere of
infinite
mostly
years. We
molten
don't know.
rock and
We
metal,
don't really know.
13,000 kilometers across,
We
with
say
a fuzzy
4 point
atmosphere
something
about
billion,
100
but
kilometers high,
who knows,
surrounded by
really?
a magnetic
That's what we know
field
today.
that protects us from the onslaught of
that
subatomic particles
worries
from
me.
the sun 150
Might not be the
million
same in 100
kilometers
years.
away, which is also flooding space with light that reaches across space to illuminate the planets, asteroids, dust, and comets, racing out past the Kuiper Belt, through the Oort cloud, into interstellar space, past the nearest stars, which orbit along with gas clouds and dust lanes in a gigantic spiral galaxy we call the Milky Way, that has a supermassive black hole in its center and is surrounded by 150 globular clusters and a halo of dark matter and dwarf galaxies, some of which it's eating, all of which can be seen by other galaxies in our local group like Andromeda.
He's trying to push
and
everything together
and
in
our
like
group is on the outskirts of
one
the Virgo
paragraph.
galaxy cluster, which is
The
part
entire
of the Virgo
universe in one paragraph?
supercluster,
Holy
which is
shit.
just one of many other gigantic structures that stretch most of the way across the visible universe, which is 90 billion light years across and expanding every day, even faster today than
that's the
yesterday,
radio. no
to mysterious dark energy,
barrier.
and even all that might be part of an infinitely larger multiverse that extends forever both in time and space. See? Astronomy puts you in your place. But what
It
exactly
does.
is astronomy? This isn't necessarily an
It really
obvious thing
does.
to ask. When I was a kid, it was easy.
Trying to think
Astronomy
about
is the
these
study
numbers
of
is
things in the sky, the sun, moon, stars, galaxies, and stuff like that. But it's not so easy to pigeonhole these days. Take, for example, Mars. When I haul my scope out to the end of my driveway and look at Mars, that's astronomy, right? Of course. But what about the rovers there? Those machines aren't doing astronomy, surely. They're doing chemistry, geology, hydrology, petrology. Everything but astronomy. So nowadays, what's astronomy? I'd say it's still studying stuff in the sky, but it's branched out quite a bit from there. Borders between it and other fields of science are fuzzy, a theme I'll be hitting on several times over this series. Humans might like firm, delineated boundaries between
they need
things,
to
but nature isn't so picky.
overlap
And
a
that
little
brings us
more.
to our first edition of
Sciences
Focus
need
On.
to talk to each other
This week's topic,
a lot more. They'd be
astronomers.
able to
Who
find
are
a
we?
little
What
the
do we
fuzzy
do?
areas
I
and
used to look
define
through
them.
telescopes for a living, or at least study the data that came from detectors strapped onto them.
Yeah.
But now I talk and write
Nobody
and
looks
make
through a
videos
telescope
about
anymore.
astronomy and relegate my view into
look
my
through-
personal backyard
They don't even
telescope.
look through anything anymore.
But I still consider myself
Read
an astronomer,
numbers on a
so that
page
should give you an
on a
idea that there's
screen.
a lot of wiggle room in the profession. In fact, when I worked on Hubble Space Telescope, I was actually hired as a programmer. I coded in the language used by the folks helping to build and calibrate a camera that was due to launch into space and be installed onto Hubble by an astronaut. Once the data from that camera are taken and analyzed, you have to know what to do with them. Do the observations fit the physical model of how stars blow up, or how galaxies form, or the way gas flows through space? Well, you better know your math and physics, because that's how we test our hypotheses. And someone who does that is generally called an astrophysicist. Of course, those telescopes and detectors
Raj
don't create
Kutrupalli.
themselves. We need engineers to design and build them, and technicians to use them. Most astronomers don't actually use the telescopes themselves anymore.
Yeah.
Someone who's trained in their specific use does that for them. Some of those instruments go into space, and some go to other worlds like the moon and Mars.
Nobody looks through
We
a
need
telescope.
astronomers and engineers and software
amateurs.
programmers who can build those too. And then at the end of all this, we need people to tell you all about it. Teachers, professors, writers, video makers, even artists. So I'll tell you what. If you have an interest in the universe, if you love to look up at the stars, if you crave to understand what's going on literally over your head, then who am I to say you're not an astronomer? However you define astronomy,
not.
humans have been looking up at the sky for as long as
I love
we've
astronomy,
been
but I'm
human.
not an
Certainly,
astronomer.
ancient people noticed the big glowy ball in the sky and how it lit everything up while it was up, and how it got dark when it was gone. The other fainter glowy thing tried, but wasn't quite as good at lighting up the night. They probably took that sort of thing pretty seriously. They probably also noticed that when certain stars appeared in the sky, the weather started getting warmer and the days longer. And when other stars were seen, the weather would get colder and daytime shorten. And when humans settled down, discovered agriculture, and started farming, noticing those patterns in the sky would have had an even greater impact. It told them when to plant seeds and when to harvest. The cycles in the sky became pretty important. So important that it wasn't hard to imagine gods up there, looking down on us weak and ridiculous humans, interfering with our lives. Surely if the stars tell us when to plant and control the weather, seasons, and the length of the day, they control our lives too. And astrology was born. Astrology literally means study of the stars. As a word, it's been used before science became a formal method of studying nature. It irks me a bit since it got the good name and now we're stuck
I'm just
with
gonna stay
astronomy,
muted until I
which
get
means
talked to.
law
I'm gonna
or
watch this.
culture of the stars, and that's not really what we do. But what the heck,
if I had
words
a
change
comment.
meaning over time, and now it's pretty well understood that astronomy is science and astrology isn't. Millennia
bullshit.
ago, astrology was as close to science as you got. It had some of the flavors of science. Astrologers observed the skies, made predictions about how it would affect people, and then those people would provide evidence for it by swearing up and down it worked. The thing is, it really didn't. The fault of astrology lies in ourselves and not our stars. People tend to remember the hits and forget the misses when predictions are made, which is why they sometimes sit in casinos pumping nickels into machines that are proven to be nothing more than a method for reducing the number of nickels you have. But astrology led people to really study the sky and find the
Yep.
patterns there,
Gambly.
which led to a more rigorous understanding of how things really worked in the heavenly vault. It wasn't overnight, of course. This took centuries. Before the invention of the telescope, keen observers built all sorts of odd and wonderful devices to measure the heavens. And in fact, it was before the telescope was first turned to the sky that a huge revolution in astronomy took place. It is patently obvious that the ground you stand on is fixed, rooted if you will, and the skies turn above us. The sun rises, the sun sets. The moon rises and sets. The stars themselves wheel around the sky at night. Clearly, the Earth is motionless and the sky is what is actually moving. In fact, if you think about it, geocentrism makes perfect sense, that all the objects in the sky revolve about the Earth and are fixed to a series of nested spheres, some of which are transparent, maybe made of crystal, which spin once per day.
It would make sense to me if I didn't know
The stars
better.
may just be holes in otherwise opaque spheres, letting sunlight through. Sounds silly to you, doesn't it? Well, here's the thing. If you don't have today's modern understanding of how the cosmos works, this whole multiple shells of things in the sky thing actually does make sense. It explains a lot of what's going on over your head. And if it was good enough for Plato, Aristotle, and Ptolemy, then by God, it was good enough for you. And speaking of which, it was endorsed by the major religions of the time, so maybe it's better if you just nod and agree and don't think about it too hard. But a few centuries ago, things changed. Although he wasn't the first, the Polish mathematician and astronomer Copernicus came up with the idea that the sun was the center of the solar system, not the Earth. His idea had problems, which we'll get to in a later episode, but it did an incrementally better job than geocentrism. And then along came Tycho Brahe and Johannes Kepler, who modified that system, making it even better. Then Isaac Newton. Newton. He invented calculus, partly to help him understand the way objects moved in space. Over time, our math got better, our physics got better, and our understanding grew. Applied math was a revolution in astronomy, and then the use of telescopes was another. Galileo didn't invent the telescope, by the way, but made them better. Newton invented a new kind that was even better than that, and we've run with the idea from there. Then, about a century ago, came another revolution: photography. We could capture much fainter objects on glass plates sprayed with light-sensitive chemicals, which revealed stars otherwise invisible to us, details in galaxies, beautiful clouds of gas and dust in space. And then, in the latter half of the last century, digital detectors were invented, which were even more sensitive than film. We could use computers to directly analyze observations, and our knowledge leaped again. When these were coupled with telescopes sent into orbit around the Earth, where our roiling and boiling atmosphere doesn't blur out observations, we began yet another revolution. And where are we now? We've come such a long way. What questions can we routinely ask that our ancestors would not have dared? What statements made with a pretty good degree of certainty? Think on this. The lights in the sky are stars. There are other worlds. We take the idea of looking for life on alien planets seriously and spend billions of dollars doing it. Our galaxy is one of 100 billion others. We can only directly see 4% of the universe. Stars explode. And when they do, they create the stuff of life. The iron in our blood, the calcium in our bones, the phosphorus that is the backbone of our DNA. The most common kind of star in the universe is so faint you can't even see it without a telescope. Our solar system is filled to overflowing with worlds more bizarre than we could have dreamed. Nature has more imagination than we do. It comes up with some nutty stuff. We're clever too, we big-brained apes. We've learned a lot, but there's still a long way to go. So with that, I think we're ready. Let's explore the universe. Today, you learned what astronomy is, and that astronomers aren't just people who operate telescopes, but include mathematicians, engineers, technicians, programmers, and even artists. We also wrapped up with a quick history of the origins and development of astronomy, from ancient observers to the Hubble Space Telescope. Crash Course is produced in association with PBS Digital Studios. This episode was written by me, Phil Plait. The script was edited by Blake DiPastino, and our consultant is Dr. Michelle Thaller. It was co-directed by Nicholas Jenkins and Michael Aranda, and the graphics team is Thought Cafe. Hey, Phil Plait here. Welcome to episode 2 of Crash Course Astronomy, Naked Eye Observations. Despite the salacious title, nudity is not required. In fact, given that a lot of astronomical observations are done at night, you may want to bundle up. As it relates to astronomy, naked eye means no binoculars, no telescope. Just you, your eyeballs, and a nice dark sight from which to view the heavens. After all, that's how we did astronomy for thousands of years, and it's actually pretty amazing what you can figure out about the universe just by looking at it. Imagine you're somewhere far away from city lights, where you have an unobstructed view of the cloudless sky. The sun sets, and for a few minutes you just watch as the sky darkens. Then you notice a star appear in the east, just over a tree. Then another, and another. And within an hour or so, you are standing beneath an incredible display, the sky spangled with stars. What do you notice right away? First, there are a lot of stars. People with normal vision can see a few thousand stars at any given time. And if you want a round number, there are very roughly 6,000 to 10,000 stars in total that are bright enough to detect by eye alone, depending on how good your sight is. The next thing you'll notice is that they're not all the same brightness. A handful are very bright, a few more are a bit fainter but still pretty bright, and so on. The faintest stars you can see are the most abundant, vastly outnumbering the bright ones. This is due to a combination of two effects. One is that stars aren't all the same intrinsic physical brightness. Some are dim bulbs, while others are monsters, blasting out as much light in 1 second as the sun does in a day. The second factor is that not all stars are the same distance from us. The farther away a star is, the fainter it is. Interestingly, of the 24 or so brightest stars in the sky, half are bright because they're close to Earth, and half are much farther away, but incredibly luminous, so they still appear bright to us. This is a running theme in astronomy and science in general. Some effects you see have more than one cause. Things aren't always as simple as they seem. The ancient Greek astronomer Hipparchus is generally credited for creating the first catalog of stars, ranking them by brightness. He came up with a system called magnitudes, where the brightest stars were first magnitude, the next brightest were second magnitude, down to sixth magnitude. We still use a variation of this system today, thousands of years later. The faintest stars ever seen using Hubble Space Telescope are about magnitude 31. The faintest star you can see with your eye is about 10 billion times brighter. The brightest star in the night sky, called Sirius, the dog star, is about 1,000 times brighter than the faintest star you can see. Let's take a closer look at some of those bright stars, like, say, Vega. Notice anything about it? Yeah, it looks blue. And Betelgeuse looks red. Arcturus is orange, Capella, yellow. Those stars really are those colors. By eye, only the brightest stars seem to have color, while the fainter ones all just look white. That's because the color receptors in your eye aren't very light sensitive, and only the brightest stars can trigger them. Another thing you'll notice is that stars aren't scattered evenly across the sky. They form patterns, shapes. This is mostly coincidence, but humans are pattern-recognizing animals, so it's totally understandable that ancient astronomers divided the skies up into constellations, literally sets or groups of stars, and named them after familiar objects. Orion is probably the most famous constellation. It really does look like a person, arms raised up, and most civilizations saw it that way. There's also Tiny Delphinus. It's only 5 stars, but it's easy to see it as a dolphin jumping out of the water. And Scorpius, which isn't hard to imagine as a venomous arthropod. Others, well, not so much. Pisces is a fish? Yeah, okay. Cancer is a crab? If you say so. Although they were rather arbitrarily defined in ancient times, today we recognize 88 official constellations, and their boundaries are carefully delineated on the sky. When we say a star is in the constellation of Ophiuchus, it's because the location of the star puts it inside that constellation's boundaries. Think of them like states in the US. The state lines are decided upon by mutual agreement, and a city can be in one state or the other. Mind you, not every group of stars makes a constellation. The Big Dipper, for example, is only one part of the constellation of Ursa Major, the Big Bear. The bowl of the Dipper is the bear's haunches, and the handle is its tail. But bears don't have tails, so astronomers might be great at pattern recognition, but they're terrible at zoology. Most of the brightest stars have proper names, usually Arabic. During the Dark Ages, when Europe wasn't so scientifically minded, it was the Persian astronomer Abd al-Rahman al-Sufi who translated ancient Greek astronomy texts into Arabic, and those names have stuck with us ever since. However, there are a lot more stars than there are proper names, so astronomers use other designations for them. The stars in any constellation are given Greek letters in order of their brightness. So we have Alpha Orionis, the brightest star in Orion, then Beta, and so on. Of course, you run out of letters quickly too, so most modern catalogs just use numbers. It's a lot harder to run out of those. Of course, just seeing all those faint stars can be tough, which brings us to this week's Focus On. Light pollution is a serious problem for astronomers. This is light from street lamps, shopping centers, or wherever, where the light gets blasted up into the sky instead of toward the ground. This lights up the sky, making fainter objects much more difficult to see. That's why observatories tend to be built in remote areas, as far from cities as possible. Trying to observe faint galaxies under bright sky conditions is like trying to listen to someone 50 feet away whispering at you at a rock concert. This affects the sky you see as well. From within a big city, it's impossible to see the Milky Way, the faint glowing streak across the sky that's actually the combined light of billions of stars. It gets washed out with even mild light pollution. Your view of Orion probably looks like this, when from a dark site, it looks like this. It's not just people who are affected by this either. Light pollution affects the way nocturnal animals hunt, how insects breed, and more by disrupting their normal daily cycles. Cutting back light pollution is mostly just a matter of using the right kind of light fixtures outside, directing the light down to the ground. A lot of towns have worked to use better lighting and have met with success. This is due in large part to groups like the International Dark Sky Association, Globe at Night, The World at Night, and many more, who advocate using more intelligent lighting and to help preserve our night sky. The sky belongs to everyone, and we should do what we can to make sure it's the best possible sky we can see. Even if you don't have dark skies, there's another thing you can notice when you look up. If you look carefully, you might see that a couple of the brightest stars look different than the others. They don't twinkle. That's because they aren't stars. They're planets. Twinkling happens because the air over our heads is turbulent, and as it blows past, it distorts the incoming light from stars, making them appear to slightly shift position and brightness several times per second. But planets are much closer to us and appear bigger, so the distortion doesn't affect them as much. There are 5 naked-eye planets, not counting Earth: Mercury, Venus, Mars, Jupiter, and Saturn. Uranus is right on the edge of visibility, and people with keen eyesight might be able to spot it. Venus is actually the 3rd brightest natural object in the sky after the Sun and Moon. Jupiter and Mars are frequently brighter than the brightest stars, too. If you stay outside for an hour or two, you'll notice something else that's pretty obvious. The stars move, like the sky is a gigantic sphere wheeling around you over the course of the night. In fact, that's how the ancients thought of it. If you could measure it, you'd find this celestial sphere spins once every day. Stars toward the east are rising over the horizon, and stars in the west are setting, making a big circle over the course of the night, and presumably day. This is really just a reflection of the Earth's spinning, of course. The Earth rotates once a day, and we're stuck to it, so it looks like the sky is spinning around us in the opposite direction. There's an interesting thing that happens because of this. Look at a spinning globe. It rotates on an axis that goes through the poles, and halfway between them is the equator. If you stand on the equator, you make a big circle around the center of the Earth over a day. But if you move north or south toward one pole or the other, that circle gets smaller. When you stand on the pole, you don't make a circle at all. You just spin around in the same spot. It's the same thing with the sky. As the sky spins over us, just like with the Earth, it has 2 poles and an equator. A star on the celestial equator makes a big circle around the sky, and stars to the north or south make smaller ones. A star right on the celestial pole wouldn't appear to move at all, and would just hang there like it was nailed to that spot all night long. And this is just what we see. Photographic time exposures show it best. The motions of the stars show up as streaks. The longer the exposure, the longer the streaks as the stars rise and set, making their circular arcs in the sky. You can see stars near the celestial equator making their big circles. And by coincidence, there's also a middling bright star that sits very close to the north celestial pole. That's called Polaris, the north or pole star. Because of that, it doesn't appear to rise or set, and it's always to the north, motionless. It really is coincidence. There's no southern pole star, unless you count Sigma Octans, a dim ball barely visible by eye. That's not all that close to the south pole of the sky anyway. But even Polaris isn't exactly on the pole. It's offset a teeny bit, so it does make a circle in the sky, but one so small you'd never notice. By eye, night after night, Polaris is the constant in the sky, always there, never moving. Remember, the sky's motion is a reflection of the Earth's motion. If you were standing on the north pole of the Earth, you'd see Polaris at the sky's zenith, that is, straight overhead, fixed and unmoving. Stars on the celestial equator would appear to circle the horizon once per day. But this also means that stars south of the celestial equator can't be seen from the Earth's north pole. They're always below the horizon. So this in turn means that which stars you see depends on where you are on Earth. At the North Pole, you only see stars north of the celestial equator. At the Earth's South Pole, you only see stars south of the celestial equator. From Antarctica, Polaris is forever hidden from view. Standing on the Earth's equator, you'd see Polaris on the horizon to the north, and Sigma Octans on the horizon to the south. And over the course of the day, the entire celestial sphere would spin around you. Every star in the sky is eventually visible. While Polaris may be constant, not everything is. Sometimes you just have to wait a while to notice. And to that point, you'll have to wait a while to find out what I mean by this, because we'll be covering that in next week's episode. Today we talked about what you can see on a clear, dark night with just your eyes. Under a dark sky, you can see thousands of stars. If you watch for a few hours, you can see them rise and set as the Earth rotates once a day. And if you go outside the next night at the same time, you'll see that things look pretty much the same as they did the night before. The stars rise and set, Polaris hangs to the north, and so on. One day hardly makes any difference to the sky's appearance. But what if you wait for another night, or a week? If you're that patient and observant, you can spot subtle changes in the sky. Let's say a couple of weeks have passed. Remember that star that was just over a tree in the east when the sun set? The one that made you first notice the stars are rising and setting? Go look at it again. If you happen to be out at the same time, you'd expect that star to be in the same place. But it's not. It's actually a bit higher above the tree. And if you look west, stars that were well off the horizon just after sunset last week are now lower. If you wait a month, this effect is even more pronounced. All new constellations will be visible in the sky after sunset. This is because the Earth is going around the sun, literally changing our viewpoint on the sky. The Earth takes a year to orbit the sun once. Every day, it moves a little bit along its orbit. And as it does, from Earth's perspective, distant stars appear to move their positions relative to the sun. So one day we might see a star very near the sun, but the next day the angle is a bit bigger. At some point, about 6 months after we first saw it, the star is directly opposite the sun in the sky. Then the angle starts to shrink again as the star approaches the sun from the opposite side until, after a full year, the cycle repeats. What this means to you, the naked eye observer, is that the stars appear to rise and set at different times over the course of the year. Stars in the east rise about 4 minutes earlier every night, and stars in the west set 4 minutes earlier. A constellation that was entirely below the eastern horizon at sunset one month might be completely visible after sunset the next month. Another way to think about it is that the stars appear to be fixed, and as the Earth circles the sun moves through the stars over the course of the year, making a complete circle around the sky once per year. The path it takes is a reflection of the Earth's path around the sun, a line in the sky. We call that line the ecliptic. That means the sun passes through the same constellations in the sky every year. We give those constellations a special name, the zodiac. Every year, during a given month, the sun will appear to be in a certain zodiacal constellation, from Sagittarius through Scorpius, Libra, Virgo, Leo, Cancer, and the rest. Eventually, over a year, the sun returns to Sagittarius and the cycle starts again. But even though we talk about this process in terms of the sun's movement, it's really the path traveled by the Earth that creates this effect, as our perspective moves with it. And of course, the planets move in the sky as well. Mercury, Venus, Mars, they orbit the sun too, and they do so in approximately the same plane the Earth does. If you could see the solar system from the side, it would look flat. So to us on Earth, the planets go around the sky over the course of a year, and they also appear to change their positions relative to the sun and the stars. The inner planets, Mercury and Venus, move so rapidly you can see their motion after a single night. The outer planets are more leisurely, but wait long enough and they too will be seen to move, sliding through the constellations. By the way, the word planet is Greek for wanderer. There's another aspect of all this you might notice over time. You've probably seen a globe and noticed that the axis of it is tilted. That is, it's not straight up and down, perpendicular to how it sits. That's because a globe is modeling the Earth, and the Earth is tilted. The Earth spins on its axis once per day and orbits the sun once per year. But the Earth's axis is tilted with respect to its orbital plane by 23.5 degrees. And this has a profound effect on our planet. Imagine for a moment that the Earth's axis were exactly perpendicular to its orbit, straight up and down. If that were the case, every day, the sun would take the same path across the sky. If you were on the equator, the sun would rise, go exactly overhead, and then set. If you're on the pole, the sun would appear to go around the horizon every day, neither rising nor setting. It would always be twilight. But that's not the case. The Earth is tilted. In the months of June and July, the Earth's north pole is tipped toward the sun. 6 months later, it's pointed away. This affects the path the sun takes across the sky. Instead of it taking the same path every day, in the northern summer, when we're tipped toward the sun takes a higher path in the sky. Because that path is longer, the days are longer too. 6 months later, in December and January, the Earth's pole is tipped away. The sun takes a lower path in the sky, and because the path is shorter, days are shorter too. That's why we have seasons. When the sun is up high in the sky, it shines straight down on the ground, heating it better. And days are longer, so it has more time to heat us up. It gets hot. In the winter, it's the reverse. The sun is lower, so it can't warm us up as efficiently, and it has less time to do so. It gets cold. There you go. Seasons. The Earth's axis is tipped. If it weren't, the seasons wouldn't occur, and the temperature of the Earth wouldn't change month to month. There's a common misconception that the Earth has seasons because it orbits the sun on an ellipse, and so it's closer to the sun in summer and farther in winter. While it's true the orbit is elliptical, Earth is closer to the sun in January, on the order of 5 million kilometers or so, than it is in July. It's the angle of the sun's rays that makes winter cold and summer hot, not our distance from the sun. Also, you may know that when it's summer in the northern hemisphere, it's winter in the southern. When the North Pole is tipped toward the sun, the South Pole is tipped away. So northern and southern hemisphere seasons are opposite each other. But nothing in astronomy is permanent. The North Pole's not always going to point toward the sun in June, and Polaris is not always going to be the North Star. That's because our planet's axis is actually moving. Have you ever seen a spinning top start to wobble, its axis moving in a slow circle even as the top itself spins? This is called precession, and the Earth does it too. Our planet spins on its axis once per day, but the axis wobbles, making a very slow circle that takes 26,000 years to complete. This affects a lot of what we see in the sky. For example, Polaris won't always be the pole star. Every year, the pole points a little farther from that star, making a big circle 47 degrees across. For ancient Egyptians, the star Thuban was the pole star, and in about 11,000 years, that position will be held by the bright star Vega. Also, the date the sun is in a particular zodiac constellation changes slowly due to precession as well. When the ancients first thought up this idea, the sun was in Aries on March 22nd, the vernal equinox, what some people call the first day of spring. But due to precession, it's now in Pisces. That's why your astrological sign doesn't match where the sun actually is in the sky. 2,000 years of precession has changed them, one of the many reasons astrology is silly. It's incredible to think about. The Earth, the sun, the stars. They allow us to tell the time and time of year just by looking up and paying attention. This is why the stars were so important to ancient humans. The stars were like a clock and a calendar in the sky, long before we had invented either. We've actually learned a lot about the sky, just by looking at it. Of course, some of the stuff I've explained we've learned through other means. The Earth is spinning, stars have different intrinsic brightnesses, and so on. But all of that knowledge, and far more, got its start by people who went outside and looked up. Later, as we applied math and physics to what we observed, we learned even more, and could then go back and explain what we saw. So don't discount naked eye astronomy. It's all we had for thousands of years. In fact, I think we lost something when we started using clocks and calendars and moving to cities with bright lights that washed away the stars from the sky. Those folks long ago were tied to the sky. They knew it like you know the streets in your neighborhood. They could see the stars rise and set. They knew the glory of the Milky Way sprawled across the heavens, even if they didn't know exactly what it was. We do know now, with our knowledge gained over the centuries. But it comes at the cost of losing touch with the sky, not living under it as much as we once did. I've spent thousands of hours over my life at night just simply looking up, watching the stars, appreciating the universe as I can see it. The things I have witnessed have shaped my life and instilled in me a permanent and endless sense of wonder and joy. The universe belongs to everyone. Go outside, and if you can, soak up your share. Today we talked about cycles. As the Earth goes around the sun, we see stars rising and setting at different times. The sun moves along a line in the sky called the ecliptic, through a set of constellations called the zodiac, really a reflection of the Earth's motion around the sun. That the planets move more or less along the ecliptic as well, and that seasons are caused by the tilt of the Earth's axis, together with its annual orbit around the sun. Crash Course is produced in association with PBS Digital Studios. This episode was written by me, Phil Plait. The script was edited by Blake DiPastino, and our consultant is Dr. Michelle Thaler. It was co-directed by Nicholas Jenkins and Michael. Besides the sun, the moon is the most obvious object in the sky. Bright, silvery, with tantalizing features on its face, it's been the target of imagination, poetry, science, and even the occasional rocket. If If you pay even the most cursory attention to it, you'll see that it changes every day. Sometimes it's up in the day, sometimes at night, and its shape is always changing. What causes this behavior? The moon is basically a giant ball of rock 3,500 kilometers across, hanging in space. Its surface is actually pretty dark, with about the same reflectivity as a chalkboard or asphalt. However, it looks bright to us because it's sitting in full sunlight. The sun illuminates it, and it reflects that light down to us here on Earth. And because it's a sphere and orbiting the Earth, the way we see it lit by the sun changes with time. That's what causes its phases. Geometry. The important thing to remember through all of this is because the moon is a ball and in space, half of it is always illuminated by the sun. This is true for the Earth too, and every spherical object in space. Half faces the sun, half faces away. We call the part facing the sun the daylight or bright side, and the half facing away the night or dark side. The phase of the moon refers to what shape the moon appears to us, how much of it we see illuminated from the Earth. The key to all this is this line, dividing the lit day side from the unlit night side. We call that line the terminator. If you're facing the moon with the sun behind you, you're seeing the half of the moon that is fully illuminated by sunlight, and it looks full. If you're off to the side, you see half of the lit side and half of the dark side, and we say the moon is half full. If the sun is on the other side of the moon, you're looking at the unlit half, and it looks dark. Now, mind you, I haven't moved anything except our point of view here. So at all times, the moon is always half lit and half dark. Remember that. The phase of the moon we see depends on from what direction the sunlight's hitting it, and the angle we see that from Earth. The moon orbits the Earth roughly once per month. In fact, that's where the word month comes from. Month and moon are cognates, words that have similar etymological histories. And in most languages, including English, the two words are very similar. The length of time we call the month is derived from the length of time it takes the moon to go through all of its phases, 29 and a half days. So, to describe the phases, let's start at the beginning. New moon. New moon happens when the sun, moon, and Earth are all more or less in a line. The moon's orbit is actually tipped a bit to the Earth's, so sometimes the new moon happens when the moon is below the sun or above it. But at some point in its orbit, at some point in the month, it appears to be as close to the sun as it can. What does this look like from the Earth? The moon is between the Earth and the sun. So from our perspective, we only see the dark half, the unilluminated half of the moon. The other side, the far side of the moon, is lit, but we can't see it. It makes sense then to call this the beginning of the moon's cycle, hence the term new moon. Now think about this for a sec. Because the moon is near the sun in the sky, it travels across the sky with the sun. It's up during the day. You can only see it from the part of the Earth that's lit, which is when it's daytime. It's a very common misconception that the moon is only up at night, but it's up during the day literally just as often. At new moon, the moon stays near the sun, so it rises at sunrise and sets at sunset. This makes it extremely difficult to see. It is, after all, sitting next to the brightest object in the sky, and only a little bit of it is lit from our perspective. But not for long. Because the moon is orbiting the Earth, after a couple of days, it's moved a bit to the east. Now we're seeing it along a slight angle, and we can see a little bit of the illuminated half of the moon on its side toward the sun. The terminator, the day-night line, appears curved around the moon. So what we see is a thin, illuminated crescent moon. At this point, the crescent is still very thin, with the horns of the crescent pointing away from the sun. Note that the moon is still pretty close to the sun in the sky, just a bit to the east, rising maybe an hour or two after sunrise. But this means it's up all day and then sets after the sun does. This is the best time to see the crescent moon, when the sun is already set and the sky starts to get dark. The moon will be low over the western horizon, and it'll set soon after the sun does. Let's wait a couple of days. Okay, now the moon has moved a bit more in its orbit around the Earth, and is farther from the sun in the sky. We see a little more of the illuminated part, and the crescent is wider. Since it's getting thicker, we say this is a waxing crescent moon. Waxing means growing or getting bigger. It's also well away from the sun now, so it's easier to spot even during the day before sunset. 7 or so days after new moon, we get to our first milestone. The moon is now 1/4 of the way around its orbit. It's 90 degrees away from the sun in the sky, which means we're looking straight down on the terminator, the moon's day-night line. It cuts right down the middle of the visible face of the moon. It's not called the terminator. So it's half lit. I don't know why he calls that. With the sunward side of the moon visible,
called the twilight
and the
zone
other side dark.
Why are you calling it terminator?
This phase
Did they change the name of it or something?
Quarter, because the moon is 1/4 of the way through its cycle, 1/4 of the way through its orbit around the Earth, even though it looks half full. So it's not really the half full moon. Astronomers prefer first quarter, So if you want to sound all astronomery, then you should call it that. But time marches on. The moon continues on its gravitational dance with Earth, swinging around its orbit. Now more than half full, we say its shape is gibbous, which means swollen or convex. Since it's getting wider, this is actually the waxing gibbous phase of the moon. It rises in the late afternoon and is up most of the night. Our next big step comes 2 weeks after new moon, when it's moved halfway through its orbit. It's now opposite the sun in the sky, 180 degrees around. The Earth is between the moon and sun, so we're looking at the fully illuminated half of the moon.
Shadow?
This is the
Am I going to have
full
to go
moon.
watch
Because
Star
it's
Trek?
opposite the sun, it rises at sunset and sets at sunrise. It's up all night shining down on Earth. But again, wait a couple of days and things change. When the moon is full, it's 180 degrees around the sky from the sun. So as it continues to move around the Earth in a circle, the distance between it and the sun is now starting to decrease, even as it continues on in the same direction. As before, it keeps rising and setting later, but now it rises after sunset and sets after sunrise. If you get up early in the morning as the sun is just rising in the east, you'll see the nearly but not quite full moon setting in the west. Not only that, but we're about to go through all the phases again, but in reverse order. A few days after full moon, the lit side is shrinking. It's in the waning or shrinking gibbous phase. Then, 3 weeks or so after new moon and a week after full, the moon is once again half lit, the terminator splitting the moon's face in 2 even halves. This is the third quarter moon because the moon is 3/4 of the way through its cycle. It's a lot like first quarter, but the side that was lit is now dark and vice versa. It's 270 degrees.
Maybe there's
around
a
the
difference
skies
between
and
a
sun.
Terminator
It rises at
and
midnight
a Twilight
and sets at
Zone.
noon. A few
That's
days
two different
later,
things,
and the moon
perhaps.
is a crescent again, getting thinner. It's now a
That's
waning
what it's called, the
crescent.
Twilight Zone.
It rises just a couple of hours before sunrise and sets a couple of hours before sunset. Then, finally, we're back where we started. 1 month after new moon, the moon has traveled 360 degrees around the sky and is once again as close to the sun as it can get. It's new moon, and the cycle starts up again, as it has for time immemorial. An interesting thing happens if you move your perspective
You didn't
from
happen
the
to go
Earth
download
to the
Star
moon.
Trek Online yet,
The
have you,
phases
Shadow?
of the moon we see from Earth depend on the angle of the moon and the sun in the sky. But on the moon, the angles are exactly 180 degrees reversed. At new moon, when the moon is between the Earth and sun, the Earth is opposite the sun as seen from the moon. It's full Earth. All the other phases are opposite too. So when we see a full moon, a moon dweller would see a new Earth, and so on. Have you ever looked at the thin crescent moon and seen the ghostly face of the rest of the unlit side? That's because it's not really
Smart
unlit. The
man.
nearly full
Smart
Earth is
man, Mr.
reflecting
Shadow.
sunlight on the moon, lighting up the otherwise dark part. The Earth is bigger and more reflective than the moon, so it's actually 50 times brighter than a full moon. This glow is called Earthshine, a term I quite like. Even more poetically, it's been called the old moon in the new moon's arms, referring to the unlit part surrounded by the crescent new moon's horns. That's lovely, isn't it? The moon is one of the most beautiful and most gratifying objects in the sky to observe. It's different every day, yet it's also the same because we see more or less the same half of it, the same face all the time. It's big and bright, and the features on its surface discernible
managed to
by
get
eye,
myself
and even
out of
better
it.
with binoculars or a small telescope. As the
That was
phases
one of the lucky
change
few.
inexorably, day after day, the angle of sunlight hitting the surface changes, bringing new things into our view. The motions become comforting, even familiar. It's a reminder that the universe may seem strange and complicated and forbidding at first, but over time, as you get outside and experience it, it becomes your neighborhood. Welcome home. Today you learned why the moon has phases. It's a sphere and it orbits the Earth, so the angle at which we see its
We're still
we
into the
humans of
baby
planet
stuff
Earth
here.
benefit from a great coincidence.
Mars and
it's
the
a
moon
coincidence
and
of
Earth,
time
the
and
phases.
of space and of math. The
We get
coincidence
into
is
the
this.
good shit soon.
The sun is about 400 times wider than the moon, and it's also, on average, about 400 times farther away than the moon. The apparent size of an object in the sky depends on how big it is and how far away it is. So these numbers being equal means the sun and the moon appear to be about the same size in the sky. And that's where another interesting thing comes in. Sometimes the moon passes directly between the Earth and the sun. It doesn't happen all that often, but when it does, you get magic. Or even better, you get science. You get an eclipse. An eclipse is a generic term in astronomy for when one object passes into the shadow of another object.
I had watched a
darkening
few of
or
the
blocking. A
advanced
solar
episodes
eclipse
here, and
is when
they
the
start
moon
getting into
blocks the
some
sun,
really,
casting a
really
shadow
cool
on the Earth.
stuff.
And a
We're
lunar
still in the
eclipse is
early
when the
baby
Earth
stuff here,
blocks
where
the sun,
eclipses
casting a
and
shadow on the moon.
probably
But how
just
do they
like the
work?
planets
Well,
and
the moon
crap
orbits
and
the Earth
whatever.
once per month, and the
For
Earth
me,
orbits the
that's
sun once per year. If the
baby
moon's
stuff.
orbit were perfectly
But if
aligned with the
you're not
Earth's,
into
essentially
astronomy,
sharing the same
it's all
plane,
interesting.
we'd get a solar eclipse every new moon and a lunar eclipse every full moon. But we don't. That's because the moon's orbit is tilted with respect to the Earth's by about 5 degrees. What that means is that at new moon, the moon can be as much as 5 degrees away from the sun, passing above or below the sun in the sky, thereby missing it from our perspective. But sometimes the moon is in the right place at the right time, and at new moon it lies perfectly in line between the sun and the Earth. And when that happens, we get a solar eclipse. This geometry
Wanted to be
happens
an
at least
astronomer.
twice per year, and sometimes as much as 5
What
times
this
per
guy
year.
does.
What's happening physically in space is that the moon is casting a long shadow. Usually that shadow misses the Earth, but during an eclipse, the moon's shadow falls on the Earth's surface. In fact, there are 2 shadows from the moon, one inside the other. One is a narrow cone tapering to a point away from the moon. If you're anywhere physically inside this cone, the moon appears big enough to completely block the sun. That means the shadow is very dark, and we call it the umbra, which is Latin for, you guessed it, shadow. Outside of this deep umbral shadow is a wider conical region where, if you're in it, the sun is only partially blocked. You can still see some of the sun past the moon. You're getting less light, and so you're technically shadowed, but it's not quite as dark as the umbra. This region is called the penumbra. Pen in this case for Latin meaning almost or nearly. When the umbra touches the Earth, we get a total solar eclipse. But what does that look like from the ground? You don't get a total solar eclipse right away. First, the edge of the moon slips in front of the sun, and we see a little dip in the sun's limb, its edge as seen from the Earth. That's the
Best
start
angle
of
I
the
can get.
penumbra sweeping over you. As the moon slowly moves, that dip grows, becoming a bite. The sun becomes a thick crescent, then a thin one. As the sun becomes an ever thinner crescent, the sky begins to darken. Then, finally, the moon's black disk completely covers the sun. The umbra sweeps over your location, and at that moment, totality begins. You might think that this just means the sky gets dark and it's like night outside for a while. But a total eclipse is far more than that, and that's because of the sun's corona. As I'll cover in more detail in a future episode, the corona is the sun's atmosphere, an ethereally thin envelope of gas that stretches from the sun's surface into space for millions of kilometers. It's really faint and therefore usually completely overwhelmed by the intensely bright light from the sun. But when the moon blocks the sun's face, the corona becomes visible. It surrounds the sun, filaments and tendrils extending into the sky, an incredibly beautiful sight. I know many people who have said it's the most spectacular thing they have ever seen. And there's more. The moon's edge isn't
Sorry,
smooth.
Shadow.
There are craters and other depressions. Craters right at the moon's edge allow
I'm not
sunlight
gonna
to
let Bart
stream
step
past.
on class.
We see these as bright patches
that?
around
Out in the
the
hall.
Earth's sun, which are called
Out in the
Bailey's
hall,
beads,
Shadow.
because they were first described by English astronomer Francis Bailey in 1836. Because the moon and sun are very nearly the same apparent size, totality is brief. The longest it can last is only about 7 or 8 minutes. That's how long it takes the umbra to move over one spot on the Earth. When totality ends and the moon starts to move off of the sun's face, for a moment, just a single spot of the sun is unblocked, glowing fiercely on one side of the moon. Sometimes you can get a circle of light around the moon's surface, and together with the bright spot, it looks like a celestial wedding ring. In fact, this is called the diamond ring effect. Then, inexorably, the moon pulls away from the sun, and the order of events is reversed. The umbra is gone, but you're still in the penumbral shadow. The sun shows a thin crescent, then a thick one, then a dip in its side, and then it's all over. The umbral shadow of the moon is pretty small where it hits the Earth, so a total eclipse is a local event. If you're too far north and south, you don't get a total eclipse, you only get a partial one, which is still cool, but lacks the mystique of a total eclipse. Remember too that the moon's orbit around the Earth is an ellipse. That means sometimes it's closer to the Earth and sometimes farther. If a solar eclipse happens when the moon is at the far end of its orbit, it can actually be smaller than the sun in the sky. It doesn't block the entire face of the sun.
Not gonna lie,
and it
my
leaves
man,
a
that
ring of
American
light
Truck
around the
Simulator
black
looks
circle of the
boring
moon.
as
The
fuck.
technical name for this shape is annulus, so this event is called an annular eclipse.
I'm sure
A
if
lot
I
of
were
people
playing,
think
it'd
if
be
you look
fun,
at a
but
total solar
to
eclipse,
watch,
you can go
oh boy.
permanently and completely blind. That's really not true, but some parts of eclipse watching are more dangerous than others. I mean, obviously, it's not a good idea to stand there and stare at the sun. Looking at even the uneclipsed sun for more than a moment is painful, and that pain is the
Sometimes I
result
don't
of the
understand
damage
why
that solar radiation
people
is
fire
doing
up
to your
Power
retinas.
Wash
So I
Simulator and
don't
say, hey,
recommend
this
it.
looks like a
But
good
when
thing to
viewing
stream.
an eclipse, the real concern is right after
Okay, buddy.
totality ends. During totality, it's dark. so your pupils have dilated to let more light in. But then there's the flash of sunlight when the moon moves off, and that's intense enough to damage your retinas. That's why astronomers recommend extreme caution when viewing an eclipse, because that flash can catch you by surprise. When viewing the sun, don't just stand there and stare at it. You
Esports
should
Power Wash
always have eye
Simulator?
protection.
Hell
Make
yeah.
sure you
let's
have
check that
safety-approved
shit up.
filters. Don't try the homemade tricks you might have heard of, like looking through an old CD or DVD or using old-style camera film as a filter. These can let through too much infrared and ultraviolet light, and again can dilate your pupils, actually making things worse. Lots of companies make inexpensive filters that are great for sunspotting. We have links in the doobly-doo for more information on eye safety. Now, you don't have to worry about hurting your eyes at all when viewing a lunar eclipse, because in that case, it's the Earth that blocks the sun, and the Earth's shadow falls on the moon. So go nuts! But one big difference between the two kinds of eclipses is who can see them. A solar eclipse is localized to one spot on the Earth, or really a swath along the ground as the moon's umbral shadow
I think it'd be
sweeps
fun if
across
you had
the
a bunch
Earth's
of people
surface.
in
But a
there
lunar
crashing
eclipse is
trucks
when the
together.
moon moves into
Hell,
Earth's
there
shadow.
we go. Now
So
we're talking.
anyone on Earth facing the moon
Might
can
as well
see
just
a
go play
lunar
GTA
eclipse.
at that point.
This is why I've seen dozens of lunar eclipses, but never a total solar one. I've never been at the right place at the right time. Not that I'm bitter. The Earth has umbral and penumbral shadows too. When the moon first enters the Earth's penumbra, the dimming is so slight you hardly notice it. But as the moon moves deeper into the penumbra, it starts to darken. Sometimes it changes color, turning a deep orange or blood red. That's because the Earth is starting to block the sunlight heading toward the moon, and the only light that gets through is coming through the thickest part of our atmosphere. This blocks blue and green light, leaving only red to come through. That's why the moon and sun look red to us when they're on the horizon, rising and setting too. When you look upon the red eclipsed moon, you're seeing the light from all the sunrises and sunsets in the world hitting the moon and reflecting back to us. Finally, the moon starts to enter the Earth's umbra, and the real eclipse begins. At first it looks like a bite is taken out of it. That curving arc is the shadow of the edge of the Earth. The moon moves deeper and deeper into the shadow until it's completely darkened. The Earth is bigger than the moon, so the Earth's umbra is much wider. While a solar eclipse is over in minutes, a total lunar eclipse can last nearly 2 hours. I once saw a lunar eclipse so deep that it took me a minute to find the moon in the sky. There's not a lot of new science you can do with a lunar eclipse, but if you know a little geometry, you can use the size and shape of the Earth's shadow on the moon to get the relative sizes of the Earth and moon. Ancient Greeks did just this and got a number that wasn't too far off. They also knew how big the Earth was using other methods, and so they had a decent estimate for the size of the moon nearly 2,000 years before the invention of the telescope. They also knew the shape of the Earth's shadow was always a circle, which only makes sense if the Earth were a sphere. If the Earth were flat, it would sometimes cast a thin shadow, but it never does. Pretty clever, those ancient Greeks. One final note. Because of tides from the Earth, which we'll learn more about in detail in a later episode, the moon is slowly moving away from the Earth by about 4 centimeters a year. As it recedes, it's slowly getting smaller in the sky. This means that eventually it will be too far away to completely cover the sun, and we won't get any more total eclipses. Doing the rough math, that will be in about 1 billion years. Better watch eclipses while you can. Today you learned that a solar eclipse is when the moon blocks the sun so its shadow falls on the Earth, and a lunar eclipse is when the Earth's shadow falls on the moon. We don't get them every 2 weeks because the moon's orbit is tilted. And if you're clever, you can use lunar eclipses to figure out how big the Earth and moon are. This episode is brought to you by Squarespace. The latest version of their platform, Squarespace 7, has a completely redesigned interface. I've talked a lot about observing the night sky with your eyes, just simply going out and seeing what you can see. It's pretty amazing what you can learn just by doing that, and of course that's all we humans could do for thousands of years. But now we can do better. We can use telescopes. The first person to invent the telescope is lost to history. Despite common knowledge, Galileo did not invent them. He wasn't even the first person to point one at the sky, or the first person to publish results. But he was a loud and persistent voice over the years, and his amazing string of discoveries using his crude instrument landed him firmly in the history books. Aggressive self-marketing sometimes pays off. You might think the purpose of a telescope is to magnify small objects so we can see them better. That's how a lot of telescopes are marketed, but to be honest, that's not exactly the case. If you want to be really general, the purpose of a telescope is to make things easier to see, to make the invisible visible, and to make the things already visible more clearly. A telescope works by gathering light. Think of it like a bucket in the rain. The bigger the bucket, the more rain you collect. If your bucket is big enough, you'll get plenty of water even when it's only sprinkling out. In the case of a telescope, the bucket is an optical device like a lens or a mirror that collects light. We call this device the objective, and the bigger the objective, the more light it collects. Look at your eyes. Well, that's tough, so let's think about our eyes for a moment. They also work as light buckets, but they only collect light through our pupils, which even under the best of circumstances are less than a centimeter across. A very tiny bucket indeed. But we can do better. To extend the analogy, a telescope is like a bucket with a funnel at the bottom. All that light that it collects is then concentrated, focused, and sent into your eye. It turns a trickle of light into a torrent. The amount of light it collects depends on the area of the objective. That means if you double the diameter of the collector, you'd collect 4 times as much light, because the area of the collector goes up as the square of the radius. Make a bucket 10 times wider, and you collect 100 times as much light. Clearly, as telescopes get bigger, their ability to show us faint objects increases enormously. In fact, that was one of Galileo's first and most important discoveries. Stars that were invisible to the naked eye were easily seen through his telescope, even though it only had a lens a few centimeters across. Those faint stars didn't emit enough light for his eyes to see them, but when he increased his collecting area with a telescope, they popped into visibility. The primary way telescopes work is to change the direction light from an object is traveling. I can see a star with my eye because light from that star is sent in my direction, into my eye. But most of that light misses my eye, falling to the ground all around me. The telescope collects that light, bounces it around, and then channels it into my eye. When the very first telescopes were built, this changing of the direction of light was done using lenses. When light goes from one medium to another, say from going through air to going through water or glass, it changes direction slightly. You see this all the time. A spoon sitting in a glass of water looks bent or broken. The spoon is doing just fine, but the light you see from it is getting bent, distorting the image. This bending is called refraction. The way light bends depends on what's bending it, like water or glass, and the shape of the object doing the bending. It so happens that if you grind a piece of glass into a lens shape, it bends or refracts the incoming light in a cone, focusing it into a single spot. It's a light funnel. This refraction has a couple of interesting results. For one thing, the light from the top of a distant object is bent down and the light from the bottom is bent up. When this light comes to a focus, it means you see the object upside down. It also flips left and right, which can be a little disconcerting and takes getting used to when you're using a refracting telescope. For another thing, the lens can magnify the image. That's again because the light is bent, and the image created of an observed object can appear larger than the object does by eye. It depends on a lot of factors, including the shape of the lens, the distance to the object, and how far away the lens is. But in the end, what you get is an image that looks bigger. That has obvious advantages. A planet like Jupiter is too far away to see as anything other than a dot to the eye, but a telescope makes it appear bigger, and details can then be seen. When Galileo and other early astronomers pointed their telescopes at the sky, multitudes were revealed. Craters on the moon, the phases of Venus, Jupiter's moons, the rings of Saturn, and so much more. The universe itself came into focus. When astronomers talk about using a telescope to make details more clear, they use a term called resolution. This is the ability to separate two objects that are very close together. You're familiar with this. When you're driving on a road at night, a distant car coming toward you appears as a single light. When it gets closer, the light separates out, resolves into two headlights. A telescope increases resolution, making it easier to, say, split two stars that are close together, or to see details on the moon's surface. The resolution depends in part on the size of the objective. In general, the bigger the telescope objective, the better your resolution is. Resolution is more useful than magnification when talking telescopes. Fundamentally, there's a limit to how well your telescope resolves two objects, but there's no limit to how much you can magnify the image. If you magnify the image beyond what the telescope can actually resolve, you just get mush. Refracting telescopes are great, but they suffer from a big problem. Big lenses are hard to make. They get thin near the edge and break easily. Also, different colors of light bend by different amounts as they pass through the lens. So you might focus a red star, say, and a blue one will still look fuzzy. No less a mind than Isaac Newton figured a way around this. Use mirrors. Mirrors also change the direction light travels, and if you used a curved mirror, you can also bring light rays to a focus. Telescopes that use mirrors are called reflectors. The advantages of reflectors are huge. You only have to polish one side of a mirror, where a lens has two sides. Also, a mirror can be supported along its back, so they can be manufactured much larger, more easily, and for less money. Although there have been many improvements made over the centuries, most big modern telescopes at their heart are based on the Newtonian design. And in fact, no large professional-grade telescopes made today have a lens as their objective. Nowadays, it's all done with mirrors. And that brings us to this week's aptly named Focus On. The most common question I'm asked, besides, hey, who does your hair, is, hey Phil, what kind of telescope should I buy? It's a legitimate question, but it's very difficult to answer. Imagine someone walked up to you and asked, what kind of car should I buy? That's impossible to answer without a lot more information. Same for telescopes. Do you want to look at the moon and planets, or fainter, more difficult to spot galaxies? Are you really devoted to this, or is it more of a pastime? Is this for a child or an adult? These questions are critical. Most small scopes are refractors, which are good for looking at detail on the moon and planets. They tend to magnify the image more than reflectors do. But they're tricky to use because they flip the image left and right and up and down. Bigger scopes are good for fainter objects, but are more expensive and can be difficult to set up and use. I hate hearing about a scope that just collects dust because it was bought in haste. So here's what I recommend. Find an observatory, planetarium, or a local astronomy club. They're likely to have star parties, public observing events, where you can look at and through different kinds of telescopes. Their owners are almost universally thrilled to talk about them. As an astronomer, I can assure you that the problem with astronomers isn't getting them to talk, it's shutting them up. So you'll get lots of great first-hand advice and
That's kind
experience.
of true.
Also, I usually
have to bite
recommend
my
getting
tongue a lot.
binoculars before a telescope. They're easy to use, fun to use, easy to carry around, and you can get good ones for less money and still see some nice things. Even if you decide not to get more into astronomy as a hobby, they can also be used during the day on hikes and for bird watching. I have a couple of pair of binoculars and I use them all the time. There's a third aspect to telescopes that's very important. Beyond resolution and making faint things easier to see, they can literally show us objects outside of the range of colors our eyes can see. In the year 1800, William Herschel discovered infrared light, a kind of light invisible to our eyes. In the time since, we've learned of other forms of invisible light: radio, microwave, ultraviolet, X-rays, and gamma rays. Astronomical objects can be observed in all these flavors of light if we have telescopes that are designed to detect these flavors of light. Radio waves pass right around normal telescopes, ones that we use to observe visible light. X-rays and gamma rays pass right through them as if they aren't even there. But we're smart, we humans. We learned that giant metal dishes can and will bend radio waves and can be formed just like gigantic Newtonian mirrored telescopes. In fact, different forms of light need different kinds of telescopes, and once we figured out how, we've built them. We can now detect cosmic phenomena across the entire spectrum of light, from radio waves to gamma rays, and have even built unconventional telescopes that detect subatomic particles from space as well, such as neutrinos and cosmic rays. Because of this, we've learned far more about the universe than Galileo could have imagined. And we're in the midst of another revolution too. The actual biophysics is complicated, but in a sense, our eyes act like movie cameras, taking pictures at a frame rate of about 14 images per second. That's a short amount of time. Photographs, though, can take far longer exposures, allowing the light to build up, allowing us to see much fainter objects. The first photographs taken through a telescope were done in the 1800s. This has led to innumerable discoveries. For example, in the 20th century, giant telescopes with giant cameras revealed details in distant galaxies that led to our understanding that the universe is expanding, a critically important concept that we'll dive into later in the series. And now we have digital detectors, similar to the ones in your phone camera, but far larger and far more sensitive. They can be dozens of times more light sensitive than film, able to detect in minutes objects that would have taken hours or more to see using film. These digital cameras can also be designed to detect ultraviolet light, infrared, and more. We can store vast amounts of that data easily on computers and use those computers to analyze that huge ocean of information, performing tasks too tedious for humans. Most asteroids and comets are discovered using autonomous software, for example, looking for moving objects among the tens or hundreds of thousands of fixed stars in digital images. This is also ushered in the era of remote astronomy. A telescope can be on a distant mountain and programmed to scan the sky automatically. It also means we can loft telescopes into space, above the sea of air in our atmosphere that blurs and distorts distant faint objects. We can visit other worlds and send the pictures and data back home, or put observatories like the Hubble Space Telescope into orbit around the Earth and have it peer into the vast depths of the universe. I would argue that the past century has seen a revolution in astronomy every bit as important as the invention of the telescope in the first place. In the early 17th century, the entire sky was new, and everywhere you pointed a telescope, there was some treasure to behold. But with our huge telescopes and incredibly sensitive digital eyes now, that's still true. We learn more about the universe every day, just as we learn that there's more to learn every day too. That's one of the best parts of being an astronomer. The universe is like a jigsaw puzzle with an infinite number of pieces. The fun never ends. And remember, even with all the wonders revealed by telescopes, your eyes are still pretty good instruments too. You don't need big fancy equipment to see the sky. The important thing is to go outside. Look up! That's fun too. Today you learned that telescopes do two things: increase our ability to resolve details and collect light so we can see fainter objects. There are two main flavors of telescope: refractors, which use a lens, and reflectors, which use a mirror. There are also telescopes that are used to look at light our eyes can't see, and with the invention of film and later electronic design.
Ooh, gravity. You're starting to get into some good stuff now. All right.
We live,
I gotta switch
and
this.
stop me if I'm
Just
going too fast,
fucking
on a planet.
sit,
I mean, sure,
pick a lap.
duh. But this isn't the natural
Now I gotta
state of the
change the
universe,
camera again.
or at least it's not the way things usually are. Most of the universe
It doesn't
is
go
pretty
down any
empty.
further.
That's why we call it space. And if I were to magically transport you someplace randomly in the
Quit moving
cosmos,
around, kitty.
the chances are you'd be a million light years from the nearest substantial object. Evolving on a planet has warped our sense of physics. If I throw an object away from me, it comes back. That's bizarre. It should just keep going, moving away from me at a constant speed. Instead, though, it goes up, slows, stops, then falls back down toward me. The difference between living on a planet and being in deep space is gravity. Gravity from an object goes on forever, but it gets weaker rapidly with distance. A zillion light years away, the Earth's gravity is fantastically weak, but here on Earth, it's literally a force to be reckoned with. And in some places, it can be a lot stronger than what we experience right here.
Poo-poo. Where you
For
going
most
now?
of history, gravity was just a fact of life,
It's just my
neither
crotch now, man.
understood nor examined terribly closely. In the mid-1600s, scientists like Robert Hooke and Isaac Newton started investigating it using math. In fact, the two men got into a bitter feud over who thought of what first. But whoever it was who first got it right, now we have a much better understanding of how gravity works. So one thing before we get to gravity, an important concept that comes up a lot is mass. It's a bit tricky to define, but you can think of it as how much stuff makes up an object. I know that's not very scientific sounding, but it's not a bad way to think about it. Something with more mass has more stuff in it. Size doesn't really play into this. Two objects can have the same mass, but one can be much larger than the other. In that case, the bigger object's mass is more spread out. So we say it has lower density, where density is how much mass is inside a given volume. In science terms, mass tells us how much an object resists having its motion changed. An object with more mass is harder to get moving than an object with less mass, which is pretty obvious if you've ever tried pushing on a toy truck versus a real truck. But mass is also defined using gravity. Everything that has mass also has gravity and can inflict this force on another object. The amount of force you feel from the gravity of an object, like a planet, depends on three things: how much mass it has, how much mass you have, and how far away you are from it. In fact, distance dominates here. The force of gravity weakens with the square of the distance. Double your distance from an object, and the force of gravity drops by 2 times 2 equals 4 times. Go 10 times farther away, and the force drops by 10 times 10 equals 100 times. Gravity is also attractive. It can only draw things in, not repel them. But how it attracts things is where it gets fun. If I hold up a rock and let go of it, it falls to the ground. What might be hard to see is that it gets faster the longer it drops. Forces accelerate objects, so the longer the force acts, the more the object's velocity changes, in this case getting faster. If I drop a rock from higher up, it'll move faster when it hits the ground. Other forces act on moving objects as well, like friction and air resistance, counteracting gravity, making this acceleration hard to see. But in space, the force of gravity becomes very clear. Two objects that have mass will attract each other. If there are no other forces acting on them, they'll accelerate toward each other until they meet. Remember, though, that the force of gravity depends on those masses.
Sorry, dear.
If one is really massive and the other not so much, then in more practical terms, the massive one will pull in the less massive one. The more massive one does move, but much less than the other one. When objects are free to move under the effects of gravity, we say they are in orbit. The simplest kind of orbit may not be what you think. It's actually just a line. When you drop a rock, it's very briefly in orbit. Ignoring things like the Earth's rotation, which adds a bit of sideways motion, it's close enough to say the rock just falls straight down and is stopped because the Earth itself gets in the way. That's not a terribly interesting orbit. So what if, instead of dropping the rock, we throw it? That gives it a little bit of sideways motion, so instead of hitting the ground at my feet, it hits a bit farther away. If I throw it harder, it moves horizontally even more before it hits. What if I throw it really hard? This is where Newton's genius comes in. He realized that if you throw the ball hard enough sideways, it will fall at the exact same rate the Earth would curve away underneath it. As Douglas Adams said in Hitchhiker's Guide to the Galaxy, flying is just falling and missing the ground. It turns out that's exactly what orbiting is, too. A rock thrown hard enough sideways will fall toward the Earth, but always miss it, going instead into a circular path around it, guided only by gravity. It'll orbit the Earth in a circle, taking about 90 minutes to go around the planet once. Circles are simple orbits. The speed at which the orbiting satellite travels depends on the mass of the object it's orbiting and its distance from it. The farther it is, the weaker gravity is, so it doesn't have to travel as quickly to maintain the orbit. Roughly 400 years ago, the astronomer Johannes Kepler realized that there can be other shapes of orbits as well. He discovered that planets orbit the sun on ellipses, when previously it was thought they orbited in perfect circles. An elliptical orbit happens when you throw the rock sideways even harder than it takes for a circular orbit. It goes up higher on one end of the orbit than on the other. In fact, the harder you throw the rock, the more elongated the orbit gets. An orbit like this is still closed. That is, the orbit repeats itself and the rock is still bound to the Earth by gravity. At some point, though, if you throw the rock hard enough, an amazing thing happens. It can escape. Remember, gravity gets weaker with distance. If you throw a rock hard enough, while gravity can slow it down, the gravity gets weaker the farther away the rock is. If the rock has enough velocity, gravity weakens too quickly to stop it. The rock can escape, moving away forever. So we call this the escape velocity. The escape velocity of an object, like a planet or star, depends on how much mass it has and how big it is. For the Earth, that turns out to be about 11 kilometers per second. For Jupiter, it's about 58 kilometers per second, and for the Sun, it's a whopping 600 kilometers per second. Whatever the particular escape velocity for your cosmic location is, if you fling a rock away from it faster than that, I hope you kissed it goodbye first, because it ain't coming back. One way to think of it is that the rock is always slowing, getting ever closer to stopping, but it never actually stops. If it could travel infinitely far away, it would stop, but that's kind of a long trip. This works in reverse, too. If I go way far away from the Earth and drop a rock, it'll accelerate. When it hits the planet, it'll be moving at escape velocity, that same 11 kilometers per second. And if I give it a little sideways kick, it'll miss the Earth but still pass us at escape velocity. An escape orbit is open. It doesn't come back and is shaped like a parabola. What if you throw the rock even harder than that? The rock doesn't come back and moves away even faster. The orbit is now a hyperbola, which is similar to a parabola but is even more open. The rock never stops, even at infinity. It just keeps moving on. Like all forces, gravity gets weaker with distance, but its force never quite drops to zero. It just gets smaller and smaller as you get farther and farther away. So why then are astronauts on the space station weightless? Gravity is still pulling on the astronauts. In fact, at the height of the station, Earth's gravity has only decreased by a little bit. It's still about 90% as strong as it is on the Earth's surface. If they were in a tower 320 kilometers high, they'd weigh 90% of what they do on the Earth's surface. But the big difference is that the astronauts are in orbit, falling around the Earth. Weight is actually not just the force of gravity on a mass, but how hard a surface pushes back on that mass. For example, when you stand on the ground pushes back. Otherwise, you'd fall through.
I don't think I can.
The force of the ground back on you is what causes you to have weight. In free fall, there's nothing pushing back. You're falling freely, and so you have no weight. NASA likes to call this condition microgravity, since there are subtle forces acting on you. This actually highlights the difference between mass and weight. In space, you have the same mass as you do on Earth, but no weight. If another astronaut pushed on you, they'd have to exert a force. But if you stood on a scale in space, it wouldn't register anything. Space is weird. Well, compared to Earth. One more thing, and this is truly weird.
Whoa.
Photons, particles of light, have no mass, yet they can be affected by gravity too, bending their direction of flight as they pass a massive object. It turns out gravity can actually warp space. Light travels along the fabric of space like a truck on the road, and if the road curves, so does the truck. I know this is an odd concept, and we'll be dealing with it later
looks like
in more
this is
detail
just finishing up.
Escape velocity
The review is whatever.
With black holes. Today you learned that gravity is a force, and everything
Yes,
with mass
of
has
course.
gravity.
We're still on the
Gravity
baby
accelerates
stuff at the
objects with
moment,
mass,
at least in
changing
my
their
view.
speed and/or direction.
Tides. Ah, shit. More baby stuff. That's okay. We'll get into the
You
good
know,
stuff
if
later.
Shakespeare had been an astronomer,
They gotta
he'd
ramp
have
up to the
said
good shit.
that there is a tide in the affairs of the universe, and on such a full sea are we now afloat. He would have been right. You might just think of tides as the ocean going in and out every day.
Right.
But in fact, what astronomers call
gonna go
tides
fill up this
are a
coffee.
subtle but
I shall
inexorable
return
force that have
momentarily.
literally shaped most objects in the universe. And to understand tides, we start with gravity. Gravity is a force, and it weakens with distance. An important thing to note is that we measure gravity from the center of mass of an object, not its surface. One way to think of the center of mass of an object is the average position in an object of all its mass. For an evenly distributed sphere, that's its center. Right now, unless you're an astronaut, you're about 6,400 kilometers from the center of the Earth. If you stand up, your head is a couple of meters farther away from the Earth's center than your feet. Since gravity weakens with distance, the force of Earth's gravity on your head is an eensy-weensy bit less than it is on your feet. How much less? A mere 0.00005%. And that's way too small for you ever to notice. But what if you were taller? Well, the taller you are, the farther your head is from the Earth's center and the weaker force it will feel. If you were, say, about 300 kilometers tall, the force of gravity would drop by about 10% at your head. That probably would be enough to notice if you weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call the tidal force. When you have a massive object affecting another object with its gravity, its tidal force depends on several factors. For one thing, it depends on how strong the gravity is from the first object. The stronger the force of gravity, the stronger the tidal force will be on the affected object. It also depends on how wide the affected object is. The wider it is, the more the force of gravity from the first object changes across it, and the bigger the tidal force. Finally, it depends on how far the affected object is from the first object. The farther away the affected object is, the lower the tidal force will be. Tides depend on gravity, and if gravity is weaker, so is the tidal force. The overall effect of the tidal force is to stretch an object. You're applying a stronger force on one end than you are on the other, so you're pulling harder on one end. That'll stretch it. And this is where tidal forces become very important. Look at the moon. It has gravity, but much less than the Earth because it's less massive. It's 380,000 kilometers away, so the gravitational force it has on you is pretty small. And you're pretty small compared to that distance, just a couple of meters long from head to feet. But the Earth is big. It's nearly 13,000 kilometers across. That means the side of the Earth facing the moon is about 13,000 kilometers closer to the moon than the other side of the Earth. This is a pretty big distance, enough for tides to become important. The side of the Earth facing the moon is pulled harder by the moon than the other side of the Earth, so the Earth stretches. It becomes ever so slightly football-shaped, like a sphere with two bulges, one pointing toward the moon and one pointing away. This is probably the weirdest thing about tidal forces. You might expect only one bulge on the side of the Earth facing the moon. But remember, we measure gravity from the centers of objects. The side of the Earth facing the moon feels a stronger pull toward the moon than the Earth's center, so it's pulled away from the center. But the side facing away from the moon feels a weaker force toward the moon than the Earth's center. This means the center of the Earth is being pulled away from the far side. This is exactly the same as if the far side is being pulled away from the center, and that's why you get two bulges on opposite sides of the Earth. The tidal force is therefore strongest on the sides of the Earth facing toward and away from the moon, and weakest halfway in between them on each side. A lot of the Earth is covered in water, and water responds to this changing force, this stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second, the Earth is spinning. If you're on a part of the Earth facing the moon, you're at high tide. 6 hours later, a quarter of a day, the Earth's rotation has swept you around to the spot where it's low tide. 6 hours after that, you're at high tide again, and then another 6 hours later, you're at low tide for the second time that day. Finally, a day after you started, you're back at high tide once more. And that's why we have two high tides and two low tides every day. Very generally speaking, the ocean tide causes the sea level to rise and fall by a meter or two every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just sit in your house all day, you move up and down by about that much. twice. Like the saying goes, a rising tide lifts all
Mr. Shadowman has
surfaces.
been
The Earth's spin
a
has
disruption
another
in
effect.
class.
Lag in the water flow means the water can't respond
Please
instantly to the tidal
beat
force from
your
the moon. The
child
Earth's spin actually
so I don't
sweeps the
have to.
bulges forward a bit along the Earth. So picture this. The bulge
The good
nearest the
old
moon
days.
is actually a bit ahead of the Earth-Moon line. That bulge has mass. Not a lot, but some. Since it has mass, it has gravity, and that pulls on the moon. It pulls the moon forward in its orbit a bit, like pulling on a dog's leash, accelerating it. The moon responds to this tug by going into a higher orbit. The moon is actually moving away from the Earth. The rate of recession of the moon has been measured, and it's something like a few centimeters per year. Roughly
Oh,
the
Trina,
same
if you're
speed
still there,
your
love.
fingernails grow. Now
This
get
lemon
this.
drop watermelon?
The moon has
It's
gravity.
good. I like
Just
it.
as the bulge
Nice
is
and
pulling
strong.
the moon ahead, the moon is pulling the bulge back, slowing it down. Because of friction with the rest of the Earth, this slowing of the bulge is actually slowing the rotation of the Earth itself, making the day longer. The effect is small,
I got
but
baby looking
again,
at me
it's
now.
measurable.
What?
Okay, let's get a little change
What do
of
you want?
perspective.
Huh?
Everything I've said about the moon's tidal effect on the Earth
Coming for
works the
Pop's
other
lap.
way too. The moon feels tides from the Earth, and they're pretty strong because the Earth is more massive and has more gravity than the
Missy
moon.
just
Just like
rushed,
Earth, there
baby.
are two tidal bulges on
It's
the
my
moon,
lap, bitch.
one facing the Earth and one
Hi,
facing
baby
away.
girl.
Long ago, the moon was closer to the Earth and
baby.
spinning rapidly. The moon's tidal bulges didn't align with the Earth, and the Earth's gravity tugged on them, slowing the moon's spin and moving it farther away. As it moved farther away, the time it took to orbit once around the Earth increased. Its orbital period got longer. Eventually, the lengthening rotation of the moon matched how long it took to go around the Earth. When that happened, the axis of the bulges pointed right at the Earth. That's why the moon only shows one face to us. It spins once per month and goes around us once per month. If it didn't spin at all over that month, we'd see the entire lunar surface. But since it does spin once per orbit, we only ever see one face. This is called tidal locking, and it's worked on nearly every big moon in the solar system. Tides from their home planet have matched their
Flex made
spin
his
and orbital
300
period.
followers.
These moons all show the same face toward their planet. Now wait a second.
What's
If
he
the
up?
moon has gravity, which
297.
causes tides,
He
and
needs
is the
3
root
more.
cause behind all these shenanigans,
He needs 3
what
more
about the sun?
followers.
It's even bigger than the moon. Tides depend on
I
the
had to check my
gravity from
tabs.
an object and your distance from it. The sun is far more massive than the moon, but much farther away. These two effects largely cancel each other out. And when you do the math, you find the sun's tidal force on the Earth is just about half that of the moon's. The way the sun's tidal force and the moon's tidal force interact on Earth depends on their geometry, which changes as the moon orbits us. At new moon, the Earth, moon, and sun are in a line. The moon's tidal force aligns with the sun's, reinforcing it. This means we get an extra high tide and an extra low tide on Earth. We call this the spring tide. When the moon is at first quarter, the tidal bulge from the moon is 90 degrees around from the sun's. High tide from the moon overlaps low tide from the sun. We get a slightly lower high tide and a slightly higher low tide. We call those neap tides. The pattern repeats when the moon is full. The moon, Earth, and sun fall along a line again and we get spring tides. A week later, the moon is moved around and we get neap tides again. Not only that, the moon orbits the Earth on an ellipse. When it's closest to us, we feel a
Ping
stronger
needs 3
effect.
more
If
followers
that
for
also happens
300.
at
He's
new
been
or
streaming
full
for
moon,
40
we get
something
an
hours.
added
He
kick
says
to
he's
the
not
spring
going
tides.
off until he gets
This is called the
300
Procyon
followers.
tide and can lead to flooding in low-lying areas.
not
Unless
sure
you
if
live
you're
on the
already
coast,
followed.
I bet you had no idea tides were so complex.
3 away.
Tides are universal. They work wherever there's gravity. If two stars orbit each other, each raises a tide in the other. Just like the Earth and Moon, that can slow their spin and increase their separation. Many planets orbiting other stars may be tidally locked to those stars. Near a black hole, where the gravity is incredibly intense, the tides are so strong they would pull you like taffy into a long, thin string. Astronomers call this effect spaghettification. No, seriously, that's what we call it. Today you learned that tides are due to the changing force of gravity over distance. The strength of the tidal force from an object depends on the gravity of the object and the size of and distance to the second object.
Solar system. Moving up a little bit.
The solar system is the name we give to our local cosmic backyard. A better way to think of it is all the stuff held sway by the sun's gravity. The sun itself, planets, moons, asteroids, comets, dust, and very thin gas. If you took a step back, well, a few trillion steps back, and looked at it from the outside, you might define the solar system as the sun. And that's because the sun comprises more than 98% of the mass of the entire solar system. The next most massive object, Jupiter, is only 1/10 the diameter and less than 1% the mass of the sun. But that's a little unfair. Our solar system is a pretty amazing place, and you can figure out a lot of what's going on in it just by looking at it. For thousands of years, we had to explore
check
the solar
something.
system stuck
Oh,
on
you
this
know what? I can
spinning,
probably just do
revolving
it straight
ball,
up.
the Earth. The problem was, for a long time, we didn't know it was a spinning, revolving ball. Well, the ancient Greeks knew it was a ball. They had even measured its size to a fair degree of accuracy, but most thought it was motionless. When a few folks pointed out that this might not be the case, like the ancient Greek astronomer Aristarchus of Samos, they got ignored. The idea that the sky spins around the Earth seems obvious when you look up. And when great minds like those of the astronomer Ptolemy and the philosopher Aristotle supported that idea, well, people like Aristarchus got left behind. The basic thinking was that the moon, sun, and stars were affixed to crystal spheres that spun around the Earth at different rates. While it kinda sorta worked to predict the motions of objects in the sky, in detail it was really unwieldy and failed to accurately predict how the planets should move. Still, Ptolemy's idea of a geocentric universe stuck around for well over 1,000 years. It was the year 1543 when Nicholas Copernicus finally published his work proposing a sun-centered model, much like the one Aristarchus had dreamed up 2,000 years previously. Unfortunately, Copernicus's model was also pretty top-heavy and had a hard time predicting planetary motions. The last nail in geocentrism's coffin came a few years later, when astronomer Johannes Kepler made a brilliant mental leap. Based on observations by his mentor, Tycho Brahe, Kepler realized the planets moved around the sun in ellipses, not circles, as Copernicus had assumed. This fixed everything, including those aggravating planetary motions. It still took a while, but heliocentrism won the day. And the night, too. This paved the way for Newton to apply physics and his newly created math of calculus to determine how gravity worked, which in turn led to our modern understanding of how the solar system truly operates. The sun, being the most massive object in the solar system by far, has the strongest gravity, and it basically runs the solar system. In fact, the term solar comes from the word sol for sun. We named the whole shebang after the sun, so there you go. The planets are smaller, but still pretty huge compared to us tiny humans. At the big end, we have Jupiter, 11 times wider than the Earth, and 1,000 times its volume. At the smaller end, we have, well, there is no actual smaller end. We just kind of draw a line and say, planets are bigger than this. That's a bit unsatisfactory, I'll admit, but it does bring up an interesting point. I've been using the term planet, but I haven't defined it, and that's no accident. I don't think you can. A lot of people have tried, but definitions have always come up short. You might say something is a planet if it's big enough to be round, but a lot of moons are round, and so are some asteroids. Maybe a planet has to have moons. Nope. Mercury and Venus don't, and many asteroids do. Planets are big, right? Well, yeah, but Jupiter's moon Ganymede is bigger than Mercury. Should Mercury be stripped of its planetary status? I could go on, but no matter what definition you come up with, you find there are lots of exceptions. That's a pretty strong indication that trying to make a rigid definition is a mistake. It'll get you into more trouble than it'll help. Planet can't be defined. It's a concept, like continent. We don't have a definition for continent, and people don't seem to mind. Australia is a continent, but Greenland isn't. Okay by me. So that's what I tell people if they ask me if Pluto is a planet. I say, tell me what a planet is first, and then we can discuss Pluto. Pluto is what it is, a fascinating and intriguing world. One of thousands, perhaps millions more orbiting the sun out past Neptune. I think that makes it cool enough. All the orbits of the planets lie in a relatively flat disk. That is, they aren't buzzing around the sun in all directions like bees around a hive. The orbit of Mercury, for example, lies in pretty much the same plane as that of Jupiter. That's actually pretty interesting. Whenever you see a trend in a bunch of objects, nature is trying to tell you something. In fact, there are other trends that are pretty obvious when you take a step back and look at the whole solar system. For example, the inner planets, Mercury, Venus, Earth, and Mars, are all relatively small and rocky. The next four, Jupiter, Saturn, Uranus, and Neptune, are much larger and have tremendously thick atmospheres. In between Mars and Jupiter is the asteroid belt, comprised of billions of rocks. There are lots more asteroids scattered around the solar system, but most are in the main belt. Then, out beyond the orbit of Neptune, is a collection of rocky ice balls called Kuiper belt objects. The biggest are over 1,000 miles across, but most are far smaller. They tend to follow the plane of the planets too. But if you go even farther out, starting tens of billions of kilometers from the sun, that disk of Kuiper belt objects merges into a vast spherical cloud of these ice balls called the Oort cloud. They don't follow the plane of the inner solar system, but orbit every which way. So what do all these facts tell us about the solar system? we think they're showing us hints of how the solar system formed. 4.6 billion years or so ago, a cloud floated in space. It was in balance. Its gravity trying to collapse it was counteracted by the meager internal heat that buoyed it up. But then something happened. Perhaps the shockwave from a nearby exploding star slammed into it, or maybe another cloud lumbered by and rammed it. Either way, the cloud got compressed, upsetting the balance, and gravity took over. It started to collapse. As it did, angular momentum became important. That's a lot like regular momentum when an object in motion tends to stay in motion. But in this case, it's a momentum of spin, which depends on the object's size and how rapidly it's rotating. Decrease the size and the rotation rate goes up. The usual analogy is an ice skater starting a spin, then drawing their arms in. Their spin is amplified hugely. The same thing happened in the cloud. Any small amount of spin it had got ramped up as it collapsed. It flattened into a disk, much like spinning raw pizza dough in the air will flatten it out. As it collapsed, material fell to the center, getting very dense and hot. Farther out in the disk, where it was cooler, material started to clump together as little grains of dust and other matter randomly bumped into other little bits. As these clumps grew, their gravity increased and eventually started drawing more material in. These little blobs are called planetesimals, wee baby planets. As they grew, so did the center of the disk. The object forming there was a protostar, or, spoiler alert, the proto-sun. Eventually, its center got so hot that hydrogen fused into helium, which makes a lot of energy. A lot of energy. A star was born. The new sun blasted out fierce light and heat that, over millions of years, blew away the leftover disk material that hadn't yet been assimilated into planets. The solar system was born. Closer to the sun, it was warmer. Hydrogen and helium are very light gases, and the warm baby planets there couldn't hold on to them. Farther out, there was more material in the disk, and the planets were bigger. Since it was cooler too, they could hold on to those lighter gases, and their atmospheres grew tremendously, eventually outmassing the solid material in their cores. They became gas giants.
Streamlabs.
There was also a lot of water out there far from the sun, in the form of ice. Smaller icy objects formed past Neptune, but space was too big and random encounters too rare. They didn't get very big, maybe a few hundred kilometers across. A lot of them, billions, perhaps trillions of them, got too close to the big planets and were flung hither and yon. Closer in, material between Mars and Jupiter couldn't get its act together to form a planet either. Jupiter's gravity kept agitating it, and impacts between two bodies tended to break them up, not aggregate them together. And there you have it, our solar system, formed from a disk sculpted by gravity. Echoes of that disk live on today, seen in the flatness of the solar system. This isn't guesswork. The math and physics bear this out. And not only that, we see it happening now, today. When we look at gas clouds in space, we see stars forming. We see protoplanetary disks around them. We see the planets themselves getting their start. We may think of ourselves as the solar system, but we're really just a solar system. The scenario that happened here so long ago plays itself out daily in the galaxy. We're one of billions of such systems. And remember, every atom in your body and everything you see around you, every tree, every cloud, every human, every computer, everything on Earth, even the Earth itself, was once part of that dense cloud. We are quite literally star stuff. Today you learn that the solar system is one star, many planets, a lot more asteroids, and even more icy comet-like objects. It formed from a collapsing cloud, which flattened into a disk, and that's why the solar system is flat. Rocky planets formed closer to the sun, and larger gas giants farther out. Icy objects formed beyond Neptune in a disk as well, and a lot of them were flung out to form a spherical shell around the sun. We see the same thing happening out in the galaxy too. The motions of the objects in this system caused a lot of confusion to ancient astronomers, but we...
Oh, okay. The sun? Get better.
The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot, blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But What is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart.
Maybe when you die,
At the very core of the sun,
get put into some
conditions
kind of
are hellish.
extremely
The pressure is a
heat-resistant
crushing
capsule
260
and get
billion
shot into the
times
sun
Earth's atmospheric pressure,
feet first.
and it's a searing 15 million
That might work.
degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse
I think that'd
together.
be a good
Through
way to go,
a complicated
honestly.
series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear
starting to get
energy
into the
stored in those
mid-grade
atoms
stuff
is
here.
released. That amount of energy is described by Einstein's famous equation E equals mc
Energy
squared,
equals
which
mass
states
times
that
light
mass
squared.
can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot
of them.
Get this. Every second of every day, the sun converts 700 million tons of hydrogen into 695 million
Fusion
tons
in
of
the
helium.
sun.
The missing
An
5
individual
million tons,
fusion
the equivalent
reaction
weight
is
of
gives out
15
a
Empire State
tiny
Buildings,
little
is converted
baby
into
energy.
energy. And that's a lot of energy. Enough, in
there's just
fact,
so many
to
of them.
power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet every second. And that's why, even from a distance of 150 million
still feel the
kilometers,
heat.
the sun is so bright you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside.
So far
Hydrogen
away.
fusion occurs in the core of the sun.
amount of
The energy
power it
released
puts out
heats
is
the gas
incredible.
above the core, but not quite enough to fuse hydrogen into helium. Further
just
from
like a
the sun's center,
regular-sized
the gas
star,
becomes
too.
less dense, and at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection, and it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere, or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1 million degrees. However, it's so thinly
That's
dispersed
crazy how
that
far
it's
it stretches
incredibly
out in
faint
space.
and can only be
You
seen
can't
during
see
a
it
total
'cause it's so
eclipse
bright.
or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers. And in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind
Thankfully,
is
we have
usually
a
well over 1
electromagnetic
million kilometers
field
per
protecting
hour.
us?
Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, the energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe as a much lower energy photon of visible light. So how long does this process take? I've seen different numbers for it, some as much as 1 million years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 100,000 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that
Yeah, that's kind of cool how that works. The sun is so dense that the light has trouble. Even once it's created, it bounces around, and makes its way out ever so slowly. It takes, like you said, 100,000, 200,000 years for that light that was first created to finally reach the top of the sun, the outer reaches, and then it's just poof, gone. In the way this light sees travel, the way I understand it, okay, if we as humans roaming the universe in our low energy state would observe light as having speed, or 300,000 miles per second, 188,000 miles, or 300,000 kilometers per second. But to that, if we were to suddenly be that photon, and if it would take us so long to get to the photosphere, but the moment we are able to leave, we reach our destination instantly. We don't travel. Light, once you're at the speed of light, time basically stops. So you pop into existence at the coronas, like the outside corona, and the very first thing you see is the end of your journey. Even though it takes us, like, it'll take like millions of years to get to from one point to another, to the point perspective of the light itself, it's there instantaneously the moment it leaves the surface, because time doesn't matter to a light photon. It's brought into existence the moment it leaves the corona. It's at its destination from the viewpoint of the photon. And that's kind of weird to think about.
mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating what's called a plasma, a gaseous soup of charged particles. We'll learn more about that in a later episode, but what's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings on a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even
Did
get
you see that in
tangled
the
up.
camera?
When the plasma reaches the surface, it cools. But if the interact and even get tangled up, when the plasma reaches the surface, the solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as its fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface,
the lens of the
but if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as it cools, it dims. It sits on the surface, dimming, producing a dark spot on the surface of the sun, which we call a sunspot.
Which is actually
can
like
be huge.
one
They commonly
degree
dwarf
or
the
half a
entire
degree
Earth,
difference between
and some are
a
so big
non-sunspot.
they can be seen without using a telescope,
The tiny
as long as you're
difference
wearing
in
adequate eye protection,
light.
of course. Around the edges of sunspots, the magnetic
guys
field
out.
lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little torch. The dark
that's a
parts
new
of
one.
sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun, looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is
Crazy.
why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all
Mass
that vast
coronal
energy
ejection?
stored
Yeah,
in the
you see?
lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally
Quebec
deflected by the Earth's magnetic field, so we're okay. But if conditions are right, the Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts. In 1989, Quebec suffered a massive power outage from a solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen.
Solar ejection.
If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction,
I think a CME is going to fuck us.
Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important.
We need to figure out how to protect ourselves against CMEs.
And the very basis of life itself.
Because I think that's going to be the next thing to fuck us over.
Knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma.
I'm glad he brought that up for the CMEs. Because that's one of the most, that's the danger that's going to hit us the most. That's the thing that's going to fuck over. Like, it's not going to be an asteroid, probably not an asteroid or shit, that's what else? A super volcano. Maybe super volcano, maybe. But I'm pretty sure it's going to be a CME that sends us back to the Stone Age. I think a CME would be even worse than a super volcano. Super volcano, at least we still have power. We can kind of mitigate. But a CME, we would take out all of our electronics. Everything would go down. No one can communicate. No one can do anything. Be bad. Very bad. Next. What you got, bro? Oh, I didn't check it out. Was it?
The Earth is a planet. That's a profound statement, and one that's not really all that obvious.
Hope they get into
For thousands of years, planets were just bright lights in the sky, one-dimensional points that wandered among the fixed stars. How could the Earth be one of them? With the invention of the telescope, those dots became worlds, and with spacecraft, they became places. The Earth went from being our unique home in the universe to one of many such, well, planets. The Earth is the largest of the terrestrial planets, the 4 smaller, denser, rocky worlds orbiting close into the Sun. It's about 13,000 kilometers across and has a single large moon, which we'll learn more about next week. Unlike the other 3 terrestrial planets, Earth has something very important: water. Or more specifically, liquid water on its surface, where it can flow around, evaporate, become clouds, rain down, and then mix up chemicals so they can do interesting, complex things, like support life. Earth's ability to sustain life depends on that water. It also depends on Earth's atmosphere, of course. Breathing has its advantages, and both, weirdly enough, depend on Earth's magnetic field to exist. And that in turn depends on what's going on deep inside our planet. So let's take a look. Like the sun, the Earth is a many-layered thing. At its very center is the core, which actually has two layers, the inner core and the outer core. The inner core is solid and made mostly of iron and nickel. These are heavy elements and sank to the center of the planet when it was forming, leaving lighter elements like oxygen, silicon, and nitrogen to rise to the surface. The solid inner core is about 12.
You might not know this, but all the water and gold on Earth was sent here by meteorites. All the gold that was on the Earth when it was created was bringing down to the center. So when the Earth cooled and got hard, there was nothing on it, absolutely nothing. So all the minerals, everything was brought to us by comets.
100 kilometers in radius, or about 10% the radius of the Earth. The outer core is also mostly iron and nickel, but it's liquid. The material in it can flow. It's about 2,200 kilometers thick. The temperature in the Earth's core is tremendously high, reaching 5,500 degrees Celsius. The pressure is huge as well, as you might expect with the weight of an entire planet sitting on top of it. You might think at such a high temperature, iron would be a liquid, but iron can stay solid if the pressure is high enough. In the inner core, the pressure is extremely high, and even though it's hot, iron is solid. In the outer core, where it's still hot, but the pressure is a little bit lower, iron is a liquid. Above the core is the mantle. It's about 2,900 kilometers thick. The consistency of the mantle is weird. Most people think it's like lava, but really it's like very thick, hot plastic. It behaves more or less like a solid, but over long periods of time, geologic periods of time, it can flow. We'll get back to that in a sec. On top of the mantle is the crust, a solid layer of rock. The overall density of the rock in the crust is less than in the mantle, so in a sense it floats on the mantle. There are two types of crust on Earth. Oceanic crust, which is about 5 kilometers thick, and continental crust, which is a much beefier 30 to 50 kilometers thick. Still, the crust is very thin compared to the other layers. The crust isn't a solid piece, though. It's broken up into huge plates, and these can move. What drives the movement of these plates is the flow of the rock in the mantle, and that in turn is powered by heat. The core of the Earth heats the bottom of the mantle. This causes convection. The warmer material rises. It's not exactly a speed demon, though. The rate of flow is only a couple of centimeters per year, so it takes about 50 or 60,000 years for a blob to move a single kilometer. The hot material rises toward the surface, but it's blocked by the crust. The magmatic rock pushes on the plates, causing them to slide around very slowly. Your fingernails grow at about the same rate the continents move. Over millions of years, though, this adds up, changing the surface geography of the Earth. Where you see the continents now is not at all where they were millions of years ago. In some places, generally where the plates come together, the crust is weaker. Magma can push its way through, erupting onto the surface, forming volcanoes. Other volcanoes, like Hawaii or the Canary Islands, are thought to be from a plume of hotter material, punching its way right through the middle of a continental plate. As the plate moves, the hot spot forms a linear chain of volcanoes over millions of years. Volcanoes create new land as material wells out, but they also pump gas out of the Earth too. A large part of Earth's atmosphere was supplied from volcanoes. The interior of the Earth is hot. In the core, it's about as hot as the surface of the sun. Where did that heat come from? Most of it is left over from the Earth's formation more than 4.5 billion years ago. As rock and other junk accumulated to form the proto-Earth, their collisions heated them up. As the Earth grew, that heat built up, and it's still toasty inside even today. Also, as the Earth formed and gained mass, it began to contract under its own gravity, and this squeezing added heat to the material. Another source is elements like uranium deep inside the Earth, which add heat as the atoms radioactively decay. And a fourth source of heat is from dense material like iron and nickel sinking to the center of the Earth, which warms things up due to friction. All of these things add up to a lot of heat, which is why after all these billions of years, the Earth still has a fiery heart. The outer core of the Earth is liquid metal, which conducts electricity. The liquid convects, and this motion generates magnetic fields, similar to the way plasma in the sun generates magnetic fields. The Earth's rotation helps organize this motion into huge cylindrical rolls that align with the Earth's axis. The overall effect generates a magnetic field similar to a bar magnet, with a magnetic north pole and south pole, which lie close to the physical spin axis poles of the Earth. The loops of magnetism surround the Earth and play a very important role. They deflect most of the charged particles from the solar wind, and they trap some too. Without the geomagnetic field, that solar wind would hit the Earth's atmosphere directly. Over billions of years, that would erode the Earth's air away like a sandblaster stripping paint off a wall. Mars, for example, doesn't have a strong magnetic field, and we think that's why its atmosphere is mostly gone today. But we do have an atmosphere, and it's more than just air blowing around. Earth's atmosphere is the layer of gas above the crust. Because it's not solid, it doesn't just stop, it just sort of fades away with height. By accepted definition, and by that I mean it's not really science, it's more of a, let's just do it this way kind of a thing. The line between Earth's atmosphere and space is set at 100 kilometers up. This is what's called the Kármán line, and if you get above it, congratulations,
Kármán
you're an
line.
astronaut. The atmosphere is, by volume,
Kármán
about
line.
78% nitrogen, 21%
notebook.
oxygen, 1% argon of all things, and then an assortment of trace gases. There's water vapor too, almost all of it below a height of about 8 to 15 kilometers. This part of the atmosphere is warmest at the bottom, which means we get convection in the air, creating currents of rising air, which carry water with them, forming clouds, which in turn is why we have weather. At a height of about 25 kilometers on average is a layer of ozone, a molecule of oxygen that's good at absorbing solar ultraviolet light. That kind of light can break apart biological molecules, so the ozone layer is critical for our protection. Incidentally, the Earth's magnetic field does more than trap solar wind particles. It also channels some of them down into the atmosphere, where they slam into air molecules about 150 kilometers up. This energizes the molecules, which respond by emitting light in different colors. Nitrogen glows red and blue, oxygen red and green. We call this glow the aurora, and it happens near the geomagnetic poles, far north and south. The lights can form amazing ribbons and sheets, depending on the shape of the magnetic field.
Beautiful.
I've never seen an aurora.
Oh,
Someday.
buddy.
You may not be aware of the atmosphere unless the wind is blowing,
It's a
but it's
beautiful
there.
thing.
It exerts a
Everybody needs to
pressure
see
on the
the
surface
aurora.
of the Earth of about 1 kilogram per square centimeter, or
Incredible.
nearly 10 tons per cubic meter. There's roughly a ton of air pushing down on you right now. You don't feel it because it's actually pushing in all directions, down to the sides, even up, and our bodies have an internal pressure that balances that out. The Earth also has liquid water on its surface, unique among the planets. The continental crust is higher than oceanic crust, so water flows down to fill those huge basins. The Earth's surface is about 70% covered in water. Most likely, some of this water formed when the Earth itself formed, and some may have come from comet and asteroid impacts billions of years ago. The exact
of it came
proportion
from
of
comets.
locally sourced versus extraterrestrial water is still a topic of argument among scientists. Earlier, I mentioned trace
I argue
molecules of
towards
gas in the atmosphere. One of these is carbon
asteroids.
dioxide, which only constitutes about 0.04% of the lower atmosphere, but it's critical. Sunlight heats the ground, which emits infrared light. If this infrared light were allowed to radiate into space, the Earth would cool. But carbon dioxide traps that kind of light, and the Earth doesn't cool as efficiently. This so-called greenhouse effect warms the Earth. Without it, the average temperature on Earth would be below the freezing point of water. We'd be an ice ball. This is why climate scientists are concerned about carbon dioxide. A little is a good thing, but too much can be very dangerous. Since the Industrial Revolution,
Too much
we've
is
added a
bad.
lot of the gas to our atmosphere,
Hell yeah.
trapping more heat. By
It's like-
every
it was
measure
+2
available, the
here in
heat content
Canada.
of the Earth is increasing,
was
upsetting the balance. It's
ridiculously
melting
warm for
glaciers in
what
Antarctica and
the
Greenland,
time
as
of
well
year.
as sea ice at the North Pole. Sea levels are going up,
Yeah.
and some of the
Oh
extra
my
CO2 in the air is absorbed by the oceans, acidifying them. There's an
That's
old concept
horrible.
in science fiction called terraforming, going to an uninhabitable alien planet and engineering it to be more Earth-like. I don't know what the opposite process would be called, but it's what we're doing to Earth right now. The Earth is the only habitable planet in the solar system. And you know what? We should keep it that way. Today you learned that the Earth is a planet with a hot core, a
Yeah.
thick layer of molten rock called the mantle, and a thin crust.
The moon
The
again?
outer core
Didn't we just do the moon?
This episode of Crash Course is
Then we
brought
got
to you by
Mercury after that.
Squarespace.
I
The
thought we
moon is
did
pretty hard to
already.
miss when it's
Let's
up
try
at
again.
night.
All
It's
right,
big,
let's see again,
bright,
buddy.
and really very pretty. Even
All right.
cooler, it's
All
the
right.
closest astronomical object in the universe
I guess
to
the
us,
moon
and
deserves 2
arguably
episodes.
the one we know best.
We'll see. See if you can teach me anything useful.
I hate to break it to you, but we humans are pretty egotistical. Even though there are over 160 known moons of decent size in our solar system, we call ours the moon with a capital M, like it's the only one, or the most important
the
one. And I
actual
guess
name
to
is
us,
Luna.
it is the most important one. It's only the 5th largest moon in the solar system in absolute size, but compared to Earth, it's
true
pretty
name
big,
of the
fully
moon
a quarter of the
is
diameter
Luna.
of the planet. That's a way bigger ratio than for any other moon orbiting a major planet
check
in the
out
solar
Luna
system. By the
today?
numbers, the moon is about 3,470 kilometers in diameter, and on average about 380,000 kilometers.
Look how they do that to the Earth.
means
You
it
see it's
looks
upside
pretty
down?
big in our sky, but
Because when it comes to space, it really doesn't matter.
When the moon rises, it
That's
can look
funny.
huge and looming on the horizon, like you could fall into it. But that's not really the case. It's easy to show it's the same size on the horizon as it is high overhead. Yet people think it looks twice as big when it's on the horizon. This is the well-known moon illusion, and it's due to two factors: how we perceive the sizes of objects and how we perceive the sky. We don't really see the sky as a hemisphere over our heads, but more
We'll
like a
get
flattened
there,
ball with
Uranus.
the horizon
Episode 20.
farther away than
Hang
the
on,
zenith.
buddy.
So when the
We'll
moon's
get
on
there.
the horizon, our brains are convinced it's farther away. But if it's farther away, it must be physically bigger to appear that size, right? So our brain
They lumped it
interprets
in
the
with
moon's
Neptune,
size
though. I'm
as
not sure what that's
huge.
about.
It's an illusion, but a convincing one. In fact, the moon is about the same size as a small pill held up
Wait,
at arm's
Neptune
length.
is Uranus.
Our satellite is a lot smaller
Uranus
than you
is
think. The
Neptune.
internal structure of the moon is roughly similar to the Earth.
Finkel is
It has a
Einhorn.
solid iron
Einhorn
inner
is
core,
Finkel.
a liquid outer core,
Oh,
a thick
well,
mantle, and a crust of
pardon me,
light.
Mr.
Perfect
Perfect.
timing.
The core is small, probably.
I guess I forgot that you never ever make a mistake.
I
do not. Hello, Mr. Henry.
The
I gotta
lower
turn those
mantle may
down
be
a
a
little
thick
bit. I'm
fluid,
sorry,
but
sir.
unlike Earth's mantle, the upper part
damn,
is
I might have
solid.
to
The
turn them
easiest
off
part of the
altogether.
moon to
Can you-
observe
can you
is its
please
surface.
refrain
So of
from
course we
those
know the
today,
most
Mr.
about
Henry,
that.
sir?
The near side, the side we
Today
see from
we're
Earth,
in the
is divided
classroom.
into two distinct types of regions: highlands, which are
blips.
heavily cratered, and maria, Latin for seas, which are darker and smoother. The craters in the highlands are from countless impacts over the eons from asteroids and comets.
Okay, I turned
Rocks
them
from
way
these
down on
regions have been
this
dated to
side.
be well
Hopefully they
over
won't be
4
too bad.
billion
I don't wanna
years
step on your
nearly
parade,
as
Henry.
old
I know
as
you
the
love them.
moon itself. The maria, on the other hand,
let me
don't
see.
have nearly as many craters. They're younger, but that's relative. Rocks from those areas appear to be roughly 3 to 3.5 billion years old on average. The maria are made of darker basaltic material, which means they probably
that's a
formed
little
from
better.
lava flooding older areas. For most of human history, the far side of the moon was hidden from us. But in 1959, the Soviet
was using
Union
a
flew
ladder.
a Luna 3 space probe around the moon, photographing the far side for the first time. Everyone expected it to look a lot
that's
like
not
the
too
near
loud.
side, but shockingly, it's vastly different. There
Henry
were
loves
almost
his
no
blurps.
maria.
I
That's
gotta
weird.
have to
The near side is
accommodate the
covered
men.
with them. And not only that, observations from subsequent lunar probes
Mr.
showed
Henry,
the
how are you?
crust on the lunar far side is thicker than it is on the near side as well. The moon is starting to stack up mysteries. Why is it so big compared to Earth? Why are the near and far sides
That's
so
better.
different?
At least we're not stepping on class
It
today.
turns out the composition of the
You can
crust
step
has
on
a lot
me
of
all you like.
similarities to Earth,
I
but also a
encourage
lot
it,
of
Mr.
differences as
Henry.
well. Why? It turns out
Class
the
a
answers
little
to these
less.
questions are all related to how the moon formed 4.5 billion years ago. A lot of ideas have been
The
proposed
Earth was
to figure out
smacked
how the
into,
moon formed,
and then there was
but the
two
best one
moons
going
for a
these
while,
days
and
is
then they
called
bang
the
into one.
giant impact hypothesis. When the solar
That's how it
system
happened.
formed, there were a lot more objects orbiting the sun than there are now. These ranged in size from grains of dust up to objects the size of planets. And that meant there were lots of collisions. No doubt the Earth suffered many such impacts, but one
There's a
happened
real
later in
big
its
one.
history, relatively speaking, roughly 50 million years after things started to settle down. A Mars-sized planet, given the unofficial name Theia, slammed into our young planet.
Oh,
But it
look
wasn't
at
a
that.
head-on
Look at
impact. It was a grazing collision.
This is the kind of video
impact
game I
was
wanna play.
colossal,
This shit.
blasting a huge amount of material from both planets into space. Most of it came from the outer layers of the Earth, since the collision was a grazing one.
Star
This
Trek
material
Online is the
rapidly
closest I've
coalesced
come
into the
to-
moon,
I
and
haven't
that
played
explains
Eve
why
yet.
there's some, but not total similarity in composition to Earth. It used to be part of the Earth, but
Makes
some of it
sense.
came from the other planet too, and we may even have some evidence of it. Some rocks from the moon show a peculiar ratio of different kinds of oxygen atoms called isotopes. It's possible some of the more exotic isotopes of oxygen came from the other planet. Actually, this idea has been around for a long time, ever since the Apollo missions in the 1970s. There's a lot of evidence to support it too. But a new twist on it goes farther. When the
what's
moon
that?
formed from the debris of the collision, it was close to Earth, probably 20,000 kilometers away. The collision was so violent that it completely melted the Earth, and the moon was molten too. Tidal forces rapidly
should have been
synchronized
two
the moon's
moons.
spin and orbital period, so that one face always pointed toward Earth. If you were on that side of the moon, the Earth would dominate the sky, appearing 80 times larger than the moon appears in our sky today. And the Earth was hot. It hung there like a blast furnace and would have seriously heated the near side of the moon. The far side would have been much cooler. The material on the near side would have vaporized, and a lot of it would have condensed on the far side. Over time, This created the thicker far-side crust we see today. Then there was another seriously terrifying event, the Late Heavy Bombardment, a period of intense collisions with comets from the outer solar system, probably triggered by the movement of outer planets. This rain of millions of comets left scars on all the inner worlds, including the moon. That's when most of the Highland cratering occurred. Some of these collisions were massive, carving gigantic craters on the moon. Later, lava bubbled up through cracks in the moon's surface, flooding these craters, creating the Maria we see today. But the far side's crust was thicker. Impacts there couldn't get as deep, and it was harder for lava to break through and bubble up. That explains why there are so few Maria there. This idea that the Earth cooked the moon and formed the crustal anomaly is pretty new, and is still being argued over. There are also competing hypotheses about this as well. As we gather more evidence, we'll eventually get a better understanding of just why the moon's crust is so weird. After all that, I have to say, it's a little unfair to divide the lunar surface today into just highlands and Maria. For example, craters are pretty diverse. Some are small and simple bowl shapes. Others are huge, dozens of kilometers across and more, punctuated with a central peak, a mountain in the middle that formed as material from the gigantic impact that formed it splashed back up in the middle. Double craters are common too, probably formed when binary asteroids hit the moon. There are also crater chains, long lines of small craters that may have formed when a nearby large impact splashed out long streamers of material. Rays are common from big craters too. These are extremely long splash marks pointing radially out from the impact.
A couple years
probably formed when plumes of material were ejected. Some of the brightest are from the crater Tycho in the moon's southern hemisphere, and they stretch for 1,500 kilometers. The material is a bit more reflective than the surrounding terrain, so they appear bright in contrast, and are one of the most outstanding features visible near the time of the full moon. And there's so much more. Long, sinuous rills like dry riverbeds wind their way across the surface, actually the sites of ancient lava flows. There are lava tubes as well, where the top of the lava flow cooled and formed a tunnel through which lava could flow for long distances. Sometimes the roof, as it's called, collapses and forms a skylight, and we can see into the otherwise hidden tunnel. There are also cliffs, mounds, ancient and quite dead volcanoes, even mountain chains. There's no tectonic activity on the moon, but mountain ranges formed at the edges of giant impacts, where the huge forces unleashed pushed up the rocks at the crater rim. And new observations show there's something else on the moon too. Water. Deep craters near the moon's poles have floors that never see sunlight. Comet impacts can distribute water all over the moon, but most of it is destroyed by sunlight. But it can collect in these dark craters. And studies show there could be over 1 billion tons of water there in the form of ice. That would be a huge boon to colonization. Water is heavy and really expensive to transport from Earth. If it's already on the moon, that makes it a lot easier to put people
water there,
and that's in our
shelter
future,
there.
I have no doubt. We're starting to get serious about going back to the moon. NASA has plans of returning, and other countries like China and India are looking moonward as well. It's not a matter of if, but when. And it could be soon. So soon that I'd bet there's a really good chance the next person to step foot on the moon is already alive. Perhaps some teenage student in some country is just now taking an interest in science, math, engineering. An interest that will one day lead to another giant leap for humanity. Today you learned that the capital M moon is a lowercase m moon.
I like
it's
that
big
one.
Compared to Earth,
I was a little
skeptical
skeptical because I know a lot about the moon already. Mercury,
Mercury is the closest planet to the sun.
The second hottest.
That makes it pretty hot, but also it's pretty cool.
The second hottest planet. Venus is the hottest. It's got that greenhouse effect. Runaway greenhouse effect.
There are 7 naked eye solar system objects in the sky. Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. 7. Each of them was associated with a god in ancient times. Mercury was the Roman messenger of the gods, fleet of foot. Literally, he had wings on his shoes, and a rapid traveler. To anyone who's seen Mercury in the sky, this affiliation with the swift god is no surprise. Mercury, the planet, moves pretty quickly, visibly changing its position relative to the background stars, even after a single night. Despite its speed, the planet never gets very far from the sun. At best, it can reach a separation of about 28 degrees. That's about 3 times the apparent size of your fist held at arm's length. In 1639, the Italian astronomer Giovanni Suppi used a telescope to observe Mercury. It undergoes a complete cycle of phases over time, just like the moon does. The only way that can happen is if Mercury orbits the sun and not the Earth. Another checkmark in the column for heliocentrism, which was starting to look better and better all the time. And of course, that's the way things really are. Mercury is the innermost of the planets in the solar system. It orbits the Sun at an average distance of about 58 million kilometers, roughly a third the distance of the Earth from the Sun. That's why we never see it stray far from the Sun. From our viewpoint, its smaller orbit keeps it huddled closer to our star. That's why we see it move so rapidly too. It's closer to the Sun, so the gravity it feels from the Sun is stronger, and therefore its orbital velocity is faster than Earth's. It orbits the Sun once every 88 days, and that's also why we see it undergo phases. When it's between us and the Sun, we're looking at its dark side, and when it's on the other side of the Sun, we're looking at its fully illuminated half. In between, it goes through the same phases as the Moon: crescent, half full, gibbous, and so on. Not that this is such an easy observation to make. Because it never gets far from the Sun, it's always low to the horizon after sunset or before sunrise. When we observe it, we're looking through all of the muck and turbulence in our air, so it's usually pretty fuzzy. Making matters worse, it's a dinky planet, only about 4,900 kilometers in diameter, about a third the Earth's width. One upside to all this is that because it's close to the Sun, it's illuminated fiercely and can be pretty bright even near the horizon. If you ever get a chance to see it, you really should. It's pretty cool. Mercury's orbit is weird. It has the most elliptical orbit of any planet, ranging from 46 to nearly 70 million kilometers from the Sun. When it's closest to the Sun, it receives more than twice as much light and heat as when it's furthest. Mercury's too small and difficult to observe to see surface features on it, which for a long time made it impossible to figure out how long its day is. Astronomers assumed that the tides from the Sun had locked Mercury's spin so that its day was equal to its year, just like our Moon spins once for every time it goes around the Earth. However, in 1965, astronomers used Doppler radar to observe Mercury and directly measure its spin, and they got a surprise. Its day was only 59 Earth days long, not 88, but that's a significant number as well. To be more exact, the actual length of Mercury's year is 87.97 days, and the actual length of its day is 58.65 Earth days. If you divide those two numbers, you see their ratio is almost exactly 2/3. It turns out there's more than one way to tidally lock the rotation of a planet to its orbit. Remember earlier when I said Mercury's orbit is highly elliptical? The tides from the Sun are far stronger on Mercury when it's at perihelion, the closest point in its orbit to the Sun, than when it's at aphelion, the farthest point in its orbit. After Mercury first formed, tides from the Sun slowed its rotation, just like the Earth's tides on the Moon slowed the Moon down as well. But at some point, Mercury's spin slowed to where it was 2/3 of its orbital period. So at one perihelion pass, one side of Mercury faces the Sun. Then, 88 or so days later, it approaches perihelion again. But it's spun 1.5 times, and this means the exact opposite side of Mercury faces the Sun at this closest approach. 88 days later, Mercury is spun 1.5 times again, and the whole thing repeats. It turns out that's a perfectly legitimate, stable configuration, just like the 1-to-1 spin-orbit setup. The way the physics works out, tides like simple multiples. Once the day became 2/3 the period of the year, forced by Mercury's elliptical orbit, the tides stopped slowing it, and things have been that way ever since. Mercury's elliptical orbit, together with the 2-to-3 spin-to-orbit ratio, make for a very, very weird day on Mercury. If you stay in one spot, it takes the Sun 2 Mercury years, 176 days, for the Sun to go around the sky once. That's because if you're on the side of Mercury facing the Sun at one perihelion, the other side will face it 1 year later. It'll only be after the second year ends that you're facing the Sun again. But it gets weirder. Mercury's spin is constant. It doesn't speed up or slow down. However, its motion around the Sun is faster at perihelion than aphelion. At aphelion, Mercury's spin is a bit faster than its orbital speed, so the Sun moves rapidly westward across the sky. But at perihelion, Mercury's motion around the Sun actually more than compensates for its spin, so the Sun appears to stop in the sky and actually move backwards for a few days. Then, as Mercury pulls away from the Sun, its orbital velocity slows down, and the Sun starts to move west once again as the planet's rotation dominates. If you're at just the right spot on the planet's surface, this means you could actually watch the Sun rise, slow, stop, set again, then rise again. And you think time zones on the Earth are a pain. Mercury's hard to observe from Earth, and much of what we know about it is due to observations from space probes sent there. Mariner 10 made 3 flybys of Mercury in the 1970s and mapped about half the surface. We learned that it had almost no atmosphere, and was therefore unsurprisingly covered in craters. In 2011, the Messenger probe entered orbit around Mercury after making a series of close flybys. The pictures it returned were breathtaking and revealed a world that has seen a lot of pummeling over the eons. It's covered in craters, pole to pole, some hundreds of kilometers in diameter. The largest is called Caloris Basin, a whopping huge impact feature 1,600 kilometers across. There's some smoother plains on the planet's surface too, which appear to be older than the cratered regions. These plains are covered in cracks called rupes. These are compression folds, like wrinkles on a fruit rind that's dried out. Apparently, as Mercury's interior cooled after it formed, the planet shrank and the crust cracked as it tried to shrink as well. Several of the craters have extensive ray systems. Like on our moon, these are formed when impacts fling out long plumes of material that then settle down on the surface. One of my favorite things of all about Mercury, craters are named after artists. Musicians, writers, painters, and more. So we have craters like Botticelli, Chekhov, Debussy, Degas, Occhio, Sibelius, Vivaldi, and Zola. There's even one named Tolkien. Dipping below the surface, we can only infer what Mercury's internal structure is like. But the planet's dense, nearly as dense as Earth. We know the surface is rocky, so to be as dense as it is, it must have a large iron core, far larger in proportion to the planet than Earth's. Mercury's core may reach 3/4 of the way to the planet's surface. Why does it have such a high proportion of iron? Mercury may have formed as a larger planet, then got blasted in a huge grazing impact that blew away the lighter materials that had risen to the surface, leaving behind the denser part. Or maybe the heat of the still-forming sun vaporized the lighter materials off its surface. Mercury has a measurable magnetic field, which is a bit surprising since it rotates so slowly. Rotation plays a big part in the sun's and Earth's magnetic fields. But that fits with so much of its interior being molten iron. The bigger core may allow for a stronger field despite its slow spin. It doesn't have much of an atmosphere, but there is a trace of one, mostly due to its magnetic field trapping the solar wind and to material flung up from the surface after violent impacts from comets and asteroids. A lot of this material blown off the surface escapes the planet and gets blown away by the solar wind and pressure from sunlight. It forms a long comet-like tail that is tens of millions of kilometers long. This tail is comprised of elements like sodium, calcium, and magnesium, material that's known to be abundant on the surface. Speaking of which, here's a fun fact. Pound for pound, impacts on Mercury are more violent than they are on Earth. Mercury has weaker gravity, so it doesn't pull in impactors as hard as the Earth does. But it orbits the sun far faster than Earth does, so asteroids and comets tend to hit at higher velocity. That makes the explosive energy higher, making craters bigger. And there's one more surprise Mercury has, and it's really surprising. Despite being so close to the sun and having a surface temperature that can reach 430 degrees Celsius, 800 degrees Fahrenheit, astronomers have found water ice on Mercury. It exists in the bottoms of deep craters near Mercury's poles where sunlight never reaches. These are called cold traps, and temperatures there don't get above minus 170 degrees Celsius. It's not known for sure where the water comes from, but it's likely to be from comets and asteroids that impacted the planet, scattering the water across the surface. Of course, in the harsh heat, that water just goes and goes away, but in those deep craters, it can persist, accumulating over the eons. There may be billions of tons of it there. It's bizarre to think that in one of the hottest places in the solar system, there can be conditions so cold, ice can exist. But one thing we've learned about nature over and over again, it has a lot more imagination than we do. Today you learned that Mercury is the closest planet to the sun. It's airless and dense and is covered with craters. Its rotation is locked to its orbit in a 2:3 ratio, and together with its elliptical orbit makes a day on Mercury very long and very weird. And despite being very hot, there's actually water ice in deep craters at its poles. Crash Course Astronomy is produced in association with PBS Digital Studios. Head to their channel to discover.
We're up to Venus. I do like me some Venus. It's one of my favorite
Crash
planets.
Course is brought to you by Squarespace.
Venus was the Roman goddess of love. And honestly,
Oh
if you've
my.
ever seen it after sunset, hanging like a diamond in the twilight, the planet Venus is stunningly beautiful. The only problem? Venus is hell. Venus is the second rock from the sun, closer to the sun than Earth is. It's the third brightest natural object in the sky after the sun and moon, and it's shockingly bright when you see it. In fact, a lot of the time when people see it, they think it's an airplane. Some folks, and this is true, even report it as a UFO. Like Mercury, it never gets far from the sun. At best, it can reach about 45 degrees away. If you want to see it, the best time to look is after sunset or before sunrise. Through a telescope, Venus can be seen to undergo phases just like the Moon and Mercury do too. When it's on the far side of its orbit from Earth, we see the illuminated face, so it looks full. As it rounds the Sun and approaches Earth in its orbit, it gets bigger from our point of view because it's getting closer. But it also wanes, it's gibbous, then half full, then a crescent. When it gets between the Sun and Earth, it's as close as it can get to us, about 45 million kilometers away. It's a very thin crescent at that point, but close enough to us that you can see the phase easily with just binoculars. Ironically, even though we see only a small portion of it illuminated then, it appears so big that it's actually brighter than when it's full but far away. The orbit of Venus around the Sun is tipped with respect to the Earth's by a little over 3 degrees. So, like the Moon is seen from Earth, Venus usually passes above or below the Sun in the sky as it laps the Earth and pulls ahead in its orbit. But again, just like with the Moon, sometimes things line up just right and Venus passes directly across the Sun's face. This event is called a transit. During a solar eclipse, the Moon can completely block the Sun, but Venus is much farther away, so it can only block about 0.1% of the Sun. We see the planet as an inky black circle against the Sun's face. Transits were very important centuries ago. Scientists realized that by precisely timing the start and end of a Venus transit and applying a little geometry, they could figure out how far away Venus was and use that like a meter stick to measure the size of the entire solar system. Grand expeditions were sent to remote parts of the Earth where the transits were visible, but it turns out Earth's atmosphere blurs the disk of Venus just enough that exact timing of the transit isn't possible. Scientists had to wait until we could use radar and other methods to get the exact distances to planets in the solar system, but transits are still pretty amazing to watch. They're very rare. The way the orbits of Earth and Venus align, they happen in pairs, separated by 8 years, but then don't happen again for over a century. The last pair of Venus transits happened in 2004 and 2012. I was fortunate enough to see both the 2004 and 2012 transits, and they were totally cool. But the next one, December 10th, 2117.
Yeah,
if you missed the last two, sorry about that. Venus is actually so bright sometimes that it can be seen in broad daylight. I've done this myself. So here's an obvious question. Why is Venus so bright? Telescopic observations show it to be a nearly featureless white disk, completely covered in a thick cloud layer, reflecting almost all of the sunlight that falls on it. Okay, great, so that's why it's bright. But then why are its clouds so thick? Well, it turns out that Venus might be nice to look at from a distance, but up close? Yikes! In some ways, Venus is the planet in the solar system most similar to Earth. It's only a wee bit smaller, 12,100 kilometers across, about 95% the width of Earth, and has 80% the Earth's mass. But if it's a twin of Earth, it's the evil twin. Venus is closer to the Sun. At a distance of about 110 million kilometers, 2/3 the distance of the Earth from the Sun, you'd expect it to be warmer. What you might not expect is that its surface temperature is 460 degrees Celsius. That's 860 degrees Fahrenheit. Hot enough to melt lead, and it gets worse. Its air is almost entirely composed of carbon dioxide, and atmospheric pressure on Venus is a crushing 90 times that of Earth's. As if that's not bad enough, it rains sulfuric acid too, but it's so hot the drops evaporate before hitting the ground. Yep, Venus is hell. Why? How did it get so hot? It turns out Venus is a victim of a runaway greenhouse effect. A long time ago, Venus may have been more temperate and might even have had liquid water oceans. But the Sun was cooler when it was younger, and as it aged, it got hotter. At some point, the thinking goes, the Sun warmed Venus enough that its oceans started to evaporate. Water vapor is an excellent greenhouse gas, so Venus's heating accelerated. It got so hot the oceans boiled away. Any carbon dioxide dissolved in the water was released to the atmosphere, heating the planet even further and thickening the atmosphere hugely. It got so hot that the CO2 even got baked out of the rocks, which was like, well, throwing gasoline on a raging fire. The greenhouse effect raged out of control at that point. Venus lacks a magnetic field, so it has no protection from the solar wind blasting past it. Over billions of years, this stripped a lot of the lighter elements from the atmosphere, as well as all of the water. The resulting atmospheric chemistry is pretty screwy compared to Earth. Sulfur dioxide is a popular molecule there, and clouds form from sulfuric acid. Those clouds are high off of the surface and very white and reflective. It's pretty incredible to think about. The Sun warmed, so Venus warmed, and then a cascading series of events led to it being a ridiculously hostile environment due to the runaway greenhouse effect. Even though Mercury is closer to the Sun, Venus is way hotter. Given that, the last thing you might expect on Venus is Snow? Well, possibly. Observations show that there's something shiny on the mountaintops, and snow fits the bill, but it's not water ice like on Earth. As the thinking goes, at lower elevations, minerals like bismuthinite and galena would be vaporized by the heat. They'd then circulate up into the atmosphere and deposit onto the surface at mountaintops where it's cooler. If this is correct, then Venus is so bizarre it literally snows metal there. There's other weird stuff going on at Venus too. For one thing, it has an incredibly slow rotation rate. One day on Venus is about 243 Earth days. It rotates so slowly that at its equator, you could jog faster than the planet spins. Its slow spin is probably why it has no magnetic field too, since rotation is critical in generating the magnetic fields of objects like the Earth and Sun. Not only that, but the planet spins backwards. This is called retrograde motion, and in a sense it means Venus's North Pole got swapped with its South Pole. It flipped over. It's not clear why that happened. A lot of ideas have been proposed, including a giant collision that skidded the planet's spin to a halt. But as of right now, Venus's lazy rotation is still not completely understood. If you could survive it, living on Venus would be really odd. The thick clouds mean it's about as bright as twilight on Earth, despite being closer to the sun. The thick atmosphere also means surface temperature is about the same everywhere on the planet, pole to equator. Due to its backwards rotation, the sun would rise in the west, and due to the slow rotation, its day is actually longer than its year. Calendars on Venus would be a mess. But calendars would probably be the least of your worries if you had to live there. Incidentally, Venus has no moon. Being closer to the sun, it's possible that any moon it may have once had would have been perturbed by the sun's gravity and was eventually tossed out of Venus's grasp. It's also possible it simply never had one to begin with. And here's another fun fact. Venus is the most spherical of all the planets. Because it rotates so slowly, it doesn't bulge out at the equator from centrifugal force like the Earth does. The diameter from pole to pole is almost exactly the same as it is through the equator. We don't have a lot of data about the interior of Venus, though given its similar composition and size to Earth, it's not too crazy to think it has a core, mantle, and crust like we do. But even given the weird atmosphere, the surface of Venus is really different than ours. Venus doesn't have tectonic activity like Earth does. It's thought that water helps drive that, and Venus long ago lost its water to the greenhouse effect. Still, the surface appears to be very young. About 1,000 impact craters have been found, and they're evenly distributed around the planet. The majority appear to be in pretty good shape. They haven't been eroded much, indicating they aren't terribly old. Not only that, but the erosion we do see seems to be about the same for all these craters, indicating they're all roughly the same age. That's weird. This all points to some sort of catastrophic event that resurfaced the planet roughly 500 million years ago. Any features older than that were wiped out, and then big impacts over time created the craters we see now. But what could repave an entire planet? A big clue can be found by counting volcanoes on Venus. There are 167 bigger than 100 kilometers in diameter, a huge number. These volcanoes could, over time, pump out enough lava to cover the entire surface of Venus. There's also a lot of indirect evidence that volcanic activity is ongoing, now, today. One mountain on Venus, called Idun Mons, is seen to be abnormally warm, for example, indicating it might have magma under its peak. Also, sulfur dioxide levels dropped a lot in the 1980s, which may indicate a big volcanic event happened in the 1970s, blasting out lots of the gas, which then subsided. It's possible, though somewhat speculative, that the entire planet is a supervolcano, a ginormous pressure cooker of barely constrained magma. Every few hundred million years, the whole surface lets go in a colossal eruption, covering everything in lava. Yikes! Some volcanic features on Venus are different than on Earth. Without tectonics, slow bubbling leaks of lava from the interior of the planet can continue in one spot for a long time. This creates what are called pancake domes. Huge, flat, low domes. Many are dozens of kilometers across, but less than a kilometer high. The lava that formed them was probably really viscous, which is why the domes are flattened and spread out. The searing surface temperature of Venus probably kept the lava hot and helped it spread out more too. Oh, and one final note.
Move a little
Under
around.
international
I think she's done already.
agreement, surface features on Venus, mountains, plains, craters, and so on, are all named after women or goddesses of various cultures. This is an homage to the planet itself being named after a goddess, of course, but also, it's just cool. Today you learned that Venus is the same size as Earth, but with a super thick atmosphere. A runaway greenhouse effect makes it the hottest planet in the solar system. It has the slowest rotation of any planet and spins backwards.
But
tremendous
she's not really in
activity
frame.
ages ago resurfaced the entire planet, and it still may be active today. Crash Course Astronomy is produced in association with PBS Digital Studios.
I know you are, dear.
Head to their channel to discover more awesome videos.
Oh, baby girl. Oh,
Hey folks,
dude.
I'm Phil Plait, and this is Crash Course
Belly
Astronomy.
rubs.
You know, I
Belly
can't think of
rubs for
any
baby
object in
girl.
the sky
Oh,
that's
happy
captured our
girl.
imagination, like Mars
Who's a
has. The
happy
red planet was
baby
once
girl?
thought to be the god of war, and in more modern times has been the setting for a
yeah.
zillion science fiction novels, movies, TV shows, and more. And now that we've gone there, landed there, roved there, it's become far more than a simple background for an alien invasion story. It's become a world, a place, and maybe
90
one
bucks.
day, a destination.
For an ounce? That's pretty good. I'm actually paying about 120 bucks an ounce now, but that's Canadian.
Mars is the fourth
I don't know,
planet
it's
from the
about the
sun
same.
and the outermost of the
I
terrestrial
used to be
planets.
playing,
That is,
shit,
ones
what
that are
was it?
rocky and similar in size to Earth. It orbits on average a little
70
over
bucks
200 million kilometers
Canadian.
from the sun. That puts it outside Earth's orbit, and it never gets much closer to us than about
You all
60
done,
million
baby?
kilometers. It's colder than us
she
too,
just
with an
wants a
average
better
surface
spot.
temperature of about
I can't go
60
down
below
anymore.
0 Celsius. And it's not a terribly big planet.
Oh,
It's only
baby.
about half the size of Earth. Still, when it's closest to us in space, it shines brightly in our night sky, a red beacon glowering like an angry eye.
420.
No doubt this is why ancient
What?
civilizations associated it with war. But it turns out Mars isn't red because
Hold on a
it's
second.
bloody, it's red because it's rusty. Literally. That red color you see comes from fine-grained dust on the surface,
Oh, boy.
almost like ruddy talcum powder.
Why is
The
the
dust
tilt
is
not
rich in
working?
iron that's oxidized, forming rust. The dust coats a lot of the surface, giving it a butterscotch or
camera's
ochre coloring,
50
and also
bucks.
gets blown into the atmosphere. A lot of the surface of Mars is also
Where you
gray
at, baby? I
volcanic
can't see
rock
you
called
on
basalt,
camera.
and together with
Where
other
are you?
minerals gives Mars its overall reddish look.
Oh,
We can get a
baby girl.
decent view of
Oh,
Mars
she's
from
done
Earth
anyways.
using
Oh.
telescopes, but small features are maddeningly difficult
Is that
to
my
tease
crotch?
out. The idea of a
That's not my
clement
crotch.
environment on Mars
Okay.
stuck with us, though, at least until the 1960s and 70s when we started sending probes to the planet. They did not see a lovely,
That
habitable
might be
world.
interesting.
Instead, what we got were photos of a dry, dead, forbidding planet. The
Oops, sorry.
surface geography of Mars is weird.
Sorry.
There's a
We
huge
gotta fix
dichotomy
this. This
between
is
the northern hemisphere,
hastily
which
set
is
up.
mostly smooth plains, and the southern, which is
Crotch
cratered,
cam.
hilly
No.
highlands. Apparently,
Trina would be
Mars
here all the
suffered a
time.
tremendous impact from an
Trina,
object
crotch
hundreds
cam.
of kilometers across
Oh,
eons
yeah.
ago. It left behind a vast basin
Let me
near the
just
north
fix this
pole of
first.
the planet, which filled with lava. Topographic maps show the northern hemisphere has much lower elevations than the southern and can be depressed by several kilometers. Walking from the south to the north pole is essentially all downhill. Another large feature is the Tharsis Bulge, a huge plateau that's home to the 4 biggest volcanoes on Mars and the largest volcano in the solar system, Olympus Mons. Mars doesn't have plate tectonics today, but there's evidence it once did. Tharsis was probably over a hot spot, a plume of hotter material rising up through the planet's mantle. That's what may have created the bulge, and as the plate slowly moved, the plume punched through the crust to create the chain of 3 smaller, but still huge volcanoes. But the grandest of the surface features on Mars is easily Valles Marineris, a canyon discovered when the Mariner 9 probe orbited Mars in the 1970s. It's a gigantic crack in the surface of Mars, 4,000
Those are actual
kilometers
photos.
long, 200
They're so
kilometers
beautiful.
wide, and 7 kilometers deep. That's 10 times longer and 10 times wider than the Grand Canyon. Unlike the Grand Canyon, it wasn't carved
Little
by
baby
water.
Grand
It may have
Canyon?
formed when the Tharsis Bulge rose up, creating the valley as a radial crack in the surface. Mars, like Earth, has polar ice caps. Both are mostly water ice, several kilometers thick, but they get seasonal coatings of dry ice, frozen carbon dioxide, that covers them from 1 to 8 meters thick. This happens in their respective winters. In the summer, sunlight thaws the CO2, turning it directly into a gas, which then blows away from the pole, generating fierce winds. Speaking of which, Mars has an atmosphere, but it's thin. Pressure at the surface is less than 1% of Earth's, and the air is mostly carbon dioxide. In fact, as much as a third of the Martian atmosphere freezes out every winter to coat the polar ice cap.
It was
The air doesn't
2017,
provide
yeah.
much of a shield from asteroid
next
and
one-
comet impacts, so
Wait.
the surface is heavily cratered, and it still
2017?
gets hit today. The space probe Mars Reconnaissance Orbiter has been circling Mars so long, it's actually seen new craters from
What's the
fresh
next one?
impacts on the surface. However, the atmosphere
Let's
is
see,
substantial
here's
enough
$10
to
draw.
interact with the surface. Winds
that'd
blow
be beautiful.
seasonally, filling craters with the ubiquitous dust. There's also sand on Mars, made of
That would
eroded
be
basaltic
beautiful.
rock, so it's gray. The wind blows this into beautiful dunes, including series of parallel
caught one
ridges
when
and
I was a
crater
kid.
floors, and barcon, or horseshoe-shaped dunes.
I
Mars
just stared
also
at
gets
it.
dust
I didn't know
devils,
the difference as a
towering
kid. I was like,
vortices
oh,
of
what's
wind
this?
similar to tornadoes.
Eyes
These dust
burning
devils
out
have
of my
been seen
skull.
from
I didn't give-
orbit,
I didn't
and when
know
they
any
blow the
better.
red dust around on the grayish
Oops.
basaltic plains, they can leave behind incredibly complex and beautiful
Oh, that's
curly
beautiful.
cubes. One of my favorite recent
Wait,
discoveries
wait,
about
let me see that
Mars is
again.
that it leave behind incredibly complex
That would be like a weird ass tattoo. People are like, what the fuck is that? It's like, that's the surface of Mars right there, bitch. Because this looks like skin, kind of ish. That's just weird. People think you'd have a disease or something. But I like it.
and beautiful curlicues. One
I
of my
like it.
favorite recent
It
discoveries
is
about
beautiful.
Mars is that it has avalanches. There are lots of cliffs towering above the surface, and in the spring, when buried frozen carbon dioxide thaws, it can
Hey,
dislodge
Shadow,
material, creating
yes!
tremendous cascades of rock
Shadow
and
knows
dust.
what's up.
Several of these have been caught in the
Oh, I
act
got
by
this stupid
orbiting
ad
space
bullshit
probes.
again.
Mars
I
has
gotta
two
take a clip.
moons, small potato-shaped rocks named Deimos and
That's
Phobos.
the
Both
better
are
one.
tiny. Phobos is about 25 kilometers across, and Deimos just 15. Both look very much like asteroids, and may
10-minute
indeed have been
recording and just
captured by
loop it.
Mars from the nearby asteroid belt. To be honest, though, it's not clear what their
I
origins
hastily
are.
set up this
Phobos
scene.
orbits Mars only 6,000 kilometers over the surface, and it moves so rapidly in its orbit that it orbits faster than Mars rotates. From the surface, it appears to rise in the west and set in the east. Tides from Mars are altering its orbit, slowly lowering Phobos closer and closer to the surface. In a few million years, it's
Kaboom!
expected to drop low enough to actually enter the atmosphere and impact the surface. That'll be really exciting to watch.
Hell yeah.
From a safe distance. Incidentally, from some locations on the surface, the moons can be seen to transit the sun, passing directly across its face. The rovers on Mars have taken lots of pictures of these events, which is pretty cool. So Mars has rocks, air, weather, volcanoes. But what about water? If it has frozen water at the
does have
poles,
water?
what about the rest of the planet? We know there's water ice
Probably
at the
underneath it.
mid-latitudes of Mars.
I think
Some
there's
recent
water
small
underneath.
asteroid impacts have white area around them, underground deposits of
Yeah.
ice splashed out by the impact.
Yeah.
There's no strong evidence of liquid water on the surface of
No.
Mars right now, though. Some
Agreed.
crater walls collapse a bit.
Need
and
that
have dark
evidence,
channels
baby.
running down them, which look like they could have been carved by flowing water. But there are other possible sources too, so their cause still isn't certain. But in the past, things were different. Mars was once very wet. There's tons of evidence for flowing water on the surface long ago, including dry riverbeds, dry
Shadow.
lakes, sedimentary layers, and minerals we know need water to
comment.
form. There's even evidence Mars had oceans, but that's all gone now. What happened? It's not clear. Billions of years ago, Mars was almost certainly warmer and had a thicker atmosphere. But for some reason, its internal dynamo shut down, and its magnetic field disappeared. This left it vulnerable to the solar wind,
think it was
and
'cause
over
it was
billions of
a
years, the
smaller-
Martian atmosphere was eroded away.
A smaller
Water
planet,
went with
and
it. This
it didn't
raises
get as
another
bombarded
obvious
as much
question.
as Earth.
If it had air and water, could it have had life?
So it didn't
that
stay
question
hot
wasn't taken
enough.
terribly seriously just a few decades ago.
I
But
think
now
it could
we're
have.
very
Mars
interested
could
in it,
have had
enough to
life
spend
a
a lot of
long
money
time
sending
ago.
probes to Mars to look at what conditions for life are like now and
Mm-hmm.
once were in the past. It's still an open question, and we know life on Earth got its start not long after the surface cooled. Mars is smaller and cooled more quickly after its
Yep.
formation, so it's not crazy at all to wonder if life formed there even before it did here.
It seems
Intriguingly, the
like-
Curiosity rover detected simple organic molecules in
That'd
the
be
rock sample. This
huge.
doesn't mean there's life, but it means the ingredients were and are there. It also detected a brief spike in methane, a volatile gas that can be produced by life, as well as by other geologic processes. The evidence we have right now is maddeningly
is meh.
vague. But we're just starting out. Give it time. Mars isn't the same planet it used to be.
That'd
but
be
that doesn't
huge.
mean it's off limits. Getting to Mars is hard. Over half the missions sent there have failed, but not impossible. We've had amazing successes, including orbiters, landers, and rovers. I'd say we've learned as much about the red planet in the past couple of decades as we had in
There's a theory out there in astronomy about panspermia, where something hit Mars a long time ago, flung off life, and which hit Earth and then became Earth's life. So we're all Martians in a way, but that's just a theory, of course.
all the centuries of study before them. Still, all we've sent are robots. They're good and relatively inexpensive, but they're slow.
Wally.
They can only cover so much ground. A human could do as much in a week as a rover could in years. But humans are fragile. We need water, air, food. We aren't terribly tolerant of radiation or vacuum. But the idea of sending people to Mars isn't as nuts as it might have
Nope.
once been. We're getting
It's
better at
not.
building rockets. And the tech needed for human exploration of Mars is being developed now. There are even discussions about landing sites and where to build bases.
Yep.
One interesting idea is to use lava tubes, underground caverns created by ancient lava flows where the
that's the
top of the
same-
flow cooled and created a roof. We
The lava tubes is the same theory they're going to be using to get colonized on the moon as well. That's probably the best way to go.
know these exist on Mars because we've seen holes in the roofs, called skylights, openings to the cavern below. This would provide shelter from solar radiation, protection from weather, Mars can get some pretty nasty dust storms in the spring and could be sealed up and filled with air. From there, a lot of the planet could be explored, and in a few years, we'd once again dwarf everything we've learned up to that point. I can't say when this will happen. 20 years from now, maybe 30 or more.
If we actually got there with the instruments to do ourselves back and forth instead of just sending a robot, the amount we'd learn would be incredible.
But it'll happen. Eventually, there will be life on Mars, and it'll be us. Today you learn that Mars is smaller and colder than Earth.
That's,
it has polar ice caps and
I
lots
like
of
these.
rusty
You know,
dust
usually
covering its surface.
this
It
is
also
probably
has
like
the
the
solar
baby
system's
episode,
largest
so to speak.
volcano and valley. It's dry now.
Jupiter, going through the planets, but I do believe there's
As we take our grand
way
tour
up.
of the solar system
Light,
here on Crash Course
meteors,
Astronomy, we're going to skip over the
distance.
asteroids for now. We'll get to them, I promise.
Stars.
And instead, pay a visit to the king of the planets, the big guy, the
Exoplanets?
top
Ooh, I'm
dog,
looking forward
the
to
big
that
cheese,
one.
the head honcho.
Oh, I
the
love
one
brown
and only
dwarfs.
Jupiter.
They're like suns that didn't quite become suns. They're not quite enough to become called a sun, but not small enough for a planet. Low mass.
Jupiter is the
like
largest planet
dwarfs.
in the solar system. It's
High
not
mass
even
stars.
close. All the other planets could
Start
fit
getting into
inside
really
it
good
with room to
stuff.
spare. It's a gas
Really
giant,
good
which
stuff.
means it's gassy and giant. And I do mean giant. It's 11
right.
times wider than Earth. More than 1,000 Earths could fit inside it. And it has a mass of over
Deep time.
300 times that of our
I
planet.
wanna
Despite
see
its
this one big
bulk,
time.
it rotates extremely rapidly.
I have no idea what this
One day
is.
on Jupiter is a mere 10 hours long. That's
Dark
the
energy.
fastest spin of any of the planets in the solar system. Not surprisingly,
Gamma
a
ray.
planet that big can reflect a lot of sunlight. And even though it orbits the sun on average at a distance of about 800 million kilometers, it's one of the brightest objects in the night sky.
familiar
With
with most of
binoculars or a
this,
small telescope, Jupiter is a
not
wonder.
this guy.
You can easily see it as a disk,
time.
and
What the
its
fuck is
4
that?
biggest moons are readily visible. If they weren't hidden by the planet's glare, they'd be naked eye objects. Galileo himself discovered those moons. They're worlds in their own right, and so we'll dive into them, literally, in the next episode. When we look at Jupiter, we're not seeing its surface. We're seeing the tops of its clouds,
Yeah,
and there are
it's a
strange
gas
mix of
giant with a
permanence and
solid
change.
core.
The atmosphere of Jupiter is banded with multiple stripes running parallel to its equator. The lighter color stripes are called zones, and the darker ones, belts. They're fairly stable, though their shape and coloring change over time. Belts and zones circulate around the planet in opposite directions. They form due to convection in Jupiter's atmosphere. Upwelling air cools and forms white ammonia clouds. That creates the light-colored zones. That air flows to the sides and sinks, and sunlight changes the chemistry in the clouds, forming molecules that color the air yellow, red, and brown. This is what causes the darker belts. In May of 2010, one of Jupiter's biggest belts sank so deeply it disappeared from view completely, covered by other clouds. Then, a few months later, it
Hold on.
popped back up and
Hold on.
reappeared. None the worse for
What? It's like, whoa. Oh, it like this band sunk so deep that it disappeared. Then it came back up.
view completely, covered by other clouds. Then, a few months later, it popped back up and reappeared. None the worse for wear. This has happened several times in the past, too. I saw one
Why?
of these events once through a telescope, and Jupiter looked really weird, lopsided. Turbulence in the regions between zones and belts can create storms, gigantic vortices raging in the clouds. Dozens of them
between,
dot the
yeah.
face of Jupiter all the time, but there is one to rule them all, the Great Red Spot, a
The Great Red
fittingly
Spot.
huge
Remember-
storm for a giant
remember,
planet. It's
learning about
actually
that in
a
school as a
colossal
kid?
hurricane, several times larger than our entire planet Earth, with sustained wind speeds of 500 kilometers per hour. And it's old. It was first seen in the late 17th century. Imagine a storm on Earth
I lost
lasting
my
for more
audio.
than 3 centuries.
We'll see
And it
if
may
comes
be
back
far
on.
older. The 1600s is just when we first spotted it. So why is it so stable? It turns out that a vortex, a local spinning
Natural
region in a fluid,
satellites?
can persist if the fluid in which it's embedded is itself rotating.
they're
Jupiter's rapid
moons.
spin is what keeps the red spot circulating. And the redness is probably due to cyanide-like molecules that absorb
Natural
blue
satellites,
light,
another
letting redder
name
light
for a
pass
moon.
through. Weirdly, the red spot appears to be shrinking. It was
I think what the thing most people are kind of weird about is we call our moon the moon, when actually I think the actual name for the given name for our moon is Luna. So, instead like Enceladus and all these other moons of Europa, all these other moons have names, and the name of our moon is Luna. So we just call it the moon, but it's Luna.
Substantially bigger and more elongated just a few decades ago. It changes color over time too, having gone from deep red to salmon and then back again. No one knows why its shape, size, and color change, but given how long the spot's been around, I doubt it's going to evaporate anytime soon. Remember, we're only seeing the tops of the clouds on Jupiter. Its atmosphere is thick, several hundred kilometers deep. Like the composition of the Sun, the air on Jupiter is mostly hydrogen and helium, but it's also laced with ammonia, methane, and other poisonous gases. As you dive into Jupiter's atmosphere, the pressure increases with depth, but you'll never reach the surface. The planet doesn't really have a proper surface. The gas gets thicker and hotter, and eventually just sort of smoothly changes into a liquid over a several hundred kilometer range below the clouds. Below that is where things get really weird. Instead of a mantle like terrestrial planets, Jupiter has a huge region made up of liquid metallic hydrogen. We think of hydrogen as being a gas, or if it gets really cold, a liquid. But under the ridiculous pressures generated deep inside Jupiter, smaller. Hydrogen undergoes this strange transformation.
Once they get to a certain size, they become a planetary satellite or an asteroid.
But instead, share them. This means the hydrogen can conduct electricity and has other properties more like a metal. This substance is hot too. About 10,000 degrees Celsius.
Asteroids go around the sun,
the surface of the
planetary
sun.
satellites will go
if we
around
could
a
see
planet.
it, it would glow tremendously
Saturn has
bright. Finally,
billions
at its center is most likely a
planetary
dense core of
satellites
material,
create the-
probably composed of rock and metal. We really don't know because it's incredibly difficult to understand the physics and chemistry of material locked in at those pressures and temperatures. What's weirder is that we're not even sure if Jupiter has a core. If it did, it's possible it was eroded away by currents of hot metallic hydrogen early on in Jupiter's formation process. It's also possible it never had a core in the first place. The solar system formed from a flat disk of gas and dust. The center of this disk is where the sun was born, and it's thought that the planets formed as smaller particles of material stuck together during random collisions farther out in the disk. As they got bigger, much bigger, these protoplanets eventually started to grow even faster by drawing in material around them due to their gravity.
Gas.
Jupiter formed where the disk was thick, rich with material. It's possible that several large protoplanets were forming, collided, and stuck together to really kickstart Jupiter's growth. If that were the case, it started out with a rocky metallic core, and once it got big enough, it drew in that gas that made it the giant we see today. Another idea is that Jupiter didn't grow from the bottom up, but from the top down. The disk itself collapsed in several places to form huge distended clumps. These then would have collided, stuck, and created the planet. If that's the case, then Jupiter might not have a core at all. These two different mechanisms make different predictions about Jupiter's structure, and that means that
I need to listen to that again.
The disk itself collapsed in several places to form huge distended clumps. These then would have collided, stuck, and created the planet. If that's the case, then Jupiter might not have a core at all.
That doesn't make sense to me. If the things collide and stuck, they form a core to start with. That core then creates more gravity, draws in more crap, more gravity, more crap, more gravity, more crap. It just has to be a core.
These two different mechanisms make Jupiter's growth. If that were the case, it actually started to grow even faster. It was thick, rich with material. It's possible collided and stuck together to really kickstart Jupiter's growth. If that were the case, it started out with a rocky metallic core, and once it got big enough, it drew in that gas that made it the giant we see today. Another idea is that Jupiter didn't grow from the bottom up, but from the top down. The disk itself collapsed in several places to form huge distended clumps. These then would have collided...
Distended clumps. What does he mean by that? Distended clumps. Distended. That's unfamiliar term.
Stuck and created the planet. If that's the case, then Jupiter might not have a core.
I'm not sure what he meant by that.
These two different mechanisms make different predictions about Jupiter's structure, and that means that, hopefully, we can eventually figure out which is correct by studying Jupiter more carefully. But at the moment, we still don't know. Either way, Jupiter grew immense, and it's mostly liquid under all that atmosphere. Couple that with its rapid rotation, and you can see it's noticeably flattened. It's wider at the equator than through the poles by about 6% due to centrifugal force. So Jupiter is a big bruiser of a planet. But how close was it to becoming a star? Sometimes people ask me if Jupiter is a failed star. In other words, as it formed, it almost got massive enough that nuclear fusion could start in its center, turning it into a star. I see this a lot on TV shows and in articles, and it really burns me up. When a star forms, hydrogen fusion starts when the star gathers so much mass that its gravity can compress atoms together in its core hard enough to get them to fuse. This happens when a star has roughly 1/12 of the sun's mass. In fact, the smallest stars we see do have about that mass. What about Jupiter? The mass of Jupiter is about 1/1000th the mass of the sun. Far too little to undergo fusion in its core. If you want to turn Jupiter into a star, you'd have a lot of work ahead of you. You'd have to take Jupiter and then add about 80 more Jupiters to it. Saying Jupiter is a failed star is really unfair.
It's not.
It's not a failed star.
Close.
It's a really successful planet. Even though Jupiter isn't a star, it does have another funny property. It emits more heat than it receives from the sun. The Earth and other terrestrial rocky planets are in a heat balance with the sun. We emit pretty much the same amount of heat that we receive, but Jupiter's different. After it formed, it started to cool by radiating away heat from its upper atmosphere. A large fraction of the planet is a gas, remember, and when you cool a gas, it contracts. So the atmosphere cools and contracts, but this increases the pressure inside the planet, so it heats up. That heat works its way out of Jupiter and gets radiated away as infrared light. In the end, the amount of heat Jupiter gives off is more than it receives from the sun. It's still actively cooling 4.5 billion years after it formed. Oh, and hey, remember the belts and zones, the stripes we see in Jupiter's atmosphere and all the storms that pop up? Those are driven in large part by Jupiter's internal heat. On Earth, our weather is powered by heat from the sun, but on Jupiter, they get their energy from the planet itself. Jupiter has a very strong magnetic field, no doubt due to all of that metallic hydrogen inside it, coupled with its rapid rotation. Like Earth, it has aurorae at its poles as the solar wind is funneled down to the cloud tops. As we'll see next week, Jupiter's moons affect the magnetic field and aurora.
If you've never been to the north or the south areas to see the aurora, I highly recommend that. I used to live in northern Manitoba, Canada, and it was right over our heads. And we would quite often just head on out and just lay in just lay on a truck bed or stare up, and it was just incredible. I recommend it.
On Jupiter as well. Jupiter also has a ring, though it's not nearly as grand as Saturn's. It wasn't even discovered until we sent space probes to the planet. The ring is made of dust, probably thrown into orbit around the planet due to meteorite impacts on its smaller moons. Speaking of impacts, we know that Earth gets hit by interplanetary debris all the time. Go outside for an hour and you're bound to see a few meteors. Jupiter, being larger and with more gravity, gets hit a lot more. A lot more. A lot. And sometimes it gets hellaciously whacked. In 1994, the comet Shoemaker-Levy 9 impacted Jupiter multiple times. Jupiter's fierce gravitational tides had ripped the comet into dozens of pieces.
I remember that.
And each slammed into the planet,
was that long ago?
After the other, with the force of millions of nuclear weapons. The scars left in the upper atmosphere from the plumes of material that exploded outward lasted for months. Several smaller impacts have been seen in Jupiter's atmosphere since then, and it may suffer an impact large enough to see from Earth every year or so. And while that sounds scary, it might actually be our savior. There's an idea that Jupiter's gravity tends to take comets that fall toward the inner solar system and fling them away into interstellar space. Over the eons, this has cleaned out a lot of otherwise dangerous objects that could have eventually hit Earth. On the other hand, Jupiter has a tendency to warp the orbits of some other comets so that they do swing by the Earth. It's hard to say if Jupiter's influence is a net benefit or not. But either way, it's clearly the 2 septillion-ton gorilla in the solar system. Today you learned that Jupiter is really, really big. It's the biggest planet in our solar system.
What's next?
It has a dynamic
Jupiter's
atmosphere.
moons. Ooh, that's actually pretty interesting. Jupiter itself is pretty interesting, but its moons is really interesting.
As we
Some
saw
of them
in the
they
last
think are
episode,
going to support
Jupiter
life or
is
even
by far
have
the
life.
largest and most massive planet in the solar system.
That
means it has a very strong gravitational
right back
field, which also means it can hold on to a lot of moons. A lot. Right now, as we record this episode, there are 67
I think
that
so
have been
too,
confirmed. And how many it really has
Both Jupiter and
depends
Saturn,
on how small
even
an object
Neptune
you're willing
to
to call a
degree.
moon.
Hey, what was the bathroom? Until momentarily. Actually, just
In
two momentarily.
1610, Galileo pointed his telescope at Jupiter and witnessed a revolution.
Wireless headset.
Literally,
I
he
hear
saw
everything.
3 little stars lined up on either side of Jupiter. Stars he could not see with his naked eye, and they moved. A week later, he saw a 4th one, and he knew he was seeing objects revolving, orbiting around Jupiter. It was proof that not everything in the solar system revolved around the Earth. That was a pretty big deal. Those 4 moons are now called the Galilean moons in his honor. Not bad for a week's work. All 4 are really big, too. If Jupiter weren't there, drowning them out with its glare, they'd be visible to the naked eye. In that case, we might even call them planets, too. The biggest of Jupiter's moons is Ganymede. At 5,270 kilometers across, it's the biggest moon of any planet. It's even bigger than the planet Mercury. In fact, in size, it's halfway between Mercury and Mars. Size isn't the only planet-like characteristic of Ganymede either. It's mostly rock and ice, but it probably has a liquid iron core. It even has a magnetic field, likely generated by that liquid core. The surface is similar to our own moon in that there's very old crater terrain, as well as smoother, younger areas. Ganymede is also crisscrossed with large grooves. It's not clear what the origin of those grooves is, but it may be related to stress and strain on the surface caused by the tides from the other large moons as they orbit Jupiter and pass each other. Ganymede has a surprise well below its surface too: oceans of water. Measurements of Ganymede's magnetic field, made during multiple passes by the Galileo spacecraft in the 1990s, combined with Hubble observations of the moon, indicate Ganymede has quite a bit of salty liquid water deep beneath its surface. As we'll see in a sec, it's not alone in that regard. The next biggest moon is Callisto at 4,800 kilometers in diameter. In many ways, it's similar to its big brother Ganymede, mostly rock and ice. It probably has a rocky core, then a layer of mixed rock and ice above that. The surface is mostly ice, but mixed with darker material as well. It has a magnetic field too, but it probably doesn't have a metallic core. The surface is heavily cratered, and there's no indication of any volcanoes or tectonic activity. That means the surface is very old, maybe as old as Callisto itself. It even has an atmosphere, but it's a tad thin, roughly 1/100 billionth the pressure of Earth's air at the surface. Callisto orbits Jupiter farthest out of the 4 biggies, almost 2 million kilometers away. That's too far to gravitationally interact with the other 3. When I talk about the moons affecting each other, it's really the other 3 interacting. Next up is Io. It's only a little bit bigger than our own moon, and orbits Jupiter so tightly it only takes about a day and a half to go around the planet. When the Voyager 1 space probe passed Io in 1979, it revealed a surface that was really weird. It was yellow and orange and red and black, and didn't seem to have any obvious impact craters. An engineer, Linda Morabito, noticed that in one image, there appeared to be what looked like another moon behind Io, partially eclipsed by it. But that was no moon. It was a volcano on Io erupting, its plumes shooting up from the surface and opening up into a wide arc. Io is the most volcanic object in the entire solar system, with over 400 active volcanoes. Quite a few of them are erupting at any given time, and images taken even a few months apart show changes in the surface due to ejected material. A lot of the eruptive material is rich in sulfur, which is why the surface has all those odd colors on it. The energy for all this activity comes from the other moons. As they pass Io in their orbits, they flex it via tides, heating its interior through friction. A lot of that sulfur ends up as a very thin atmosphere around Io, and some of those sulfur atoms are then picked up by Jupiter's powerful magnetic field as it sweeps past Io and accelerates them to very high speeds. This has created a tremendous donut-shaped radiation belt around Jupiter, like Earth's Van Allen belts, but far more powerful. The radiation there is so intense it would kill an unprotected human in minutes. Of course, if you're floating in space near Jupiter unprotected, you might have some more immediate concerns. Oh, one more thing. Both Ganymede and Io are magnetically connected to Jupiter. Charged particles flow from those moons along the lines of magnetism to Jupiter, which then slams them down at Jupiter's poles, just like the Earth does with the particles from the solar wind. On Earth, this creates the aurorae, the northern and southern lights, and it does at Jupiter too. You can even see the ultraviolet glow where each of the moons connects to Jupiter, their magnetic footprints in the planet's atmosphere. And now we come to Europa, the smallest but perhaps most exciting of all the Galilean moons. Slightly smaller than our moon, it was known for decades to be very reflective, meaning its surface was probably loaded with water ice. But even so, the Voyager observations were shocking. They showed a surface completely lacking in craters, meaning something had resurfaced the moon like Io or Venus, but Europa has no volcanoes. Even more intriguing, the surface was covered in long cracks, dark streaks all over the moon, as well as complex ridges. These and other features appear to be due to material from the interior of Europa welling up and forming the new surface, kind of like the way lava does on Earth. But in this case, the material is water. It's now thought that Europa has an entire ocean of water sealed up under a solid crust of ice several kilometers thick. Water welling up and moving under the crust causes it to shift, creating all the various surface features. The amount of water that may be locked up on Europa is staggering, easily more than all the water in all the oceans on Earth. Like Ganymede and Io, the interior of Europa is kept warm by tidal flexing from the other moons, keeping the ice melted. Now get this. A lot of Europa's material is silicate
moons
rock,
and
like
shit,
on Earth and other
like,
terrestrial
everything
planets,
flexes a little
located
bit,
in a layer
and there's
under
enough
the ocean. If this interacts
gravity
with the
in
ocean in
Io,
the same way Earth's oceans
or Europa,
interact with
sorry,
the seafloor,
to
this could
make
make
that
the subsurface Europan
that
water
flexing and
salty. In
to make
fact,
heat
those dark
in the
cracks on
core,
the surface
enough
have been
heat
found to be rich in salt and organic
to have
materials.
liquid
In other
water.
words, carbon-based compounds.
Liquid water.
This is pretty exciting.
Yeah.
We think Earth's life originated in salty ocean water.
Yep.
If there are carbon-based molecules actually in Europa's water,
I love
it's not
Europa.
too
It's
crazy
my
to wonder if
favorite.
the same spark that occurred here also
favorite.
happened there. We think Europa has everything it needs to spawn life. We just don't have any direct evidence of it yet. Some people have proposed sending a space probe to Europa specifically to look for life. It would land near a crack in the ice where the crust is thinner and somehow penetrate it, perhaps melting its way down. Chemical sampling could then look for signs of biological activity. That's amazing to me. The idea of life in Europa, even if it's just microbial life, is taken very seriously by astrobiologists, scientists who study the
Microbial life.
possibility of life in space.
Any
It used to
kind
be
of life.
science fiction. Now it's a topic of scholarly research. Astronomers
we
have a
need to get
concept
to,
called the
Mars.
habitable zone, the
We gotta get
distance
to
a
the
planet
moon.
can be from its parent
gotta
star,
get to
where the
Europa.
temperature on the planet's surface can support liquid water.
And maybe
It's a
even
fuzzy
Io.
concept. Venus and Mars are both technically in the sun's habitable zone, but Venus is too hot
19.
and Mars too cold for liquid water. Atmospheres make a
19,
big
he
difference.
says.
But it's still a useful concept as a rule of thumb for potential habitability. But Europa changed that. Jupiter is way
list them out
outside
for
the
us?
sun's habitable zone. Yet there's Europa, all wet. It's a great example that we need to let our ideas
Cheers.
breathe a bit sometimes. Let them relax and flow outside the boundaries we set for them. When we look for signs of life on planets orbiting other stars, I bet we'll have to keep our minds open to types of life we've never considered before. Those are just the 4 big moons of Jupiter, each
I
thousands
have
of
mixed
kilometers
feelings
across.
about ice.
They probably formed
I live in
along
Canada.
with Jupiter, coalescing from the eddies and whirls
Love-hate
around
relationship with it.
proto-Jupiter as it formed billions of years ago. But the planet has dozens of other moons too.
I can
About
skate
the
on
only
it.
thing they all have in common
I
is
can
that
slip
they're
on it.
tidally locked to Jupiter. They all rotate once for every time they go around the planet. Jupiter's tides are hundreds of times stronger than Earth's.
I can
so
rally
no
race with
surprise
it.
there. The next biggest moon after the
can
big
crash
4
on it.
is way smaller. Named
Love-hate.
Amalthea, it's an irregular lump about 250 kilometers across its longest dimension. It was discovered in 1892, and it's red, probably polluted by sulfur from Io. It orbits just over 100,000 kilometers from Jupiter's cloud tops. If you stood on Amalthea's surface, Jupiter would fill half the sky. The moons get smaller and more irregularly shaped from there, with
I haven't gone skating in
Himalaya
a
and
long
Thebe
time,
and
actually.
Alara and Pasiphae, down to Hegemony and Kale and
Might have
Kallichore,
used my
which are no bigger
skates
than
3 or 4
hills.
times.
Many of the irregular distant moons of Jupiter orbit the planet backwards relative to the others in what are called retrograde orbits. They may be captured asteroids from the nearby
even know where the
asteroid
fuck
belt.
they
Many
are.
of the moons have orbital characteristics that are very similar too, which may indicate they were once a single object that broke up. Several such families of moons orbit Jupiter. The smallest moons we've seen are roughly a kilometer across. If they were sitting on Earth, they might be hard to pedal up on a bicycle, but orbiting Jupiter, they hardly rate as more than debris. There are probably thousands of moons the size of houses circling the planet, and who knows, maybe millions the size of tennis
The
balls.
size
Should
of
we even
houses?
call
I
those
think-
moons?
no, I don't think so.
Maybe, but I
No.
don't really worry about that kind of thing.
I wouldn't say
The
it.
important thing to
More like a-
remember is that these are worlds,
an
big and
orbital
small,
satellite.
each fascinating, rich, and diverse. And there's still
Yeah,
a lot
that's what they
more
are.
left to explore about them. Today you learned that Jupiter has lots of moons, and 4 big ones. They're mostly rock and ice.
Ooh, getting up to it. We're almost there.
This
We're
episode of
almost
Crash
there,
Course is
Shadow.
brought to you by Squarespace.
Uranus. One
So
more.
now we've come to the last of the
12
naked eye
minutes.
planets in the solar system, Saturn. It's the second largest planet, but ironically, the least dense. In fact, if you could find a bathtub big enough, Saturn would float in it, but it would leave a ring.
Oh, that's your kind of joke, Shadow. But it would leave a ring.
Okay,
my kind
that's
of joke
the oldest
too.
joke
I
in
laughed,
astronomy,
right?
but it's
I
true.
laughed.
Saturn is a gas giant, which means it has a thick atmosphere. Like Jupiter, it probably has a rocky core several times the mass of Earth, surrounded by layers of ice and weird metallic
It was
hydrogen.
so bad,
On
it
top
was
of all
good.
that is its atmosphere, hundreds of kilometers deep, composed mostly of hydrogen with a smaller amount of helium and a whole bunch of trace gases like methane and ammonia. Overall, its density is about 2/3 that of water. It wouldn't really float, though. Its gravity would draw in all the water from the giant bathtub. Although, actually, come to think of it, a bathtub filled with water big enough to put Saturn in would have more mass than the planet, so the water would pull Saturn in. Astronomy is fun. Saturn spins really
Yep,
quickly,
that's
completing
true.
a day in just 10.5 hours. Its rapid rotation and
I
low
probably would have
density
noticed
means
that
it's
too.
really
If the
oblate or
bathtub was big enough
squished.
to
It's
float
10%
in,
wider through the equator than through the poles. That's really noticeable through a telescope. When we look at Saturn, we only see its cloud tops. These clouds are mostly ammonia ices with water clouds lower down. The atmosphere is banded like Jupiter's, but the pattern is much fainter, probably due to Saturn being farther from the sun and therefore colder, as well as the atmosphere being deeper than Jupiter's too. That's not to say Saturn doesn't have storms. Oval hurricanes pop up every now and again. And in 2010, a huge storm erupted in Saturn's northern hemisphere. It was discovered by an amateur astronomer, and Cassini spacecraft pictures showed it getting so big, it literally wrapped around the
Uranus
planet,
would also
reaching a
leave
length
a
of over
ring.
300,000 kilometers. Traces of it persisted for years. One of the most striking features on Saturn is a huge hexagonal vortex at its north pole. Vortices like this are common on
Wipe
planets.
your,
Earth and
you
Venus
gotta
have
wipe
them too.
Uranus
That well-defined
better,
six-sided
Shadow.
shape is pretty freaky, but it's actually a natural outcome of a spinning fluid, the air circulating in Saturn's atmosphere, which itself is in a spinning system, in this case, the planet itself. It's not that different than Earth's jet stream, but
Pretty
it's
cool
a
teacher
lot
here in
bigger,
class.
about 20,000 kilometers across, wider
It has a
than
faint
Earth.
ring.
And
It
right
does.
at its center, over Saturn's north pole,
It
is
does.
a ridiculously beautiful storm system
Saturn
about
does have
2,000
rings.
kilometers across.
Uranus
Wind speeds
has
there have
rings
been
too,
clocked
yeah.
at 500
Uranus
kilometers
has
per
rings.
hour. Saturn as a planet is of course an amazing place,
rings.
but come on.
It does.
When you think Saturn, you think rings. As
Good
well
deal
you
Friday?
should. Saturn's
Hey,
rings were seen by
got a
Galileo,
bidet?
but his telescope lacked the
always
resolution
wanted
to
to try
really
one of
figure
those.
out what they were. He thought
Squirt that
Saturn
water
might
in
be
my
three
bum.
objects in close proximity. Some decades later, the Dutch scientist Christian Huygens correctly interpreted their
Huygens.
appearance as a ring surrounding the
Christian
planet. They're not solid.
Huygens.
If they were, they'd get torn apart, since the inner edge would orbit the planet way faster than the outer edge. They're actually made of countless small chunks of very nearly pure water ice. Each particle orbits the planet independently. So I guess Saturn wins in the which planet has the most moons category. What really
little bit
gets me
sick.
about
So I
Saturn's
have to
rings is their
mute from time to
scale.
time
They're
to snort.
250,000 kilometers across. If you put Saturn between the Earth and Moon, the rings would cover 2/3 that distance. And yet, despite their size, they're incredibly thin. They average about 10 meters thick. And no, I did not misspeak. I meant 10 meters. 10 meters. That's amazing. That's thinner to scale than a sheet of paper. Way thinner. If you shrank Saturn down to the size of a piece of paper, that paper would be 10,000 times thicker than the rings. So yeah, Saturn's rings are flat. But why? Well, that's tied to their origin, though the specifics of how they came to be aren't exactly known. One idea is that they were originally an icy moon that got disrupted by a huge collision. The shattered moon particles would have spread around Saturn, and any of them that were on a tilted orbit would quickly collide with others, and in the end that would average out all their orbits to form a flattened ring. Or maybe there was once a large moon near Saturn that was big enough to be differentiated. That means the rocky bits fell to the moon's core while the ice stayed near the surface. As it plowed through the material around the proto-Saturn, the moon's icy layer got stripped off, forming the rings. And again, that would form a very flat disk. However they formed, collisions would quickly flatten the ring out. And remember, Saturn is oblate, so as the rings formed, they would have felt a gravitational tug from Saturn's equatorial bulge, centering them right over the planet's midline. Saturn has 3 main rings, give or take. In classic imaginative astronomer fashion, they're given the
caught
names
most of
A,
that.
B, and C, in order of their discovery. B is the broadest, roughly 26,000 kilometers wide. A is outside B, while the C ring is fainter and inside the B ring. When the rings were first observed, the A and B rings were thought to be one ring, but then the Italian astronomer Giovanni Domenico Cassini discovered a gap between them, and we now call that the Cassini division. It's about 5,000 kilometers across, but it's not empty. There are quite a few very narrow rings
5,000
inside it. The
kilometers is
gap is
almost
due to
nothing.
one of Saturn's moons, Mimas. If you're an ice particle in the Cassini division, you
Did you do
orbit
it, Flex?
Saturn
Did you make
twice
it?
for every one time
Did you make it,
Mimas
buddy? Are
goes
you there?
around.
Let me check.
This is called a resonance, and it means that the particles at that location get tugged repeatedly by the gravity
did
of
you make it?
Mimas,
Let me
which in essence
refresh.
yanks them out of their orbit. There are quite a few gaps in the rings caused by moons, In fact, there are
needs 3
hundreds
more.
of ringlets in the main rings. Even weirder,
Needs 3
the F
more.
ring is outside the A ring and is very narrow, just a few hundred kilometers across. It's kept that way by 2 moons, Prometheus and Pandora, orbiting just inside and outside the ring. They tug on the ring particles in such a way that keeps them confined to very strict orbits. If a particle wanders out, the moon's gravity drags it back in. As the moons and ring particles interact, they can also create weird rippling waves in the rings. And this is really cool. When small moons orbit Saturn
think
on
that happens to the
slightly
universe
inclined
itself,
orbits,
too?
it can create waves in the rings.
Or at least the
Tremendous
galaxy.
vertical excursions that can reach several kilometers high. Saturn is weird, and so are its moons. I already mentioned Mimas, an icy moon that carves out the Cassini division with its gravity. It also suffered a massive impact long ago that created a single huge crater, making it look somehow familiar. But Saturn has 2 moons specifically you should know about. The first is Titan, a monster satellite that's actually bigger than Mercury, not that much smaller than Mars, and second in moon size ranking only to Jupiter's moon Ganymede. Titan not only has a substantial atmosphere, the only moon to have one, but it's thicker than our air on Earth. I wouldn't suggest breathing it though.
No.
It's mostly nitrogen with a smattering of methane and hydrogen. It's
Not
also 180 below 0 Celsius there. Definitely don't stick your tongue on a flagpole on Titan. Titan's atmosphere
Unless you're
has a
Canadian.
thick layer of haze that prevents us from seeing the
Or
surface
Russian.
using visible light. But using infrared and radar though, the Cassini spacecraft,
Yeah,
which has
I
been
said the
orbiting
same
Saturn
term
since
too with
2004,
'cause
is able
they
to
were so
map the
small.
surface. It also deployed a
They were
probe named
orbital
Huygens
satellites.
to land on Titan's surface, the first time humanity had ever landed on an outer solar system moon. What they
Moons are
saw
moons,
was an
orbital
odd
satellites
world,
are orbital
Earth-like in
satellites.
some ways,
They're
and
2 different
very
things.
alien in many others.
Orbital
Titan
satellites
has
are tiny.
wind-sculpted dunes, but they're made of hydrocarbon
Not tiny,
grains,
but they
not
have a certain
sand. There are hints of
size that are
volcanoes
smaller
that spew liquid water
moons.
instead of lava. These are called cryovolcanoes, cold
That's why,
volcanoes.
Pluto
a
got
term I love.
downgraded
This,
quite
together
a
with
few years
measurements of
ago.
Titan's
It's
gravitational
no longer a
field,
planet.
have scientists thinking that Titan may have
My whole
an
childhood
underground
is
ocean
a lie.
of liquid water. Intriguingly, Titan also has
Ooh.
long winding channels indicating
Yeah.
flows of some kind of
That
liquid
looks
on
like
its
something
surface. But
flowing.
it can't be water. It's far too cold on the surface for that. So what kind of liquid could it be?
Nitrogen?
Well, Cassini also spotted quite a few flat regions near Titan's north and south poles. These have since been confirmed to be lakes of liquid methane, the first time
Methane.
any liquid has been seen on the surface of another world. The shorelines
Could
of the
use
lakes
that
appear to
for
change over time too,
power.
hinting very strongly that Titan has weather driven by methane as opposed to water here on Earth. Weather,
you need to do is
atmosphere,
get a
surface
sat-
liquids, and
yeah,
an abundance of organic
large asteroid
carbon-based
with a lot of water
molecules.
in it.
Could there be life on
So you have a
Titan?
water
The
source.
conditions there are
Methane's
interesting.
of,
We obviously don't know yet,
power
but it's an
source
exciting possibility.
combined with
And it's not
oxygen,
the only Saturnian moon scientists are
which is
looking
an
at for
asteroid,
signs
it's
of
water.
life. Enceladus is a smaller icy moon about 500 kilometers across, about the size of my home state of Colorado or the southern part of England. Enceladus is incredibly shiny, reflecting nearly all the light that hits it, a strong indicator it's covered in water ice. Parts of it are cratered, but other parts are very
It could be
smooth,
anything,
indicating
though.
some event resurfaced the moon. The
reflectivity
surface
is a
also
good
has an
sign.
extensive series of cracks in it, much like Jupiter's moon Europa. Scientists suspected cryovolcanism, and that was confirmed quite dramatically in
Cryovolcanism.
2005 when Cassini spotted
Air,
active geysers of water
Yeah.
spewing from the south pole of Enceladus. The water is erupting from a series of cracks nicknamed tiger stripes,
is
and is coming from deep under the surface.
frozen
Like
water?
Europa, Enceladus
Cryo
has
water.
an
Cool.
undersurface ocean kept liquid by Saturn's ferocious tides, which squeeze the moon as it orbits the planet. The plumes reach several hundred kilometers
Oh,
from the moon's surface,
the
and
squeezing
Cassini
creates
even
cracks?
flew directly through the plumes and detected organic molecules.
Ooh.
Could Enceladus be yet another harbor for life in the solar system? Again,
would be
no
crazy,
one
man.
knows.
We got so
but
many
I'd put it
places
in
to
the top
check.
3 places to look, including Europa and
Europa.
Titan. It's
I
weird,
like
isn't
Europa.
it? We've
I think
always
Europa's
looked
a
for
good choice.
planets where conditions were like
I
conditions
think we should
here
get
on
to the
Earth.
moon first.
But it turns out extremely cold moons may be the best places to seek out new life. Saturn has a huge retinue of other moons too, and they're all pretty weird. Iapetus is shaped like a walnut, with a tall ridge of mountains encircling its equator. No one's quite sure how that formed. Hyperion looks like a huge piece of styrofoam that's been hit repeatedly with a BB gun. And that's not a bad analogy, since it has such a low density, it's likely to be extremely porous, like a sponge. A lot of Saturn's moons orbit the planet backwards, retrograde, similar to several moons of Jupiter. These may be captured asteroids, or even Kuiper Belt objects, giant chunks of ice that we'll learn about very soon in a future episode. All in all, Saturn has over 60 moons we've discovered so far. I want to add a personal note. When you ask astronomers or astronauts what
Who?
got them
Is that
started,
a person?
what was the very first thing that happened to them to inspire them to do what they do? Overwhelmingly, they will tell you, I saw Saturn through a telescope. It's true. It's true for me. I remember my parents buying a cheap department store telescope when I was 5 or 6, setting it up
had
in the
all my hair
driveway
when
and
I was
aiming
5.
it at Saturn. I still remember seeing Saturn in the eyepiece, a perfect jewel. The ring's small, but vivid and sharp. It's hard to believe it's real when you see it, and even after all these years, it's my favorite target when I'm stargazing. I'll never get tired of watching people's faces when they see it for the first time. They gasp, their eyes get wide, their mouths drop open. It's honestly one of the greatest joys of life. Saturn is the crown jewel of the solar system. It's the best kind of astronomical object. Visually stunning, artistically gorgeous, and filled to overflowing with incredible science. Today you learn that Saturn is a gas giant and has a broad set of rings made of ice particles. Moons create gaps in the rings via their gravity.
Oh, here it comes! Here it comes. This good?
This episode of Crash Course is brought to you by Squarespace.
Uranus, 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 Uranus,
Uranus. What's this? Is that a game? Oh, it's cool. Oh, it's like a cool game.
There are 5 planets in our solar system
Uranus
you can see
is
without a
up.
telescope. Well, 6 if you include the one you're sitting on.
Uranus.
But there are 2 more big ones out there, orbiting the sun out in the cold depths of the outer solar system, Uranus and Neptune. They're a lot alike in many ways, but of course they have their individual quirks. Uranus was the first planet to be discovered, and by that I mean it wasn't known in ancient times. It took an astronomer with a telescope to find it. In 1781, William Herschel was mapping the skies through his telescope when he spotted a greenish object that was clearly a disk and not a dot like a star. He noted its position and moved on, but when he went to observe it again sometime later, he was astonished to discover it had moved. It was quickly determined to be a planet more distant from the sun than Saturn. In true brown-nosing style, he named it Georgium Sidus, or George's star, after the reigning king George III. Yeah, happily that name didn't stick. In keeping with the nomenclature of Roman gods, the new planet was dubbed Uranus. Interesting tidbit, it actually is visible to the unaided eye if you have very sharp eyesight and very dark skies. It's right on the thin hairy edge of visibility. What's funny is that several people had observed it before Herschel, but none had noticed its movement. Some even cataloged it on their maps as a star. The planet is massive, about 14.5 times the mass of Earth, but not terribly dense. This means its interior must be made of lightweight stuff. Scientific models of the planet based on physics and chemistry of the outer solar system indicate its interior is probably made up of 3 general layers. There's a small rocky core, smaller than Earth, surrounded by a very thick layer of materials like water, ammonia, and methane. This mantle makes up the bulk of the planet, in fact, and is dense, hot, and under a lot of pressure. In many ways, it's more like an ocean than anything else. However, somewhat confusingly, I'll admit, outer solar system planetary scientists refer to water, ammonia, and methane as ice. So even though it's not ice like we usually think of it here on Earth, we say that the mantle of Uranus is icy. To distinguish it from the gas giants Jupiter and Saturn, Uranus is called an ice giant. Speaking of ice, here's a really weird thing. Studies have shown that the pressure inside Uranus can break up methane molecules, squeezing the carbon in them so tightly that it actually forms diamonds. These would then fall down to the base of the mantle like sparkly hailstones, except it's dark. But still, down there in the depths of Uranus, there may even be an ocean of liquid diamonds, where solid ones float like diamondbergs. Not that we'll ever see that. When we observe the planet, we're only seeing the top of its atmosphere. Besides hydrogen and helium, the air there is about 2% methane. Methane is really good at absorbing red light, which means the light we see reflected from Uranus is mostly green and blue, making the planet look distinctly cyan or aquamarine. And it's pretty striking through a telescope. But in visible light, the planet looks almost featureless. It doesn't have that deep banding like Jupiter, or even the pale ones of Saturn. Though when you look in the infrared, some banding can be seen. There are clouds, but again, they're difficult to see in visible light. The clouds are made of methane, ammonia, and hydrogen sulfide. That last one is what makes rotten eggs smell so bad. I'd avoid breathing through your nose at Uranus. But then the atmosphere there is about negative 220 degrees Celsius, so that might be a better reason not to inhale. In late 2014, a bunch of storms popped up in Uranus's atmosphere, so big and bright they were easily visible from Earth. The storms may have dredged up very reflective methane ice from lower down in the atmosphere, and this time I do mean icy ice, which is why they were bright. The northern hemisphere of Uranus is approaching summertime, which may be why these storms formed. And that brings us to the weirdest thing about this planet. It's sideways. If you were above the Earth's North Pole looking down,
Just like
you'd
us.
see our planet spinning counterclockwise, west to east. The sun spins that way, and all the planets do as well, except
like us.
Venus and Uranus. While Venus is flipped all the way over, Uranus is tilted by about 98 degrees.
Yikes.
That means that in the summer, its axis is pointed almost directly at the sun, so seasons on Uranus are pretty extreme by outer solar system standards. Weird. No one knows why Uranus is tipped so much. An obvious thought is that it got whacked hard by an impact long ago. If it were a grazing collision by a big object, that could have pushed hard enough on the planet to tip it over. Unfortunately, Uranus is very far away and has only been visited by spacecraft once, Voyager 2 in 1986, and even then, it was a quick flyby. Uranus's weird tilt is just one of those many mysteries that astronomers are trying to solve with limited data. Uranus has a magnetic field, but it's truly odd. Its axis is tipped over by 50 degrees from the planet's spin axis, and it's way off center. The center of the magnetosphere is about 8,000 kilometers from the planet's center. It may be that the magnetic field is generated in the icy mantle, or that the core somehow interferes with the magnetic field, throwing it off.
Yeah.
Truthfully, no one really knows why.
Yeah, that's
Uranus
weird.
has more than
What?
24 moons, 5 big ones and a bunch of dinkier ones. Cool
fuck would that
fact,
happen?
the moons are named after characters in
Universe
Shakespeare
is
plays.
weird.
So we have Ariel, Umbriel, Titania, Oberon, and Miranda. Even Puck. Of them all, I think the most interesting one is Miranda. When Voyager 2 flew past, it revealed an icy world that looks like it was put together by Dr. Frankenstein. A patchwork of jumbled terrains all crammed together, crisscrossed by canyons
Yeah.
and grooves. It's possible
looks
a
like
giant
flowing
impact in its
something.
past actually disrupted the moon somewhat, and it settled back together into this weird mishmash. But the reason I like it so much is a feature called Verona Rupees. It's the tallest cliff in the solar system, 5 to 10 kilometers high. If you jumped off the top, it would take you 6 minutes to fall to the surface. That would be a fantastic ride. Like Jupiter and Saturn, Uranus has a ring system too. They were discovered by accident in 1997. Astronomers were observing Uranus pass directly in front of a star.
Impact.
They were hoping to use this to gather information about
Extreme-
the planet's atmosphere as starlight passed through it. But they saw
In
several
the hall.
dips in starlight before the main
You'll
event,
respect the
which
classroom
they realized
extreme.
were from rings around the planet. The rings are made of dark particles, probably ice and reddish organic
There will be
molecules.
tests.
There
You
are
have your
13 rings
pencil
known.
and
Most of
paper?
them are very faint.
Got your
and narrow.
notebook?
They may have been created by an impact, completely shattering a small moon orbiting Uranus. But as for now,
Some of this stuff,
ring
I
origins
like.
are
Most of the
unclear.
stuff I
And
know,
then,
but some of
finally,
it's like
we have
popping up. I'm
Neptune,
like, yeah,
the
that is
guardian
kind of
of
weird.
the solar system's nether regions. Neptune is an ice giant like Uranus and has a lot of similarities. Like its green brother, it probably has a rocky core surrounded by a thick icy mantle of water, ammonia, and methane. Above that is an atmosphere of hydrogen, helium, and methane. But there are differences too. Neptune is more massive than Uranus, 17 times Earth's mass versus just 14.5 for Uranus. Neptune is slightly smaller than Uranus, which means it's a lot denser. Also, while Uranus is teal, Neptune is a deep, rich azure. I like to call it the other blue planet, the
those
first
are
one
beautiful.
being, Earth. Through a telescope, Neptune's color is quite lovely. It has roughly the same amount of red light absorbing methane in its atmosphere as Uranus does, so its deeper blue hue is something of a mystery. That may have to do with its active atmosphere. Unlike blander Uranus, Neptune has clouds of methane, ammonia, and hydrogen sulfide lying in the skies at different depths, and white streaky clouds were seen during the Voyager 2 flyby in 1989. They looked whipped
beautiful.
by wind, and for good reason. Sustained
like a
wind
wind,
speeds
yep.
in Neptune's atmosphere have been clocked at over 2,000 kilometers per hour, faster than the speed of sound on Earth. It's thought that the low temperatures in the atmosphere reduce
Holy shit.
friction,
How
allowing
the
the
fuck
winds
does
to
that
gather
work?
to such amazing speeds. Voyager
What'd that
saw a
sound
huge
like?
storm marring Neptune's face, called, for some reason, the Great Dark Spot. A few
You
years
wouldn't hear
later,
it.
when
It would
Hubble
hit
was
you.
used to observe the planet, the
And then you
spot
would
was
hear it.
gone.
How the fuck does
But
that
others had appeared. They're probably vortices, cyclones, which allow us to see through the upper atmosphere and peer farther into Neptune's depths. Neptune has a magnetic field, and like Uranus,
sound is
it's
different than
offset
Neptune?
from the planet's center.
sense,
Perhaps that icy mantle is at work, somehow interfering with the generation of the magnetic fields in both planets. Neptune has rings too, but shocker, they're weird.
Yeah.
There are 3 main rings,
Neptune
2
has
narrow and 1 broad. They're clumpy and have bright stretches that make the rings look more like incomplete arcs. It's possible those arcs are being constrained by small moonlets near the rings. Speaking of which, Neptune has over a dozen known moons. Most are quite small,
gonna
but
say hi to
one,
the old lady for a
Triton,
bit.
is by far the largest. At 2,700 kilometers across, it's smaller than our own moon, but the rest of them are really dinky. Triton orbits around Neptune backwards, retrograde. As we'll learn in a future episode, There's a repository of giant ice balls out past Neptune, so Triton was probably one of those that got too close to Neptune and was captured by its gravity. Most of what we know about Triton came from a single flyby of Voyager 2 in 1989, and only about 40% of the surface was seen. But this quick glimpse revealed a weird little moon. The surface is covered in nitrogen ice, as well as water and carbon dioxide ice. It's really flat and has very few craters, meaning something resurfaced it in geologically recent times. Most likely this was from cryovolcanoes, cold volcanism. That is, volcanoes where water and ammonia take the place of lava there. Also, Triton has been seen to have active geysers of nitrogen erupting from its surface. They're probably due to warming from the sun, and they make Triton one of the few objects in the solar system seen to be geologically active. It also has a very thin atmosphere of nitrogen, probably due to evaporation from the surface. After all this, Neptune is special in another way, too. Neptune is faint and can only be seen telescopically. It was discovered in 1846, and it wasn't an accident. Over the decades, astronomers observed Uranus and found something weird. It wasn't where it was supposed to be. Over time, its predicted position was off from where it actually was. The French mathematician Urbain Le Verrier concluded that this was due to an unseen planet, and was able to use the mathematics of orbital mechanics to predict where the new planet would be. He sent a letter with the predicted position to the Berlin Observatory. Astronomer Johann Galle read the letter, went right out, and found the planet that very night. Neptune was within a degree of the predicted spot. Amazingly, another mathematician, Englishman John Couch Adams, had also worked on the math and had made a similar prediction. But Le Verrier beat him by 2 days. 2 days.
Not that kind of
such
streamer.
tight races are fame made in science. Interestingly, over time, Neptune seemed to wander from its predicted position as well. A ninth massive planet was predicted, leading to a grand search that resulted in the discovery of Pluto. But Pluto was far too small to affect Neptune. When Voyager passed both Uranus and Neptune, it found the masses of the planets were different than what had been measured from Earth. When the new masses were used in the orbital equations, Uranus and Neptune were right where they were supposed to be. It helps to have the right numbers to plug into your equations.
See, that's
Pluto, therefore, was found.
That's something that people have to remember too. All the knowledge that we think we have right now, a lot of it's probably either incomplete or just plain out wrong. So you have to keep the open mind when it comes to this stuff that, like, why is this? Why is that? That's weird. This, and then somebody explains it and be like, oh yeah, that makes sense. But then like down the road, we get better sensors and they look back at it and you're like, no, it was this. And you're like, oh, okay. We have to keep an open mind that that's not all of it's true. We're just trying to do our very best into what's most likely the truest way to do it. And then remember that those truth can be revised as we go further. Truth can be wrong, but we just got to keep trying. The best truth we can get.
By accident. That means Neptune is the only planet in the solar system found via math. See? Your algebra teacher was right. Someday, this stuff will be important. Today you learn that Uranus and Neptune are ice giants with small rocky cores, thick mantles of ammonia, water, and methane, and atmospheres that...
Ooh, I do love me some asteroids.
When
the
you
bringer
look at
of
a
water
diagram of the solar system,
onto this planet.
You'll see a big gap between Mars
Water
and
and
Jupiter.
gold
A few
and
centuries ago, that
most
gap
of the elements
bugged astronomers. They
that we
really
use
wanted
today
there to be a
for
planet
everyday
in
shit
there. On the first
brought
day
here
of
by
the 19th
asteroids.
century, January 1st, 1801, they got their wish. Kinda? Italian astronomer Giuseppe Piazzi found a point of light moving at just the right speed to be the desired planet. But it was just a dot, and too faint to physically be a terribly big object. He suspected it might be a comet, but follow-up observations showed it wasn't fuzzy. The object was given the name Ceres, but was it really a planet? Well...
Was it? Was it not? No.
Hopes were high that Ceres was the wished-for planet between Mars and Jupiter. But then something rather amazing happened. A little over a year later, in 1802, another one was found. Then in 1804, astronomers spotted a third one.
I think they're doing the Kuiper Belt?
In 1807.
Is
It was
this the
becoming
Kuiper
clear
Belt?
that a new class of solar system object had been discovered. Given that they were all just dots in the telescopes of the time, points of light like stars, They were given the name asteroids, which literally
The
means
asteroid belt.
star-like. By
Not
the end
the
of the
Kuiper
19th
belt, the
century,
asteroid
more than
belt. Yes,
450 had been found in total.
Ingalls.
The rate of discovery has accelerated over the
There it
years,
is,
and
the
now,
asteroid belt.
today, we know of hundreds
That's a
of
pretty good-
thousands. There are probably
Pretty
billions,
good visualization
yes,
of an asteroid
billions
belt.
of them, larger than 100 meters across in the solar system, and over 1 million larger than 1 kilometer in size. So what are we dealing with here? What are these asteroids?
There's a lot of
not
them.
really a hard and fast definition of what's an asteroid and what isn't. But generally speaking, it's a class of smaller bodies that are rocky or metallic that orbit the sun out to Jupiter. Objects past Jupiter have special designations that we'll get to in the next episode. Over the centuries, we've learned a lot about them by scrutinizing them with telescopes. Asteroids come in a few basic flavors. Most of them, about 3/4,
I'm sorry, guys, I
are
put this scene
carbonaceous,
together in
which means
haste.
they have lots of carbon in them.
I usually
About
take a
1/6
recording
are
of this stuff,
silicaceous,
but now it's
heavy on
just
the
a YouTube
silicon-based
scene I'm
materials,
pulling.
rock. The rest are lumped into one catch-all category, but are dominated by metallic
Yeah,
objects,
cheers.
literally loaded with iron, nickel, and other metals. So many of them orbit the sun between Mars and Jupiter that this region is now called the main belt. The main belt has structure. For example, there are very few asteroids about 425 million kilometers from the sun. An asteroid at that distance would have an orbital period of about 4 years, a simple fraction of Jupiter's 12-year period. Any asteroid there would feel a repeated tug from Jupiter's mighty gravity, pulling it out of that orbit. The resulting gap is called the Kirkwood Gap, and there are several such asteroid
that's a new one.
deserts, all with simple
Kirkwood
multiples of
Gap.
Jupiter's period. In this way, the
Kirkwood
main belt
Gap.
is like Saturn's rings, whose gaps are carved out by the gravity of the
Except
orbiting
these
moons.
Kirkwood
Another way to
gaps
group
in the
asteroids is by
asteroid
orbit.
belt.
Some have similar orbits
So
and
that's
may
how
have
they
formed
define
from a
them.
bigger parent asteroid that got disrupted by an impact. These groups are called families, and there are a few dozen known. For example, the Eunomia family has over 400 members and are silicaceous, rocky asteroids, and probably all formed from a parent body that was about 300 kilometers across. When you watch movies, they always show spaceships dodging and swooping through asteroid belts, trying to
Star
evade
Fox.
the bad guys. But in reality,
Hey.
our asteroid belt is mostly empty space. On average, decent-sized asteroids are millions of kilometers apart. So far that if you stood on an asteroid, odds are good you wouldn't even be able to see another one with your naked eye. And despite their huge numbers, they don't add up to much. If you took all the asteroids in the main
That's
belt
true.
and lumped them together, they'd be far smaller than our own moon. Ceres is the biggest
There's
at
just
about
so
900
many.
kilometers across. It's
And they're
round, nearly spherical
where they're-
due to its own gravity
placed,
crushing
like,
it into
so
a
far
ball.
out in
A
the
funny thing
universe
about
that
Ceres, as we
they're just
write and
dotted.
record this episode,
It's so much
being
space in
visited for the
between.
first time by a spacecraft named Dawn. That means everything I tell you about this asteroid is probably about to be obsolete. But we do know a few things. Ceres probably has a rocky core surrounded by a water ice mantle. The amount of water in it is staggering, probably more than all the fresh water on Earth. It may even be liquid under the surface, like the oceans of Enceladus and Europa. Early images by Dawn as it approached the asteroid show its surface is heavily cratered, and some craters are very bright. They may be exposing ice under the surface, or just fresher, brighter material. There are tantalizing observations of localized water vapor on the surface, which may be from sublimation, ice turning directly into a gas due to the sun's heat, or it might indicate cryovolcanoes. Dawn also visited Vesta.
I should have said that a while ago. I have a buddy, a fellow streamer, who's refused to turn off his stream until he reaches 300 followers. The counter, I think, says probably 15 minutes now, but you had to reset it every 45 hours. So he's 45 hours and 15 minutes. 45 hours and 15 minutes into his stream. I don't know, the poor guy must have napped here and there, but for the most part, he's been up. So we're going to give him, he only needs 3 more, you guys. 3 more. Let's give him a little extra volume for some love. He's a pleb. He's definitely a pleb.
It's only 10 at a time, bro. It's not very quick.
Let him go to bed, you guys. He only needs 3. Poor guy. 40-something hours. Oh, boy.
Oof. Took that
Last
hit
I
off.
checked, he only needed 3. Let me go recheck on him. I'm still up there. I'm a good guy. I got all my clippies. Oh my god, let me just keep this going though.
Which is the third
Sorry?
largest, but second most massive asteroid
listening.
known. Vesta
Trust
is
me.
round-ish. What's called an oblate
Refresh 'em.
spheroid flattened a bit like a ball someone's sitting on. The southern hemisphere got hammered by impacts long ago, leaving a huge basin there. Several other main belt asteroids have been visited by spacecraft, mostly via flybys. Lutetia, Gaspra, Steins, Matilda. Ida is another and was discovered to have a small moon orbiting it. In fact, a lot of asteroids have moons, or are actually binary, with two similar-sized bodies in orbit around each other. Cleopatra, a weird dog-bone-shaped rock, has 2 moons. You might think asteroids are just giant versions of rocks you might find in your garden, tough, solid, singular bodies. But it turns out that's not the case. A few years ago, scientists realized that asteroids have spent billions of years whacking into one another, sometimes in high-speed collisions, sometimes more slowly. Slower hits can disrupt the asteroid, crack it, but not necessarily be strong enough to actually disrupt it so that it breaks apart. Over time, enough hits like that can leave behind what's called a rubble pile. Individual rocks held together by their own gravity, like a bag of gravel, or a car window that's been cracked and still holds its overall shape. This became more clear when the Japanese Hayabusa spacecraft visited the asteroid Itokawa and saw what can only be described as a jumbled mess. The asteroid had no craters on it and was littered with rubble and debris. It was also very low density, a jumbled mess.
Its own gravity, like something hit it and blew it apart, but its own gravity pulled it back into this weirdy thing here. Like a little, like it got pulled together, and this rock just go, bloop, bloop. It probably like started off right here, something boing, 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 and that's where it stood forever. Because the gravity's so low, it just ended up being a mess. The asteroid had no craters on it and was littered with rubble and debris. It was also very low density, just what you'd expect from a loosely bound Uranus. It's weird to think of some asteroids as being not much more than free-floating bags of gravel. But the universe is under no obligation to adhere to our expectations. Interesting if
it's
it
full of
passed by
surprises,
Uranus,
and we need to keep our minds flexible.
or
So here's a
maybe
question.
being a part of
Why
it.
is there even a
Maybe
main
being
asteroid
part of
belt
Earth
at all?
some
The solar
point.
system
Who knows
formed
where it
from a
came
disk
from.
of material, and over
would be
time that
cool to know.
material started to clump into bigger and bigger pieces. As planets formed, they swept up and pulled in lots more stuff and grew large. Jupiter consumed a lot of the material around it, but not all, and left a lot of debris inside its orbit. Some of this clumped together to form middling-sized objects, probably smaller than the planets we have now, but big enough to undergo differentiation. Heavy stuff like metals sank to the middle, and lighter stuff formed a mantle and crust. Collisions broke almost all of them apart, though, and that's why we see asteroids with different compositions. Some are from the denser core, others from the lighter crust. There was probably a lot more material between Mars and Jupiter billions of years ago.
Yeah, it all got
but it either got
intermixed in a
eaten by
way.
Jupiter, or the planet's immense gravity altered the asteroid's orbits, flinging them away. This may be why Mars is so small, too. Jupiter robbed it of all of its food as it formed, while
It'd be an interesting thing to go out if we got out into the universe and started finding these little bits that got flung out, and we find them and be like, we can get their molecular composition. And if those molecular compositions are very unique to, say, this or that planet, that we would actually be able to trace that piece back to that planet, or even like find one from our own planet way out there and gauge back like even what time it left and what happened at that time. That's pretty cool stuff.
most asteroids live in the main belt, not all of them do. Some have orbits that cross that of Mars, taking them closer to the sun. We call those, wait for it, Mars-crossing asteroids. Some have orbits that take them even closer to the sun, crossing Earth's orbit. We call those Apollo asteroids. Gotcha! They're named after the asteroid Apollo, the first of its kind to be found. Some have orbits that are almost entirely inside Earth's orbit, called Aten asteroids. Aten and Apollo asteroids can get pretty close to Earth, so we call them near-Earth asteroids. Now, while they get close to us, that doesn't mean they'll hit us, because, for example, their orbits may be tilted, so their orbits and the orbit of the Earth don't actually ever physically cross. But some do have paths that literally intersect Earth's. That doesn't mean they'll hit us every pass either. After all, you can walk across a street without getting hit by a car. The problem comes when you try to occupy the same volume of space as a car at the same time. Astronomers, unsurprisingly, are very concerned about asteroids that can hit us. That's why we have surveys, observatories, scanning the skies, looking for them. This is a pretty important topic, and I'll go into it in more depth in a future episode. There's another category of asteroid that exists due to a quirk of gravity. When a planet orbits a star, there are points along the planet's orbit and near it in space where the gravitational forces are in balance. If you place an object
tiny
there,
little
it tends to stay there, like an egg in a cup. These are called Lagrange points. One of them is along the same orbit as the planet, but 60 degrees ahead. Another is 60 degrees behind. The first such asteroid found was orbiting 60 degrees ahead of Jupiter and was named Achilles, after the Greek hero in the Trojan War. As more were found, the naming convention stuck. Asteroids ahead of Jupiter were named after Greek figures in the Trojan War, and those behind Jupiter were named for Trojans, and now we just call them all Trojan asteroids. Trojan asteroids have been spotted for Jupiter, Mars, Uranus, Neptune, and even Earth. Earth's was found in 2010 using observations by an orbiting observatory called WISE, which scans the skies in infrared light where asteroids glow due to their own heat. 2010 TK7, as it's called, is about 300 meters across
there's
and
our little
800
Trojan
million kilometers
asteroid.
away, orbiting the sun ahead of Earth. There are also asteroids that have orbits that are very similar to Earth's, but are slightly elliptical and tilted with respect to ours. Because of this, they can stay relatively near the Earth in space, but don't really orbit us. Instead, they sometimes get closer and sometimes recede. It's pretty weird, but a natural outcome of orbital mechanics. Some people say these asteroids are moons of Earth, but it's better to say they're co-orbital with us. Only a few are known, the most famous being Cruithne, which can get as close as 12 or so million kilometers from us. Oh, one more thing. Originally, asteroids were named after female goddesses, Ceres, Vesta, Juno, and so on. But as hundreds more were found, and then thousands, we ran out of names. Eventually, astronomers who discovered asteroids were allowed to name them through a lengthy proposal and acceptance process governed by the International Astronomical Union. They also get a number assigned to them as well. A lot of astronomers have asteroids named after them, including astronomers who study asteroids, like my friend Amy Mainzer, who works on the WISE mission. Hers is 234750 Amy Mainzer, and Eleanor Helene, who discovered quite a few asteroids and comets. Hers is 3267 GLOW for her nickname. And this one? It's a 1 kilometer wide rock in the main belt and goes by the name 165347 Phil Plate.
Dentist appointment tomorrow.
Today you learned that asteroids are chunks of rock,
that was a good
metal, or both that were once part
We have a Trojan asteroid. I learned we have a Trojan asteroid. What did you learn today?
Hey, Phil Plate here, and this is Crash Course Astronomy. Since humans have been human, we've looked to the skies for portents of the future.
No,
the
we
sun,
got
the moon, the
ones that are
planets, the
erratic.
stars. They've all been used for prognostication.
Asteroids
and so
are
have
elite.
comets. A fuzzy blob moving slowly across the stars? How could soothsayers resist? But
the
now
difference
we know
between
a
an
lot
asteroid
more
and a
about
comet
comets.
is
They're
water,
beautiful,
I think, right?
fascinating, and can bring both life and death.
If it
upon
has
our little
water
world.
and creates a tail and it gets close to the sun, it's a comet. When it exhausts all its fuel and it just dead rockets, is an asteroid, right? I think that's how it goes. From my memory.
Comets have been seen in the sky since antiquity. Comet Halley, for example, is shown in the Bayeux Tapestry, which depicts the Norman invasion of the British Isles in the year 1066. It was seen by ancient Chinese and Greeks, too. In general, and like everything else in the sky, comets were considered omens or harbingers of human events. Sometimes they were good omens. William the Conqueror liked his chances in
why are the
1066
colors
after
these
seeing
guys?
one. And sometimes bad. That same comet didn't do so well for King Harold II. A comet bright enough to see with the naked eye shows up in the heavens every few years or so, and some can get spectacularly bright. In 2007, I saw Comet McNaught very near the sun in broad daylight. When you think of a comet, you probably picture a fuzzy blob and a long tail stretching away from it. Fair enough. But there's a bit more to them than that. Comets are in many ways similar to asteroids. They're roughly hewn chunks of stuff left over from the formation of the solar system. Unlike asteroids, which are mostly rock with a dash of ice and maybe metal, comets are a more...
If you guys were to go out on an average day and head on out to and away from any light source that you can get away from, the city, town, everything, just go out to like a field or a black area and turn off all lights, let your eyes adjust for a while, and just look up. You'll see comets. Spend an hour there, you might see a half a dozen. If it's more, if we're going through an asteroid or a comet field or whatever, you can see quite a bit more, of course. But on an average day, you will see them.
More balanced mixture of ice and rock. And by ice, I mean frozen water, but also frozen carbon dioxide, carbon monoxide,
not
methane,
these
ammonia,
big ones, but
things we
shooting
normally
stars.
think of as gases on Earth.
Every
and by
night.
rock, I do mean rocks, but also gravel and dust. In fact, astronomers sometimes call comets dirty snowballs, which is a bad term. It's that ice that makes comets, well,
there's less condensation
comets.
in the
When
air.
They're way out in deep space.
You can see more.
They're so cold that they're basically inert lumps of ice and rock. but many are on
Nighttime,
elliptical orbits
cold.
that take them from
It's
those
good.
sub-freezing depths into our neck of the woods where the sun can warm them. As they heat up, the ice turns directly into a gas, a process called sublimation. The gas then flows away from the comet, creating a cloud around it. This makes the comet look fuzzy, and actually in the past they've been called hairy stars. I like that term too, and in a sense we still use it. The solid part of the comet is called the nucleus,
That's
and
a
the
beautiful
gaseous
shot.
cloud around it is called the coma,
Look at that.
Latin for hair.
That's a real
In fact,
picture. That's
why we
not
call
artist
them
rendering or
comets.
anything.
As
That's an
the ice
actual picture of a
sublimates,
comet.
the bits of rock and gravel and dust embedded in it can be freed and leave the nucleus as well. This material is what forms the comet's tail. But how that happens depends on which material you're talking about. The gas and the dust from comets form two different tails. Gas molecules emitted by the comet get ionized by the sun's ultraviolet light. That means they lose electrons, becoming charged, and charged particles are highly susceptible to magnetic
Look at that
fields.
beautiful
The
arc.
solar wind is a
Just
stream
going
of
around the
charged
sun.
particles blown out by the sun and carries a magnetic field with it. As the wind hits the ionized gas
I
from the
want to see
comet,
that again,
it
actually.
picks up magnetic fields. The solar wind is a stream
Too
of
far.
gas molecules emitted by the
That's the comet down there. The sun is somewhere in this area. You can see it. The sun pushing off the comet, blowing it away as it goes around the sun. That's a beautiful shot.
comet get ionized by the sun's ultraviolet light. That means they lose electrons, becoming charged, and charged particles are highly susceptible to magnetic fields. The solar wind is a stream of charged particles blown out by the sun and carries a magnetic field with it. As the wind hits the ionized gas from the comet, it picks up those particles and carries them downstream, away from the sun. The solar wind is usually moving far, far faster than the comet, so this ion tail winds up pointing directly away from the sun. The dust, on the other hand, is influenced more by sunlight. Light from the sun exerts a small but inexorable pressure, and this pushes on the dust particles. The dust streams away, but because the pressure isn't as intense as the solar wind is on the gas tail, the dust tail blows away more lazily and tends to lag behind the comet in its orbit. That means the two tails usually point in two different directions. In some comets, like 1997's incredibly bright and gorgeous comet Hale-Bopp, this is pretty obvious. The dust tails look white or a teeny bit yellowish due to reflected sunlight, while the ion tail glows blue or green depending on the primary constituents of the gas. Carbon monoxide tends to
Yeah, that's one of these is solar wind and one of these is light. I think this is the light particles, and the solar wind is making the ion trail push back.
tails look
That's
white
cool.
or a teeny bit yellowish due to reflected sunlight, while the ion tail glows blue or green depending on the primary constituents of
That's
the gas.
beautiful.
Carbon monoxide tends to emit blue light, while carbon molecules glow a ghostly green. A comet's tail can stretch for tens of millions of kilometers, but despite their length, tails are incredibly low density, as low as a few hundred atoms per cubic centimeter. The air you breathe is 1,000,000 billion times denser. In 1910, Earth passed through the tail of Comet Halley. This caused some public fear because cyanogen, a deadly gas, had been detected in the tail. But of course, nothing happened. It turns out getting a gazillionth of the toxic dose isn't that big of a problem. Broadly speaking, comets are classified by their orbits. If they have orbital periods less than 200 years, they're called short-period comets. These tend to orbit the sun in the same plane as the planets and go around the sun in the same direction as well. From Earth, we see them sticking near the ecliptic, the line across the sky that marks the annual path of the sun. Comets
And
that
then
take
some
longer
comets
than
go
2
up
centuries to
and
go
down,
around the sun
but-
are called long-term comets and have orbits that are tilted every which way. That means they can appear anywhere in the sky. But this raises an
Those
interesting
are the
point.
dangerous ones.
Comets go away. Every time they get near the sun and start outgassing, they lose mass. Over time, they get smaller. Eventually, they
become a
should
comet.
evaporate.
Or, sorry, an
Some
asteroid.
do this all at once because they dive into the sun, skimming our star's surface. We call those sun divers or sun grazers.
Beautiful.
Many of those may actually be pieces from a bigger comet that broke up in space nearly 1,000 years ago. But besides those, we know of some comets with orbits that can be short, some with periods of just a few years. Even a century is like a single flap of a mosquito's wing compared to the lifetime of the solar system. How can comets be billions of years old if their orbits bring them close to the sun all all the time.
They get
Astronomers wondered
disturbed
about this
from the
very
Oort
thing.
cloud.
Over the years, they came up with an idea. Maybe out past Neptune, there's a repository of comets,
The Oort
chunks
cloud.
of dirty ice, millions of them, billions, orbiting the sun where it's perpetually cold. They could have orbits that last for millennia or more, but then something tweaks them, makes them fall toward the sun. In fact, there may be two such regions, since we
Some
have
sort
both
of
short period
gravitational
and
destruction
long-term
pushes them
comets.
in
Turns
or
out,
out.
this idea is
The
correct.
ones that go
We now
in
know
come
enough
towards the
about
sun. The
those
ones that
distant
go out
regions of
are
the solar
out
system
in
that
interstellar
they deserve
space.
their own episode. So we'll dive into that topic later. So, what do comets look like up close? Like, really close. Studying them from Earth is hard. The coma obscures the nucleus,
Ooh, that's
making
a
it
bad
nearly
one.
impossible to see it directly. From Earth.
On
If
purpose,
you
I
instead
hope.
send your telescope to a comet, things change. We first
hold
did
on.
that in the 1980s, the last time Comet Halley came
1980s?
around. Several
Look at the guys
nations
here.
sent spacecraft to fly past the comet, and the Soviet mission Vega 1 was the first to successfully get pictures of the nucleus. The
That's the
low-resolution
first one.
images revealed a dark lump highlighted with two bright spots, later determined to be
first
jets of
pictures.
gas streaming away. These images were used to better determine the position of the nucleus, and a few days later, the European probe Giotto zipped past the nucleus at an incredibly close distance of just 600 kilometers. Those pictures were more detailed and showed us a flying mountain in a regular
Looks like
chunk
it's
15 by
already
8
spraying
kilometers in size. And it was
comet?
dark, reflecting only 4% of the light that hit it. That makes the nucleus as black as asphalt. You might think that all that ice would be shiny, but it's not that simple. Most of Halley's nucleus is covered in thick dust laced with darker molecules, with only a few spots emitting gas. Most likely,
Its
there are
own
deposits
dust
of
gets
ice under the surface,
come back
and
to
only
it.
some of them receive enough heat from the sun to
It pushes
sublimate
out
and
its
blow
own
out
dirt,
gas.
and
This
the
has
dirt
been
comes
seen with
back
other
in and
comets as well.
gets
The
black on
gas
the
is
top
emitted
and
from
starts coming
specific
up top.
spots
But
on
when
the
it
comet,
heats up,
venting out from
this is what
cracks in the
happens.
crusty surface. The surfaces of comets must be inhomogeneous, different in different places.
Inhomogeneous,
That
oh
fact
boy.
was brought home magnificently in 2014 by another European mission, Rosetta. It went into orbit around the comet 67P Churyumov-Gerasimenko and found it to be a bizarre little object. Measuring about 4 kilometers end to end, 67P
sure
has
what you're
two
talking about
lobes
for
connected
screen.
by a narrow neck, looking very much like a cosmic rubber ducky. The surface is completely devoid of craters. Clearly, the surface is very young. Images show jets of gas emitted from very specific places on the surface, and there are wide circular pits here and there, which may be gas vents, growing wider over time as the ice below is depleted. Surprisingly, the surface is fairly tough and hard, when some scientists
That makes
expected
sense,
it to
yeah.
be fluffier. The comet has a very low density, similar to rubble pile asteroids, so it was expected that the surface would be soft. Rosetta sent
No,
down a lander named Philae to set down on the surface,
when it
using
heats up,
harpoons to anchor
any
itself.
water
But
would
instead,
push
the
its
lander
way out.
bounced, unable to penetrate the tougher than expected material. One idea to explain this is that the ice is porous and fluffier inside the comet, but as it nears the sun, the ice at the surface warms and changes its structure, forming that harder crust. As for the double lobe thing, well, that's a bit baffling. We see some asteroids shaped that way as well. It's possible 67P used to be two separate comets that had a low-speed collision and stuck together. Or maybe it used to be one big lump, but over the eons, the ice in the middle sublimated more, leaving behind the two lobes. Rosetta is the first time in human history we've had a probe orbiting a comet, studying it up close and long term. We're still learning, still figuring this stuff out. Incidentally, I mentioned earlier that A, comets have lots of ice in them, and 2, they also get really close to Earth sometimes. In fact, they can hit us. Now, not to get all technical and scientific-y, but that is what we would call bad, as we'll discuss in an upcoming episode. But billions of years ago, lots of comets hit the Earth not long after our planet formed. Together with asteroids, many of which are also rich in water ice, they may have brought a significant amount of water to Earth. Scientists are still wrestling over the details of
That's
this,
what
and
I
it may
think
be a
happened
while
too.
before the actual numbers are nailed
I think
down.
asteroids
But
brought
it's
a
an
lot of that
intriguing
gold
thought. Even more
and
interesting,
minerals.
in 2004, NASA's Stardust
heavy
space probe
ones.
physically passed through the coma of comet Wild 2, collecting samples that were returned to Earth. Careful analysis of the material found the presence of organic, carbon-based molecules in them. And not just any random molecules, but complex ones, including amino acids. These are the building blocks of all life on Earth. Amino acids are what our bodies use to create proteins. It's possible that the ingredients of
panspermia?
life on Earth didn't start here, but instead were brought to our planet
I like how
from
they
comet
put the
impacts.
planet
Or at
upside
least
down.
there was a mix of the two.
Or is it?
If that's the case, then in a sense, all life on Earth is part alien. How about that? But what gets
That'd be
me
cool
are
theory.
the philosophical ramifications of this. When we look into space, when we examine our celestial neighbors, when we send probes to comets and survey what we find, We're looking at our own origins. Comets are like time machines, allowing us to investigate our past 4 billion years back, hinting at the secrets of the origin of life itself. And you thought astronomy was just lying out in a field and looking up. Well, it is, but if you let it, it's also a whole lot more. Today you learn that comets are chunks of ice and
A lot of
rock
people
that
think
orbit
that
the sun.
comets are the
When they
thing
get
that
near the
delivers life
sun, the ice
to other
turns into a
planets.
gas, forming the long tail.
Some planets that
and also
get hit
releases
and
dust that
destroyed by
forms
a
a
big
different tail.
catastrophe.
We visited comets up close
A lot
and
of
found them
that
to be
gets
lumpy,
thrown out into
with vents in the
space and
surface that
eventually
release the
lands on
gas
another
as ice
planet.
sublimates. Eons ago, comets and
Creates new
asteroids
life,
may have brought a lot
panspermia.
of water to Earth.
Oort cloud, hey! That's what I'll talk about earlier.
Well,
where those
look where
comets
we
come
are
from.
now. With our backs to the sun and the planets, asteroids, and comets behind us, we face deep space. There's nothing between
Now we're
us and the
talking. We're
stars so
starting to get into the
terribly,
good stuff,
terribly
baby.
far
Hell
away.
yeah.
Or is there? The empty space past Neptune isn't exactly empty. In episode 21, I mentioned that comets come in two varieties. Those with orbital periods of less than 200 years, which tend to orbit the sun in the same plane as the planets, and those with longer periods, which have orbits tilted every which way. This is something of a problem. Comets lose material when they get near the sun. Over the course of millions of years, these comets should evaporate. And yet here we are, 4.56 billion years after the solar system's birth, and comets still appear in our skies. So where are they coming from? To see, we'll have to turn the clock back a wee
coming
bit,
from the Oort
like
cloud.
4.5 billion years. Behold, our forming solar system, coalescing out of a flat disk of material around the sun. The inner planets were warmer, smaller, and rocky, while the outer planets were in a region that was colder and grew huge. Out there in the chillier part of the solar system, water came in the form of ice mixed in with dust and other stuff. These bits would collide and stick together, growing bigger. Some grew to hundreds of kilometers across. But there was a problem. Those outer planets. They had a lot of gravity, and any chunk of ice getting too close would either fall into the planet and get assimilated, or get kicked into a different orbit. It could then plunge in toward the sun or get flung out into deep space. Trillions upon trillions of such ice balls got tossed around by the planets. Even though they were small compared to the planets, they did have a little bit of mass and gravity. So every time the planet pulled hard on them, they also pulled a little bit on the planets too. It wasn't much per chunk, but after trillions of events, this adds up. A current model of what happened, called the Nice model after the city in France where it was proposed, says that the overall effect of all these encounters was that Saturn, Uranus, and Neptune slowly moved outward from the sun, while Jupiter moved inward. Neptune would have had the biggest effect on these ice balls, because it bordered the biggest volume of space where they lived. As Neptune migrated outward, close encounters with these chunks of ice flung lots of them into crazy orbits, highly elliptical and tilted with respect to the planets. Repeated, more distant encounters tended to more slowly increase the sizes of the orbits of the ice balls too. We think that this shuffling around of the outer planets is what caused the late heavy bombardment, the intense shower of objects that came screaming down from the outer solar system, scarring planets and moons a few 100 million years after the planets themselves formed. It's not known for sure, but all the pieces fit together really well. In the end, today, there are three rather distinct populations of these objects. One is a region shaped like a puffy disk or a donut, aligned with the plane of the planets. Icy objects there have stable orbits, unaffected by Neptune. We call this the Kuiper Belt, named after the Dutch astronomer Gerard Kuiper, one of many who initially speculated about the existence of this region. The Kuiper Belt starts more or less just outside Neptune's orbit, extending from about 4.5 to 7.5 billion kilometers from the sun. The second region is called the Scattered Disk. This is composed of the ice balls sent by Neptune into those weird, highly tilted orbits. This overlaps the Kuiper Belt on its inner edge and extends out to perhaps 150 billion kilometers from the sun. That's 25 times farther out than Neptune. Finally,
the way I think about the formation of the Earth and the elements within it, the very early stages of the Earth, it was completely molten. So anything that was on there, anything of any weight that was on there, was pulled to the center. If you think of like if you're smelting gold or something, the gold sinks to the bottom and the slag stays on top. So that's what happened to the Earth. Once the crust eventually did form and cool, it was slag. Well, all the good stuff was down in the middle. There was nothing, crap. So then, you know, asteroids came in with little bits of gold and bits of water and this and that and the other thing, and a lot of it evaporated it into the atmosphere. Some of it hit the ground, and whatever became liquid water, I would think most of it kind of evaporated, and that would cause heavy mist in the atmosphere. Once the planet cooled enough for it to condense, it just 70% of the world's oceans. Yeesh, that's a lot. Same for gold as well. A little bit of gold, a little bit of silver, a little bit of whatever. All the comets. There was none of that on the Earth when it was formed. It was all brought here by comets. At least that's my belief. There's theories.
Outside those two zones, there's a spherical cloud of icy objects, which starts roughly 300 billion kilometers out, 70 times farther out than Neptune, a staggering 2,000 times the distance of the Earth from the Sun. And that's just where it starts. It extends way farther out than that, perhaps as much as a light year, 10 trillion kilometers. This is called the Oort cloud, after astronomer Jan Oort, who first proposed it. The Oort cloud is the origin of long-period comets. Since they orbit the Sun on a sphere with no preferred orientation, they come in toward the inner solar system from random directions in the sky. Many newly discovered comets fall into this category. Their orbits can be extremely long. They start their fall from so far away, they swing around the Sun at nearly escape velocity, and their orbits are close to being parabolic. The scattered disk is the source of short-period comets. They can still be affected by Neptune, which can alter their orbits to drop them down closer in. They can orbit the Sun on paths between Jupiter and Neptune, meaning eventually they'll have a close encounter with Jupiter. This can send them in closer to the Sun, and they become short-period
Just
comets.
a little nudge.
That's how comets
That's
are
all it
made.
needs.
So how do we know all this? Well, until 1930, it was pretty much just conjecture. But then an American astronomer, Clyde Tombaugh, discovered the first Kuiper Belt object, Pluto. Pluto orbits the Sun on an elliptical, mildly tilted path. Its orbit actually brings it closer to the Sun than Neptune. So how come it never collides with the larger planet? Pluto's orbit crosses Neptune's, more or less. Because the orbit is tilted, they never actually physically cross. When Pluto is at perihelion, closest to the Sun, it's well above the plane of the solar system, far from Neptune's orbit. Not only that, but Pluto orbits the Sun twice for every 3 times Neptune does. Because of this, whenever Pluto is closest to the Sun, Neptune is always 90 degrees away in its orbit.
How many people are mad about that, and how many people understand what they did there by downgrading Pluto from a planet to an asteroid or a planetoid? Planetoid. Sorry. Comments. Thoughts.
That's many billions of kilometers distant, way too far to affect Pluto. This is mostly coincidence. We've seen how orbital resonances can be forced by tides and by gravity, but in this case it's due to attrition. Once upon a time, billions of years ago, there were probably a lot of objects out by Pluto with orbits of all different shapes and tilts, but the ones that got too close to Neptune got gravitationally tweaked into
extreme. I meant to say something about the cities under oceans. I believe that's true, but that wasn't because of comets. This was a different era. I believe the cities under oceans are because of global warming, not because of. I think the world is coming out of an ice age. It has been for a long time, so it's naturally getting warmer. Anyways, us throwing all that crap in the atmosphere isn't helping. It's probably gonna bite us in the ass in about 150 years, or bite somebody in the ass. It won't be me. The underwater is because the oceans have risen many feet in the last, even 8,000-9,000 years. Not long at all. They're still rising today, and it's not just because of us. The world is naturally going through a warming cycle, but we're just not helping. We're really not helping. We got to slow down.
into different orbits, turning them into comets or flinging them deeper into space. The only ones that could survive just happen to have orbits with that 3-2 or 2-1 resonance with Neptune, keeping them far from Neptune's influence. Today, those are the only kinds of objects we see with orbits near Neptune. We call these objects plutinos. They're not really a separate class of object. They're still Kuiper Belt objects, but a fun and interesting subset of them. Once Pluto was found, astronomers wondered if it might herald a new class of icy objects past Neptune. However, it took more than 6 decades to find the next one. 1992 QB1 was discovered in 1992, and that opened a sort of gold rush of Kuiper Belt discoveries. We now know of more than 1,000 Kuiper Belt objects. One, called Eris, is very close to Pluto's size and is more massive. It's probably
I do remember
rockier
hearing
than
about it
icy
not long
Pluto.
afterwards.
Pluto is an interesting object. A moon was discovered in 1978. Named Charon, it's actually about 1/8 the mass of Pluto itself. While Charon orbits Pluto, the moon has enough mass that it can be said that Pluto noticeably orbits Charon too. In reality, both circle around their mutual center of mass, located between the two. 4 more moons were discovered in Hubble images of Pluto in 2005 and 2012. There may be more. Pluto is so small and distant that we don't know much about it. But that may be about to change. And now I have to admit to being in a tough spot. As I record this episode of Crash Course, a space probe called New Horizons is heading toward Pluto. It'll fly by the tiny world in July 2015. There's no doubt our view of Pluto will change. There may be more moons discovered. We'll see surface features for the first time. So I think the best thing to do is leave little Pluto alone for now. But there is a point yet. So I think the more. But right now, I can't tell you about any of that because we don't know yet. So I think the best thing to do is leave little Pluto alone. But there is a point I want to bring up. Pluto was found in 1930, long before any other Kuiper Belt object, because it's much brighter than any other. When it was discovered, it was thought to be about the size of Earth. But over the years, better observations showed it to be far smaller than first thought. In fact, it's smaller than Earth's moon. Its surface is unusually reflective, shiny, making it look much bigger than it seems. Most other Kuiper Belt denizens are far less reflective and so are far fainter. If Pluto is king of the Kuiper Belt objects, it has a lot of loyal subjects. We think the Kuiper Belt may have 100,000 objects in it larger than 100 kilometers wide. If that sounds like a lot, get this. The Oort cloud surrounding the solar system may have trillions of icy bodies in it. Trillions! While we know lots of Kuiper Belt objects, we don't know of any Oort cloud objects for sure. 2 very interesting bodies have been found, Sedna and VP-113. Sedna's orbit takes it an incredible 140 billion kilometers from the Sun, while VP-113 gets about half that far out. Both are on very elliptical orbits. Neither, however, gets close to Neptune, so it's not at all clear how they got where they are. They may be Oort cloud objects that were disturbed by passing stars long ago, dropping them closer into the Sun. But no one knows yet. Speaking of which, we can calculate how many Oort cloud objects there should be left over from the formation of the solar system, and it's about 6 billion. However, calculating how many there are using long-period comet observations, you wind up getting about 400 billion. That's a big discrepancy.
Holy crap.
Now get this.
It is.
One idea to solve this discrepancy is that the Sun has stolen comets from other stars. Seriously, comets should form wherever stars do, and sometimes the Sun passes near other stars.
That's a lot.
When we see a long-period comet gracing our skies, could we be seeing an object from an alien solar system? Maybe.
I could
there is
understand that,
another
but
explanation, but it's highly speculative. Perhaps there's another planet in the solar system, well beyond Neptune. It's
disturbing
possible.
them.
Some very preliminary studies have shown that some long-period comets aren't coming in randomly, but instead have their orbits aligned in a way you might expect if a very distant planet perturbed them. There are a handful of Kuiper Belt objects aligned in a similar way. NASA's WISE Observatory scanned the skies in infrared and would have seen anything as big as Jupiter or Saturn out to tremendous distances, so any hypothetical planet would have to be smaller and very distant, probably tens of billions of kilometers out.
Be interesting
We've
if
seen
it was a
other
tiny
stars
black
with
hole.
planets this far out, so it's physically possible. But is there really one there? We can't say either way, yes or no. At least not yet.
Planet
This region of the solar system is
Black hole
seriously
one.
underexplored. It's distant, difficult to reach, and above all else, extremely huge and numbingly empty. You could hide a whole planet out there, and it would be pretty hard to find. The point? There's still lots of solar system left to explore. We've barely dipped our toes into these dark, frigid waters. Today you learned that past Neptune are vast reservoirs of icy bodies that can become comets if they get poked into the inner solar system.
What do we got next?
The Kuiper Belt is a donut.
Meteors again? Well, the ones that fall. We had asteroids, comets, now we're at the
astronomy.
meteors.
You may have noticed, but there's one really frustrating aspect of it. Everything we study is really far away. Nearly everything we understand about the universe comes from light emitted or reflected by objects. It'd be nice if we could get actual samples from them, physical specimens we could examine in the lab. Well, sometimes the universe can be accommodating and allows us to hold it in our hands. Cambot, can we get this up on still story?
Oh, he has some. I would love a fragment. Oh my god, what I would do for a comet fragment. Oh, please send me one, someone.
If you go outside on a clear, dark, moonless night, and you really should, chances are pretty good that within a few minutes you'll see a shooting star. It'll zip across the sky, a fiery dot leaving a long glowing trail behind it. They're one of the most exciting and fun things you'll see when you look up, and they always get a gasp and a squeal of delight from someone who's stargazing. What you're actually seeing is a tiny bit of interplanetary debris.
Has anybody ever had this happen to them before? One time I was driving down the street, my wife was driving down the highway. It was my turn to get some rest. We were on a long trip and I was getting comfortable and I just happened to look back and I saw a little twinkle in the sky, just a little twinkle. And that twinkle, instead of a shooting star that you would kind of figure to go like this across the screen, like across the sky, this one started like right in front of me and then came this way. Came toward me. So I was like, what the fuck is this thing? And all this happened within a moment of like a quarter of a second. And I didn't know what was going on, but apparently this thing was coming at me. And it wasn't even that far off. I watched it come in and it exploded in the air about 50, 60 feet off the ground. I watched it break into pieces and explode into the air. I don't know how far from me, but it was close enough that I could see it explode and watch the pieces break off and come down to earth. So that was a little bit of a scary moment. I don't know if anybody else has had that happen before. It was cool, a little scary, but really cool.
Rock, ice, or metal ramming through the Earth's atmosphere, heated to incandescence. Most are faint, but some can be astonishingly bright. I saw one once that left an afterimage on my eye. Obviously, shooting stars aren't really stars. So what do we call them? Sometimes it seems like astronomers use different names for objects to keep things as confusing as possible. But really, we do that to separate out different things. In this case, the actual bit of solid stuff coming from space is called a meteoroid. The phenomenon of the meteoroid getting hot and blazing across the sky is called a meteor. And finally, if it hits the ground, we call it a meteorite. I think the second best way to tick off an astronomer is to mix up meteor and meteorite. Sometimes astronomers can be pretty pedantic about such things. Oh, the best way to tick off an astronomer? Ask them, hey, what's your sign? Amazingly, a typical meteor that you'll see is due to a meteoroid that's tiny, probably smaller than a grain of sand. How can that be? It's because they're hauling mass. You heard me. The meteoroid is orbiting the sun, probably at speeds of a few dozen kilometers per second. As it approaches the Earth, our planet's gravity accelerates it an additional 11 kilometers per second, Earth's escape velocity. And when it enters our atmosphere, it's moving incredibly fast, up to 70 kilometers per second or more. The energy of motion is called kinetic energy. If you want to get something moving, you have to give it energy. And if you want it to stop, you have to take that energy away. This kinetic energy depends on the mass of the object and how fast it's moving. In fact, it depends on the square of the velocity. Double its speed and it'll have 4 times the kinetic energy. Meteoroids may usually be small, but they're screaming fast and have a huge amount of kinetic energy. As they hit our atmosphere, they slow from their ridiculous orbital speed to nearly a standstill. And all that energy has to go somewhere. It gets converted into light and heat, and that's what we see as a meteor. A big misconception about meteors is that they get hot due to friction with air. Actually, a far bigger contributor to their heat is compression. One of the most basic laws of physics is that when you compress a gas, it heats up. And a meteoroid coming in at hypersonic speeds compresses the air in front of it a lot, heating it hugely. The gas can reach temperatures of thousands of degrees Celsius for a few seconds. The air radiates away this heat, in turn heating up the meteoroid. The material on the surface vaporizes and blows away, a process called ablation. That ablated material leaves a glowing trail behind the meteor, which we call a train. Sometimes it can glow for several minutes, getting twisted up in high-altitude winds,
That's cool.
leaving
I've never
behind an
seen that.
eerie, ghost-like, persistent train. This all happens
I've
high
seen a
above
lot
your
of those
head,
little
about
ones.
90 to 100 kilometers above the ground.
It's not
Typically,
hard to
from
see
any one
those. You
location,
can go out at
you
any
can see a
any
few
time of night
meteors
and
per
go
hour.
check it
It may
out.
not seem like
Colder
much,
the better.
but when you add them up all over the planet, you find the Earth is getting pelted to the tune of about 100 tons of material a day. But again, most of these meteoroids are teeny tiny. Those random meteors are called sporadic meteors. They tend to be rocky in composition and generally come from asteroids. If two asteroids smack into each other, the collision can eject little bits of material that then orbit the sun on their own. If their orbit crosses the Earth, then you have a potential meteor. It may take a few million years, but at some point, the Earth and the meteoroid are at the same place at the same time, and boom. But sometimes, meteoroids travel in packs. When that happens, we can get meteor showers, many dozens or even hundreds of meteors per hour. With one exception, those don't come from asteroids. They come from comets. When a comet orbits the sun, the ice on it turns to gas, dislodging dust and gravel mixed in. This material leaves the comet and tends to stay more or less in the same orbit as the comet itself. Over time, that material gets scattered all along the orbit, creating a puffy ribbon of tiny pieces of space debris around the sun. When the Earth plows through that cloud of debris, we get a meteor shower. From our viewpoint on Earth, we see meteors shooting across the sky, apparently radiating away from a single point. That's a perspective effect. It's like driving through a tunnel and seeing the tiles on the wall and ceiling flying past you, all apparently coming from a point ahead of you. The point on the sky where the meteors come from is called the radiant, and the shower is named after the constellation the radiant's in. So we have the Perseid meteor shower, the Leonids, the Camelopardalis, or the Camelopardalids. And since the Earth hits a specific comet stream around the same time every year, the showers are annual. The Perseids are in August and the Leonids in November. Watching a meteor shower is easy. Just go outside and look up. Generally, they're better after local midnight. The Earth plows into the meteoroids, so facing the direction of Earth's orbital motion means more meteors, just like you get more raindrops on the front windshield of your car than on the back when you're driving through a storm. After local midnight, you're on the part of the Earth facing into the orbit, so you see more meteors. By the way, if you happen to be on the International Space Station, you have to look down to see a meteor. In 2011, astronaut Ron Garan photographed a Perseid burning up below him. But don't worry, the odds of the space station getting hit are extremely low. Space is big. Oh, and that one exception I mentioned before? That's the annual Geminid shower, which occurs in December. That comes from the asteroid 3200 Phaethon, which is on an orbit that takes it very close to the sun. It's possible it gets so hot that the rock vaporizes, making it act like a comet. The vast majority of meteoroids are small and tend to burn up in our atmosphere, but they can be bigger. A bolide, or fireball, is an extremely bright meteor, and those can be about the size of a grapefruit. Those happen pretty often somewhere over the Earth. I've seen a few myself. Very rarely, an incoming meteoroid will survive all the way to the ground and become a meteorite. Sometimes the immense pressure of ramming Earth's air causes the incoming meteoroid to crumble or even explode, raining down dozens or...
This is what I saw. That one night I was on the road looking back. It happened in a quarter of a second, but instead of seeing it like this, I saw it coming at me, like at me, not across. Not like, hey, look at that. No, it was like, you boom, and it exploded before it hit me. Honestly, above the ground, it was cool as fuck, but scary. This is what I saw, and I could even see the little sparks coming off the side as it come at me. There was like little fly off sparks when it was coming at me. Oh shit, it was fuck. Yeah. That was it.
Hundreds of smaller pieces. Typically, they slow rapidly after their blaze of glory and simply fall the rest of the way to the ground. The air up there is cold, and their interiors are cold from being in space so long. So, despite what you might think, meteorites don't cause fires when they hit the ground. In fact, they can be quite chilly. Meteorites are classified into three broad categories: stony, which are mostly rock; iron, which are mostly metal; and stony iron, which are a mixture of the two. The majority of meteorites we find are stony. The stony meteorites are themselves subdivided into two kinds: chondrites and achondrites. Chondrites contain chondrules, small grains of minerals. These are very primitive and are thought to have condensed out of the original disk of material that formed the solar system. Their ages can be found by looking at ratios of elements in them formed from radioactive decay. The oldest known meteorite formed 4.568 billion years ago, before the Earth itself formed. Achondrites don't have chondrules in them, Most likely they came from a bigger asteroid, one that was once molten all the way through, mixing the minerals. A big collision disrupted the parent.
I had read Extreme somewhere. I'm sure it was at a party. People were just minding their own business, going about their party, and a gentleman just slumped over and died. And they didn't understand what it was. And when they checked it out in the pool beside the party, a little meteorite, and apparently it went right through him and killed him. It's happened before. It has happened.
Body, creating the achondritic meteoroids. Iron meteorites most likely come from the center of a large asteroid, one big enough that metals fell to the center via gravity. Again, a big impact blew the asteroid up, scattering its material around the asteroid belt, and with some on orbits that eventually intersected Earth. Stony irons are the rarest. Some have green or orange crystals of a mineral called olivine embedded in a web of metal. Called palacites, they may be the most beautiful of all meteorites. I actually collect meteorites. It's fun, but can be a somewhat pricey hobby. If you're interested, make sure you get them from a licensed dealer. We have links to some in the doobly-doo. Of course, on occasion, the meteoroid coming in can be a tad bigger. And when that happens, well,
just a little bitty one. Just a little one.
On February 15th, 2013, residents of the Russian city of Chelyabinsk got a rude awakening. At 9:20 a.m. local time, a rock about 19 meters across came in at a low angle. It got nearly as bright as the sun as it slammed into the atmosphere.
I remember watching that video.
The pressure of its passage broke it up into several chunks, which broke up again. In a moment's time, the sudden energy released was equivalent to the detonation of 500,000 tons of TNT, as much as a small atomic bomb. While no one was killed, over 1,000 people were injured by flying glass, shattered by the explosion. No doubt they were at their windows gawking at the huge vapor trail in the sky when the shockwave hit. There was no warning for this event. The asteroid was essentially too small to detect while it was out in space.
Look how tiny it is.
Well, for now, at least. Telescopes are coming online soon that should be able to find smaller asteroids and give us some warning. Astronomers are more worried about ones roughly 100 meters across or bigger. These can do serious damage on a citywide scale or larger, but at the moment aren't easy to spot much in advance. And what do we do if we do see one headed our way? As of right now, there's not much we can do. Studies have been done to determine the best course of action, maybe lobbing a nuke at it or simply ramming it with a space probe to change the orbit and make sure it misses Earth. These ideas look good on paper, but they haven't been tested yet.
No, you blow it up, you're just going to have a whole bunch of pieces.
The good news is that objects that size hitting the Earth are rare, maybe once every century or three. But if we do nothing, it will happen eventually. As science fiction writer Larry Niven points out, the dinosaurs went extinct because they didn't have a space program. Hopefully, we're smarter than they were. Today you learn that meteors are small bits of interplanetary debris sloughed off by asteroids and comets. When the Earth plows through
light. Hey, now we're getting into good stuff.
Hey, Phil Plate here, and this is Crash Course Astronomy.
Hello,
in last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint. Light is a wave. It took centuries of thought and experiments to figure that out, and to also figure out that, at its most basic, light is a form of energy. It travels in waves, similar to waves of water in the ocean, except with light, the things doing the waving are electric and magnetic fields. Literally, light is a self-contained little bundle of these two fields intertwined. That's why we call light electromagnetic radiation. The details of this are very complex, but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength as well, and this may be its single most important feature. That's because the energy of light is tied to its wavelength. Light with a shorter wavelength has more energy, and light with a longer wavelength has less energy. And our eyes have a really convenient way of detecting these different energies. Color. What you think of as the color violet is actually light hitting your eye that has a short wavelength. Red light has a longer wavelength, about twice the distance between crests as violet light. All the colors in between, orange, yellow, green, blue, have intermediate wavelengths. This spread of colors, wavelengths, is called a spectrum. Over millions of years, our eyes have evolved to detect the kind of light the sun emits most strongly. Well, that makes sense. That makes it easier for us to see. We call this kind of light visible light. But that's just the narrowest sampling of all the different wavelengths light can have. If light has a slightly shorter wavelength than what our eyes can see, it's invisible to us, but it's still real. We call that ultraviolet light. Light with shorter wavelengths than that fall into the X-ray part of the spectrum, and light waves with the shortest wavelengths of all are called gamma rays. At the other end, light with slightly longer wavelengths than the reddest color we can see is called infrared light. Light waves longer than that are called microwaves, and those with the longest wavelengths of all are called radio waves. These different groups don't really have hard and fast definitions. Just think of them as general guidelines. But together, we call all of these different kinds of light the electromagnetic, or EM, spectrum. And remember, energy goes up when the wavelength gets shorter. So ultraviolet light has a higher energy than violet, X-rays have a higher energy than that, and gamma rays have the highest energy of all. Infrared light has lower energy than red light, microwaves lower than that, and radio waves have the lowest energy. When you look at the whole EM spectrum, you'll probably notice that we really do only see a teeny little sliver of it. Most of the universe is invisible to our eyes.
Yeah.
That's why we build different kinds.
That's all we can see is right here. Our eyes. This is what our eyes see. This is how much left is out there. We got a little, this is it. It'd be kind of cool to think that birds probably have a more wider spectrum, so they can see probably like from here to here. So when they look up at night, what they must see must be incredible.
Of telescopes to detect the kind of light our eyes can't detect. They let us see a lot of stuff that otherwise we'd never notice. So you might be asking, how is light made? Well, one of the most basic properties of matter is that when you heat it up, it gains energy, and then it tries to get rid of that energy. Since light is energy, one way to get rid of energy is to emit light. Another important property of matter is that the kind of light an object emits depends on its temperature. An object that's hotter will emit light with a higher energy, that is, a shorter wavelength. Cooler objects give off light with a longer wavelength. You may have seen this in action. Heat up an iron bar and it starts to glow red, then orange, then yellow as it gets hotter. The color, the wavelength of light emitted, changes as the bar heats up. Astronomers use a shorthand for this. We say that light with a shorter wavelength is bluer and light with a longer wavelength is redder. Don't take this literally. We don't really mean more blue or more red, just that the wavelengths are decreasing or increasing. So in this lingo, ultraviolet light is bluer than blue, and X-rays are bluer than ultraviolet. So objects that are more energetic, that have a higher temperature, are bluer than cooler, redder objects. This rule of thumb works really well for dense objects like iron bars and stars, even humans. You emit light, but it's in the far infrared, well beyond what our eyes can see. There are less dense objects in space too, like gas clouds, and the way they emit light is different.
You can actually see it in the wintertime here in Canada, that you give off infrared. That if you have really warm hands and you go outside, they steam. The steam rises from your hands. And it's because the infrared heat generated by your flowing heat inside actually creates the steam because it's so cold.
To understand that, we have to zoom in on them. Way, way in, and look at their individual atoms. And to understand that, we need to take a brief diversion into atomic structure. Atoms are the building blocks of matter. In general, atoms are made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive electric charge, electrons a negative charge, and neutrons are neutral. Protons and neutrons are much more massive than electrons and occupy the centers of atoms in what's called the nucleus. Electrons whiz around the nucleus, their negative charge attracted by the proton's positive charge. The type of atom depends on how many protons it has in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, and so on up the periodic table of elements. It's common to think of the electron as orbiting the nucleus, like a planet orbits the sun.
Hydrogen, helium, lithium,
that's not
beryllium,
really
boron,
the case.
carbon, nitrogen,
The
oxygen,
real
sodium,
situation
aluminum,
is
aluminum,
fiendishly complex
all
and
I
involves
remember up to.
pretty hairy quantum mechanics. But in the end, The electron is only allowed to occupy very specific volumes of space around the nucleus, and those depend on the electron's energy. Think of these like stairs on a staircase, where the landing is the nucleus. When you walk up the stairs, you have to use energy to go up, and when you do, you have to go up a whole step at a time. If you don't have the energy to get to the next step, you can't move. You can be on the first step or the second step, but you can't be on the first and a half step. There isn't one. Electrons are the same way. They whiz around the nucleus with a very discrete amount of energy. If you give them an additional precise amount of energy, they'll move up to the next energy level, the
that's
next
right.
step. But if
When
you give
they
them the wrong
orbit
amount,
around each
they'll
other,
just sit there. The opposite is true as
if they have
well.
like a
Electrons can be in a
proton and an
higher
electron
energy
circling
state
each other,
up
you
on a
put
higher
energy
step,
into that
and then
proton, the
give off
electron
energy when
jumps
they
out.
jump down. The
Instant
amount they
jump
give off is
jumps away
exactly
from
the
that
same amount
electron.
needed to get them to jump up in the first place. How do they get this energy? Light. If light hitting the atom has just the right amount of energy, the electron will absorb it and jump up. It can also jump down and emit light at that energy too. An electron can also jump 2 steps or 3 or whatever, but it needs exactly the right energy to do it. But as I said earlier, energy and wavelength are the same thing, and that's equivalent to color. So when an electron jumps up or down, it absorbs or emits a very specific color of light. Not only that, but the steps are different for different atoms. To stick with our analogy, it's like different atoms are different staircases with different heights between the steps. So when an electron jumps down a step in a hydrogen
this
atom,
guy's
it
getting a
emits a
little
different
out
energy,
there.
a different color of light than an
Like,
electron jumping down in a
I understand
helium
what
or
he's saying,
calcium
but
atom.
he's not
And this
conveying it
is the
graphically
key
very
to
well.
the universe. Because different atoms emit different colors of light. If we can measure that light, in principle, we can determine what an object is made of, even if we can't touch it, even if it's a bazillion light years away. And we can. Can you tell the difference between these two squares? They're a very slightly different shade of red. Your eye probably can't tell the difference, but a spectrometer can. This is a device that can precisely measure the wavelength of light and can, for example, distinguish light emitted by a hydrogen atom from light emitted by helium. When you hook one of these spectrometers up to a telescope, you can figure out what astronomical objects are made of. In the case of
that's
thin
cool.
gas clouds in space, the
That they
atoms
know
are
what stuff is
basically
starting to be
floating
made of.
free, rarely bumping into one another. The atoms emit those individual colors of light,
nice if they showed a
allowing us to
spectrum.
identify them.
They
Unlike
probably
dense
will show a
stars, the
spectrum
color
and
of
how
the
it
thinner
works.
gas depends more on what's in
I
it
hope.
than its temperature. And this is how we learned what the universe is made of. Stars
better
and
show a
gas clouds in
spectrum, fuckhead.
space are mostly hydrogen, with some helium and heavier elements thrown in. Jupiter has methane in its atmosphere,
Show a
Venus
spectrum.
carbon dioxide. Everything in the universe has its own mix of ingredients, like cakes at a bakery. With spectroscopy, we can taste them. But wait, there's more. You're probably familiar with the Doppler effect, the change in pitch when, say, a motorcycle goes by.
Red shift and blue
In
shift,
sound,
yes.
the wavelength defines the pitch. Higher tones have shorter wavelengths, and lower tones longer wavelengths. When the motorcycle is headed toward you, the sound waves get compressed, causing the pitch to rise. After it passes you, the pitch drops because the wavelengths get stretched out. The same thing happens with light. If an object is headed toward you, the wavelength of light from the source gets
blue.
compressed, shorter.
turns to
We
red.
say the light is blue shifted. If it heads away, the wavelength
Red
gets
shifted.
longer and it's red shifted. Apply that to a spectrum, and by measuring that shift, we can tell if an object
The blue and red shift spectrum is how we learned how old the universe was. We took the blue shift of everything that's pushing away from us, ran it in reverse, and came up with 4-point-something billion years old.
object is moving toward or away from us. Here's a teaser. This becomes super important later when we talk about galaxies. Spoiler alert, the universe is expanding, and it's
is
this
blue
redshift
shifted.
that allowed us to figure that out. And that's
Yep.
still not the end of it. With other spectroscopic techniques, we can determine if an object is spinning and how fast, whether it has a magnetic field and how strong it is, and even how massive and dense an object is. A
That's
vast
pretty cool
amount
how
of the
far along the
fundamental
sensors have
properties
coming.
of astronomical objects can be found just by dissecting their light into individual colors. Almost everything we know about the universe comes from the light objects in it give off.
Yeah, we're
Pictures
seeing
of
everything in
astronomical
just about every
objects show us
spectrum
their
now.
structure, their
Really
beauty,
cool.
and hint at their history. But with spectra, we can examine their blueprints.
that's beautiful.
Today you learned that light is a form of energy. Its wavelength
They didn't
tells
show an
us
actual
its energy
spectrum,
and
though.
color.
I was a little disappointed about
Spectroscopy
that.
allows us to analyze those colors and determine an object's temperature, density,
Yes,
spin.
they didn't show an actual spectrum, though. I don't think. I didn't see one. No. Well, in any case, when you see, I don't know if you've ever seen a spectrum before, but it lines up side to side, and one might be red, and it starts to get into different colors all the way up to like a blue. And there's sometimes you'll see small black bars that separate. This little black bar here, little black bar, and those black bars are what tell you what's inside the atmosphere. And that's how they tell what is in the atmosphere or compositions by the black bars in the spectrum. It'd be nice if they had shown that.
Oh, hey, sorry, I don't mean to be rude. I'm just
They
trying to
might show
figure
it
out
later
how
on.
far away my thumb is. How? Parallax.
That's horrible.
Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for
Yeah,
them.
once we started
By
taking
eye, and for all intents and purposes,
more than one
the
telescope, putting
stars
them
are
side by side
infinitely far
and
away. If you drive down a
far
road, you'll
space,
see nearby
I think
trees
you
flying
can see
past you,
things a
but
lot
distant
better.
mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects. And it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or
I don't think you'd
the
find it
ancient
in
Greeks
this
knew the Earth was
here
round, and
particularly.
there are lots of ways to figure that out. For example, ships sailing over the horizon
But
seem
yeah.
to disappear from the bottom up, as you'd expect as they slip around the
Sundogs.
Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured
Hey,
it out. He
remember-
knew that at the summer solstice, the sun
Reading the
shone
science
directly
behind
down
those.
a well in the city of Syene at noon.
Ice
He also knew that at
crystals.
the same
There's an
time,
ice thing
it
about
was
ice
not
crystals, and
shining
you
straight
get them
down
when
in
it's mostly
Alexandria and
cold.
could measure that angle. There's a
Because we
legend
get
that he
sundogs
paid
here
someone to
in
pace
Canada.
off the distance between the two
And
cities
usually it's really
so he
cold
could find the
and there's
distance
a lot of
between them. But
moisture in the
more
air.
likely, he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle, and applying a little geometry, he calculated the circumference of the Earth. His result, a little over
Smart guy.
40,000 kilometers, is actually amazingly accurate. For the very first
Smart guy.
time, humans had determined a scale to the universe. That first step has since led to a much, much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry,
My
you
phone
can
is never
figure out
nearby
how
for
far
those.
away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part.
He had
His
a method.
methods were sound, and they were used later
He
by
just
great
didn't have the
thinkers like
tools.
Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over
Method was
1,000
good.
years before
The
the
tools
invention
were
of the
bad.
telescope. And I think it also says a lot that these
Better
ancient
tools.
thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the Astronomical Unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the Sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe multiple times to measure the transits, and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the AU was 148,510,000 kilometers, plus or minus 800,000 kilometers.
Oh, that's a bit.
Good, but not quite good enough to make astronomers happy. Finally, in the 1960s,
800,000 is quite a bit.
astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse, so think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore these strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have 2 eyes, and this gives us binocular
Maybe one
vision.
of these days.
When you look at a nearby
Extreme. I'm not sure where you live. I don't know how cold it gets there. But here in Canada, it gets quite cold. And from time to time, I like to head on out into the boonies where there's absolutely no light. Turn off all my lights, let my things settle for a bit. Yeah, maybe. Yeah, it gets cool. So whenever you got your coldest day, head on out of the city. Far out of the city, get away from it, okay? As far as you can. Like once you hit the border of the city, okay, 30 minutes. Drive, 30 minutes away, at least. And then you find a nice little spot, you turn off all your lights, close your eyes, keep your eyes closed for another 2-3 minutes. And then when you open them back up and you look at the sky, ooh, it'll be a beautiful thing. Here, the colder it gets, the more you can see. Of course, there's moisture in the air during the daytime. Can't see stars anyways, but if you could, they'd be like wavy and whatever. If you ever look at the stars at a hot night, you notice that they wave and they kind of jiggle, and you can't, a lot of that will hide some of the stars. So the colder, the better. If you ever head out there, bring your camera. All right. Spend a little bit of time on any given night of the week. It doesn't matter which one. Pick one and go. You will see meteors or shooting stars every night. Some more than others, but you catch a few. It's really nice. You'll see.
Object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these 2 images together, compares them, does the geometry, and gives you a sense of distance to that object. And you thought your teacher lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline, then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance using parallax, we need a lot bigger baseline than the few centimeters between our eyes. Once astronomers figured out that the Earth went around the Sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the Sun to the opposite side of its orbit and observe the star again, then in principle we can determine the distance to the star assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was heliocentrism wrong? No. It's just that stars are really and truly far away, much farther than even the size of Earth's orbit. The first star to have its parallax successfully measured was in 1838. The star was 61 Cygni, a bit of a dim bulb, but it was bright enough and close enough for astronomers to measure its shift in apparent position as the Earth orbited the Sun. 61 Cygni is about 720,000 astronomical units away. That's a soul-crushing distance, well over 100 trillion kilometers. In fact, that's so far that even the Earth's orbit is too small to be a convenient unit. Astronomers came up with another one, the light year. That's the distance light travels in a year. Light's pretty fast and covers about 10 trillion kilometers in a year. It's a huge distance, but it makes the numbers easier on our poor ape brains. That makes 61 Cygni a much more palatable 11.4 light years away. Astronomers also use another unit called a parsec.
300,000 miles per
a star
second?
shifts over the course of a year.
Or
A star 1 parsec
188,000
away will
miles
have
per
a
second?
parallax shift of 1 arc
Shoot,
second,
that's fast.
1/3600th of a degree. That distance turns out to be about 3.26 light years.
Yeah, that's
As a
true.
unit of distance, it's convenient for astronomers, but it's
Chicago
a
would
terrible
be
one
really
if you're
bad.
doing the Kessel run.
Even a
Sorry,
tiny
Han.
town.
The nearest star to the sun we know
Tiny
of,
town.
Proxima
Even
Centauri,
a
is
single-
about 4.2 light years away.
A single
The
light
farthest
source
stars
above
can
you,
see
even
with
a
the naked eye
campfire.
are over
A
1,000
campfire,
light
if
years
you're
distant,
out in the
but
boonies
vast
with
majority
nothing,
are within
if
100
a campfire
light
ahead of you,
years.
you won't see the
Space-based
stars. You have to
satellites are
make
used
it
now
black.
to accurately find the distance to hundreds
blacker
of
it is, the
thousands
better.
of stars. Still, this method only works for relatively nearby stars, ones that are less than about 1,000 light years
Turn
away.
off your
But once we
headlights,
know those
turn off your
distances,
interior
we can
lights
use
if you
that
can.
information on more distant stars. How?
Close your
Well,
eyes,
like gravity, the strength
embrace
of
the
light
blackness
falls
for a
off
bit,
with
let
the
your eyes
square of the
adjust.
distance. If you have two stars that are the same intrinsic brightness, giving off the same
beautiful.
amount of energy, and one is twice as far as the other, it will be 1/4 as bright. Make it 10 times farther away, it'll be 1/100th as bright. So if you know how far away the nearer one is by measuring its parallax, you just have to compare its brightness to one farther away to get its distance. You have to make sure they're the same kind of star.
Yeah,
Some
I was
are
about
more
to say
luminous
that.
than
I was gonna
others.
say, yeah.
But thanks to spectroscopy,
All right,
we
they
can do
figured that
just
out.
that. A star's distance is the key to nearly everything about it. Once we know how far it is and we can measure its apparent
about
brightness,
brighter stars?
we can figure out how luminous it is, how much
Gotcha,
light it's
buddy.
actually giving off, and its spectrum tells us its temperature. With those in hand, we can determine its mass and even its diameter. Once we figured out
it's a
how
quick
far away
bathroom break.
stars
I shall
are,
return
we started to
momentarily.
grasp their true physical nature. This led to even more methods of finding distances. The light given
More
off by
coffee?
dying stars,
gotta get
exploding
coffee, too.
stars, stars that literally pulse, get brighter and dimmer over time. All of these and more can be used to figure out
be too
how many
long.
trillions of kilometers of space lie between us and them. And we see stars in other galaxies, which means we can use them to determine the actual size and scale of the universe itself. And all of this started when some ancient Greeks were curious about how
If I
big the
do
Earth
this
was.
again,
Curiosity
I'll
can
make
take
sure to
us a
record
great
instead of using a link.
distance. Today you learned that ancient Greeks were
Oh,
able
sorry.
to find the size of the Earth.
I'll record it
and from
next time.
that, the distance to and the sizes
What do we got
of
first?
the moon and sun.
Star. Oh shit! Hurry up! I gotta hurry up. We're starting to get into real good shit now. We got light, now we got stars.
Twinkle, twinkle,
Soon we're gonna
little
have
star.
gravity and black holes and
Oh,
hell
I know
yeah!
you
I'll be there. I'll be back. I'll be back. Hurry up! I gotta be.
At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light too. If you look through binoculars or take pictures of them, you'll see that they're all different colors too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force. Say it with me now. For science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object, but in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of two different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectra. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time it was thought that stars had roughly the same composition as the Earth, but Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today, and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic "Oh be a fine guy, kiss me," or "Oh be a fine girl, kiss me" to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the Sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between there are orange and even some yellow stars. But there are no green stars. Look as much as you want and you won't find any. It's because of the way our eyes see color.
Green, huh?
A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together to form other colors. A star can actually emit more green light than any other color, but we'll wind up seeing it as white. How do I know? Because if you look at the Sun's spectrum, it actually peaks in the green. Isn't that weird? Yep. The Sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the Sun is actually yellow. Not really. The light from the Sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the Sun, which is why the sky looks blue. The Sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the Sun a yellowish tint to our eyes. And looking at the Sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the Sun, so all the bluer light is scattered away. So, we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise. A very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, but now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low-mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low-mass stars like the sun and higher-mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today you learned that stars can be categorized using their spectra. Together with their distance, this
exoplanets, very nice.
When you look up at the night sky, and if you happen to live far from city lights,
I believe
you can see thousands of
earlier,
stars. It seems like the sky is crammed shoulder to shoulder with them, and you're only seeing the tiniest fraction of stars there are.
And the rogue
Billions
planets
more
too?
exist that are too faint to see with
crazy.
just your eyes. As you ponder this incredible number, a natural thought arises. Are there planets circling those stars too? And are any of them like Earth? People just like you and me have wondered about this for thousands of years. And right now, today, we can answer that question. And the answer is yes.
I didn't want to go too crazy.
Our sun is orbited by a lovely array of planets, and they're wildly diverse. Big, small, airless, rocky, gaseous, hot, cold, and more. That makes you think that maybe forming planets is easy with so many varieties to choose from. Even if making planets is hard, there are so many stars in the sky that it's hard to believe our sun is the only one that's been able to pull this trick off. Astronomers have fretted over this for a long time, but trying to find such planets is hard. The biggest problem is any such planets would be faint, far away, and sitting right on top of their parent star. Being able to see one in a telescope would be like trying to spot a firefly sitting next to a searchlight. So if you can't spot a planet like that directly, maybe you can spot it indirectly. Imagine two kids, one big and one small, facing each other. They clasp hands and start to spin around. As they do, the little kid who weighs less will make a big circle, and the bigger kid will make a small circle. The same would be true of a star and planet. As the planet orbits the star, it makes a big circle or ellipse, but the planet has gravity too, and it tugs on the star. That means the star will make a small circle, what's called reflexive motion. For a long time, astronomers looked really hard for this motion in nearby stars, but it turns out that indirect effect is also too small to see. There were a few false alarms, but no real planets. Then, in 1992, everything changed. Astronomers Alexander Volshan and Dale Frail made a shocking announcement. They found not just one planet, but two orbiting a pulsar, the dead remnant of a star that had exploded. This was really bizarre. When a star explodes, it's a catastrophic event that should destabilize any orbiting planets. It's the last place anyone would have thought to find them. However, follow-up work quickly confirmed that the planets did indeed exist, and in fact, a third one was found a few years later. The first true alien planets had been found. Officially, we call them exoplanets, which, you have to admit, is pretty cool. While this was an incredible discovery, it was still a little unsatisfying. For one thing, pulsars are really weird, and for another, it looked like those planets may have formed around the pulsar after the supernova explosion, from the material left over from the catastrophe. That's nothing at all like our own solar system, and that still left the question open. Are there exoplanets orbiting sun-like stars? We didn't have to wait long to find out. In 1995, Swiss astronomers Michel Mayor and Didier Queloz made a big announcement. They had found a planet orbiting the star 51 Peg, a star very much like the sun, just 50 light years away. How did they do it? Well, remember those two kids holding hands and circling each other? Even though the wiggling back and forth of the star is too small to measure, that doesn't mean the effect is undetectable. As the host star of the exoplanet makes its little circle, sometimes it's headed toward us and sometimes away. That means that its light will undergo a Doppler shift, and that can be detected. It's not a big shift and takes some pretty fancy equipment to see it, but it's measurable. That's how Mayor and Kairos found their planet. And the planet they found, called 51 Peg B, is weird. For one thing, the orbital period turns out to be just a little over 4.23 days. That's right, I said days. That means the planet is seriously close to its parent star, just 8 million kilometers out. Compare that to Mercury, which on average is 55 million kilometers from the sun. Not only that, but the amount of Doppler shift in the star is related to the mass of the planet. A more massive planet pulls harder on the star, making it move more quickly. They found the planet was at least half the mass of Jupiter, and probably more. That was a problem. According to planetary formation models, that wasn't possible. You can't form a planet that big, that close to a star. Well, it turns out the models are probably right. The planet didn't form that close.
Oh, it migrated.
It probably formed farther out, just like Jupiter did. And like Jupiter, it then moved, migrated inward toward the star as it interacted with the disk of planet-forming material around the star. In our solar system, Jupiter didn't get very far in its inward motion. It's thought that interactions with Saturn put the brakes on that and pulled Jupiter out to where it is now. Apparently, 51 Peg B didn't have its own version of Saturn pulling on it. Its inward spiral continued until it ran out of disk material to interact with, which was very close indeed to the star. We call planets like that hot Jupiters. Once 51 Peg B was found, other teams began looking for short-period planets, and within a few years, several more had been found. Many of them hot Jupiters, just like 51 Peg B. Now, mind you, at first there was a lot of doubt and skepticism in the community about these exoplanet discoveries. A lot of other phenomena could masquerade as planets, like star spots, pulsating stars, or background stars messing up the measurements. Scientists discussed these possibilities vociferously, as well they should. Science is all about not fooling ourselves. A good scientist wants other scientists to try to poke holes in their ideas.
Yeah.
It's disappointing to be wrong, but if we are, we want to know. That all changed in 1999. A planet
Thank
called
you, Extreme.
HD
I'll take a look at that
209458b had been discovered on a very short orbit around its star, taking just 3.5 days. As luck would have it, from Earth, we see the planet's orbit edge on. That means once per orbit, it passes directly in front of its star. This event is called a transit, and when the planet transits the star, it blocks a little bit of the star's light, and that means we can detect a dip in the star's brightness. And sure enough, that dip was found. HD 209458b was the first independent confirmation of an exoplanet, and pretty much everyone was on the bandwagon after that. The beauty of transiting exoplanets is that the amount of starlight blocked tells you how big the planet is.
Especially
a
in
big
winter.
planet blocks more light. If we know the planet's mass from the star's Doppler shift, we can use the planet's size to calculate its density. This is important. A gas giant like Jupiter has a low density, and a rocky metallic planet like Earth has a very high density. Without even being able to see the planet directly, we can already start to determine what it's like physically. In 2009, NASA launched a space-based telescope named Kepler, designed specifically to stare at
lucky guy.
150,000 stars
Wish
to
I
detect
had
that
that kind of
telltale dip in
interest in
light,
that kind of
indicating
equipment
exoplanet
then.
transits.
Or
And
even
oh
now.
my, did it work.
The equipment.
By early 2015, Kepler
think I would
found its
use it, though.
1,000th confirmed exoplanet, and there are 500 more confirmed from ground-based telescopes. That's more than 1,500 planets,
I'm not in a
and we
good
have well over
place
3,000
world
more
to do
candidates
so.
from Kepler awaiting confirmation.
Waste.
All these planets have been found using indirect methods. What about actually seeing them, getting photographs of them? That's hard because planets are so faint. But it's not impossible.
You can
In
get the
2004,
spectrometer.
the first picture of an exoplanet was released, 2M1207b, a planet with 5 times the mass of Jupiter. It orbits a brown dwarf, a peculiar kind of low-mass star that we'll learn more about in a future episode. It's a young system, which makes it easier to see. The planet is still glowing hot from its formation, and it appears a lot brighter using a telescope that can see in the infrared. About a dozen other planets have been seen this way too. My favorite is the planet orbiting the star Beta Pictoris. It has 7 times the mass of Jupiter and orbits the star in about 20 years, and we've actually seen it move. Images taken a few years apart actually show the planet in different positions around the star, confirming its orbital motion. That is incredible. Taking photos of these planets is still a daunting task, which is why so few have been seen. But we're getting better at this, and as new technology comes along, we'll get more pictures of exoplanets and learn even more about them. The sheer variety of exoplanets is staggering. Hot Jupiters are the easiest to find because they're massive and fast, making their signal easier to detect. But as the techniques have improved, planets of lower mass have been seen. The smallest exoplanet found is smaller than Mercury, and not much bigger than Earth's moon. We've seen planets bigger than Earth but smaller than Neptune called super-Earths. About 500 multiple planet systems have been found too, including one with 7 planets. We've found them around every kind of star too. Exoplanets have been detected around stars like the Sun, as well as tiny cool red dwarfs, hot massive blue stars, and even red giants, stars nearing the ends of their lives. One exoplanet system announced in 2015 is incredibly old. The host star is 11 billion years old. When our solar system was just beginning to form, these planets were already over 6 billion years old, older than our solar system is now. We've even seen planets orbiting binary stars, making Star Wars seem a lot closer to home
That
than
would be
being in a
cool.
galaxy far, far away. We've seen so many exoplanets now that we can extrapolate a bit and get some numbers. The results are staggering. In our galaxy alone, there may be hundreds of billions of planets. In fact, planets may outnumber stars in the sky. Now, if we've seen planets as big as Jupiter and as small as Mercury, then we must have seen planets around the same size as Earth, right? Yes, we have. We've actually found hundreds of them so far. It looks like making planets the same size as ours is pretty easy for stars to do. But Earth-sized is one thing, Earth-like is another. How many of these planets might actually be habitable? That is, at the right distance from their star to have Earth-like conditions where liquid water could
Maybe
exist
a
on their
few?
surface. We're not sure. But from what we've seen so far, it looks like the galaxy may have more than 10 billion Earth-like planets. 10
I love it.
billion. And maybe a lot more than that. Now,
yeah.
I want to be careful
Life's
here.
out there
We don't
everywhere.
know what kind of atmospheres these planets will have or what they're
Not saying
composed of.
alien
Do the planets have magnetic
visit or
fields strong
anything,
enough
it's
to
most
prevent
likely
solar wind from
bacterial.
eroding away their atmosphere? Do they even have an atmosphere, let alone liquid water? We don't know.
knows?
But still, there are a lot
Nobody
of planets
knows.
out there. There could very well be a twin of Earth orbiting a star not too far away. And over the whole galaxy, we could be part of a very large family. After all this time, we finally have an answer to one of the biggest questions we've ever asked in astronomy. The sky is filled with planets. Today you learned that planets orbiting other stars exist and can be detected with a variety of
Beautiful. What
methods.
do we got? Brown dwarfs. Oh, I love these little planets. Little
The sky we
suns
now know
that didn't
is
quite make it
full
to a
of
sun.
stars and planets. Stars are massive enough to fuse hydrogen into helium in their cores, generating energy. The heat created by that process tries to expand them, but their gravity balances that outward force, creating an equilibrium. Planets, even gas giants like Jupiter, are far too small
sun
to
that
generate
didn't quite
fusion.
make it to
the
a
stuff
sun.
inside them resists being squeezed, so their gravity is balanced
just
by
hot
simple
enough
gas
to give
pressure.
off a bit
Jupiter
of
is
a
only
glow.
about 1% the mass needed to have fusion going on in its core. That's a pretty big gap between a big planet and a small star. It's natural to ask, what would happen if we dumped more mass onto Jupiter? Eventually it would become a star. The pressure in its core would get high enough to initiate hydrogen fusion. But what if we stopped just short of that? What if we have an
Just
object
short.
far more massive than a planet, but not quite massive enough to become a true star? What sort of thing would we have then? What indeed?
Brown dwarf, good sir. Now, living on a planet around
By
a
the late
brown dwarf would
1950s,
be
astronomers were
really
starting to
fucking
get a
cool,
pretty
'cause
good handle on how stars worked. The
the amount of
mathematical
energy
equations that
needed,
govern the
you'd have
physical
to be
processes of fusing hydrogen
so
into
close
helium
to
were
the
being
star
worked
that it would
out
just
and
take
applied
up
to
the
what we
entire
knew
sky.
from observing the stars themselves. In the 1960s, the idea that you could have a star with a minimum mass was becoming clear. If it had less than about
it'd be habitable.
0.075 times the sun's mass, roughly 75 times the mass of Jupiter, it simply lacked the oomph needed to squeeze hydrogen together hard enough to generate fusion. What would such an object look like? Well, it might form like a star, collapsing from a gas cloud just like the sun did 4.6 billion years ago. But instead of turning on and becoming a star, it would simply sit there, cooling. It might start off pretty hot due to the physical forces that made it, but it couldn't sustain that heat. Like a charcoal ember, it would radiate its heat away. After a few billion years, it would be cold, black, and for all intents and purposes, dead. As people started working out what such an object would be like, they tried to come up with a name for them. These things were black and small, but the name black dwarf was already being used for another type of object. Some people called them substellar objects, but that wasn't terribly catchy. Really low-mass stars are red, and these new objects would be so cool that they'd emit light in the infrared, and almost nothing at all in the visible. So they're somewhere between red and black. Jill Tarter, then a young astronomer working in the field, but who later made a name for herself looking for aliens, and oh boy, we'll get to that later, dubbed them brown dwarfs. She didn't mean it literally. Stars can't be brown, but the name stuck. Work proceeded in figuring out what brown dwarfs were like, and a lot of progress was made despite there not being any actual examples of them found. But the hunt was on. Now, as I talked about in episode 26, astronomers classify stars by their temperature. The hottest are O stars, then B stars, which are slightly cooler, down through A, F, G, K, and with the coolest stars being M. But then, in 1988, astronomers found a star that was so cool it was distinct from even the M-class stars. It was the first of a new cooler class of stars, so it was given the letter L. Why L? Because there wasn't any other astronomical object that used that letter, so why not? Many more such L stars were found, but still, these weren't true brown dwarfs. These stars were massive enough to initiate fusion in their cores. Worse yet, when brown dwarfs are first born, they're very hot. They can mimic higher mass L stars for a while, looking just like them, making it hard to distinguish between the two. But then a way out was found. A low-mass brown dwarf, it was determined, would have lithium in it, whereas normal stars wouldn't. Lithium is an element, the next one in the periodic table after hydrogen and helium. It can be fused much like hydrogen can, and regular stars would quickly use up their supply of lithium when they were still young. Brown dwarfs, lighter than about 65 times the mass of Jupiter, wouldn't fuse lithium at all. Very careful observations of an object would be able to detect lithium if it were there. That would provide a test to distinguish brown dwarfs from regular stars. The lithium test isn't perfect, but it does work under a lot of circumstances. Astronomers began using it to look for actual, real brown dwarfs. And so they found one. In 1995, a group of astronomers was observing the Pleiades, a nearby cluster of stars that's visible to the naked eye. They were trying to find the faintest stars they could in the cluster to get a complete sample of its membership. The advantage of this is that the distance to the cluster was pretty well known, so a faint star in it must be very low mass. They found an oddball object which they named Theta 1. It was very red and cool, and best of all, lithium was found in its spectrum. The best models of stellar mass showed that it had about 50 times the mass of Jupiter, or 0.05 times the mass of the Sun. It was clearly substellar. Huzzah! The very first true brown dwarf had been found. At just about the same time, astronomers found that another nearby star, called Gliese 229, had an extremely faint companion. Spectra showed that it was even weirder than Theta 1. It also had lithium and so was clearly a brown dwarf, but its spectrum showed it had methane in its atmosphere. Methane is a delicate molecule and would break down even in the mild heat of Theta 1's atmosphere. This new object, called Gliese 229b, was even cooler than Theta 1. It was looking like we needed yet another letter to classify stars, and so T-dwarfs became a thing. On a personal note, when I worked on Hubble Space Telescope, Gliese 229b was one of our camera's first targets after it was installed on Hubble in 1997. I was lucky enough to work on the spectrum we took of it, and it was freaky. It emitted almost no light in the visible part of the spectrum and rocketed up in the infrared. I'd seen a lot of stellar spectra before, but nothing like this. Remember, Gliese 229b had only been discovered 2 years before. I became so intrigued by it, I wound up studying low-mass stars and brown dwarfs for several years after. Well, it didn't take long before more brown dwarfs were found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, an orbiting observatory designed to scan the entire sky looking at infrared light. It found hundreds of brown dwarfs, and now at least 2,000 are known, with more found all the time. Some are so cool that they form yet another classification, Y dwarfs. So now we have O, B, A, F, G, K, M, L, T, and Y. You're on your own for an acronym here. So if brown dwarfs aren't brown, what color are they? Some are so cool they don't emit visible light at all, so they'd be black. You could be right over one and you wouldn't see it. But some are still warm and so give off some visible light, feeble as it might be. What color would they look? Funny thing, they might be magenta. You'd think they'd be really red because of their temperature, but it's a bit more complicated than that. Remember, they have molecules in their atmospheres that absorb specific colors of light. In some brown dwarfs, there are molecules like methane and even water, well, steam at those temperatures, that are pretty picky about what colors they absorb. Some of these molecules block more red light than blue, so that messes with their colors, making them look magenta. WISE takes pictures in the infrared, which our eyes can't see. To make pictures, astronomers map each infrared color to one our eyes can see. So an image using the shortest wavelength infrared detector is displayed as blue, the medium wavelength one green, and the longest one red. Brown dwarfs put out a lot of light in the intermediate wavelength WISE sees, so weirdly, they appear green in WISE pictures. That does make them easy to spot in those images, even when thousands of other stars are visible too. The physical nature of brown dwarfs is just as weird as you'd expect. For one thing, they have a very unusual characteristic. As they get more massive, they don't get any bigger. Usually, if you dump mass onto an object, it gets bigger. Take 2 lumps of clay and smush them together, and you get one more massive, slightly larger lump. Same with planets and stars. But brown dwarfs are different. At their cores, the density is very high, and the physics is a bit different than what you'd expect. The details are complex, but the end result is that when you add more mass to them, they actually get denser, not bigger. This effect becomes important right around the mass of Jupiter, which means that a brown dwarf, twice as massive as our biggest planet, won't actually be a whole lot bigger. So what's the difference between a small brown dwarf and a really big planet? Well, not much. Nature isn't as picky as we are about having narrowly defined borders between classes of objects. Some people say a planet forms from a disk of material around a star, growing larger as it accretes stuff, while a brown dwarf collapses directly from a cloud of gas and dust. But then you could have 2 objects the same mass and which look exactly the same, yet one would be a planet and one a brown dwarf, depending on how they formed. That strikes me as inconvenient. Astronomers are still debating this, and it gets worse. For example, as I said before, brown dwarfs over 65 times Jupiter's mass fuse lithium. It turns out that ones more massive than about 13 times Jupiter can also fuse deuterium, an atom that's very similar to hydrogen, except it has a proton and a neutron in its nucleus. But neither of these fuses actual hydrogen, so they're not considered true stars. That's still a little arbitrary, so again, I don't make too much of a fuss about it. I think it's best not to think of them as planets or stars, but something with characteristics of both. For example, the way their atmospheres behave depends a lot on how hot they are. In some, iron is vaporized, a gas. In others, they're just cool enough that iron condenses out of the atmosphere, which means it literally rains molten iron. One more thing. The nearest star to the Sun is a red dwarf called Proxima Centauri, which orbits the binary star Alpha Centauri. It's about 4.2 light years away. In 2013, astronomers announced the discovery of a binary pair of brown dwarfs called Luhmann 16. They're only 6.5 light years away and became the third closest known star system to Earth. You gotta wonder, could there be an even fainter, cooler brown dwarf closer to us? We know there's none in our solar system, even out in the Oort cloud. It would have been seen by now by one of several different sky surveys. But a light year or two out? Maybe. Is Proxima Centauri really the closest star, or will we find one even closer? It seems unlikely, but no more unlikely than the existence of brown dwarfs themselves. Maybe sometime soon we'll have to rewrite astronomy textbooks. Again, today we learned that brown dwarfs are objects intermediate in mass between giant planets and small stars. They were only recently discovered, but thousands are now known. More massive
low mass stars, low mass. Well, I know a little bit
stars in
about
the
them.
sky look pretty, flickering intense diamonds dotting the velvety night. But make no mistake, they are churning cauldrons of violence, barely constrained thermonuclear generators, creating enough energy to vaporize the Earth 1,000 times over. Their lives depend on it. Heck, our lives depend on it.
Holes?
But in their case, how they live and how long they live depends on that creation of energy. And in this universe,
that's what you're asking
nothing
about
lasts
earlier.
forever.
Stream. We'll get to that one on episode 35, I guess. We'll find out together, buddy.
Very roughly speaking, we can divide stars into two groups, low-mass stars and high-mass stars. That line lies around 8 times the mass of the Sun, and the reason for that is something we'll get to shortly. Things get very exciting at the high end, but for now, let's take a look at the low-mass end of the scale. Things are simpler there. Stars make energy in their cores by fusing hydrogen into helium. This is actually a pretty complicated process with lots of steps, but in the end, 4 protons plus some other ingredients get turned into one helium nucleus. Each time this happens, a little bit of energy is released, but in the core of a star, it happens countless times every second. It adds up to a lot of energy, enough to power a star, in fact. The rate at which hydrogen fusion occurs depends on how much pressure the star has in its core. A higher mass star squeezes hydrogen harder, so it fuses far more quickly. The rate is so much higher, in fact, that even though they're a lot bigger than low mass stars, high mass stars run out of hydrogen fuel in their cores more quickly. The lower mass a star is, the longer it lives. In the lowest mass stars, cool red dwarfs, the rate is so slow they last a long time. But there's more to it than that. They fuse hydrogen only in their very centers, and their cores aren't very big. Outside of this small region, the gas is convective, which means the hot stuff rises all the way to the surface, cools, then falls back to the core. That's important because it means the entire star is available for fuel. Both hydrogen and helium rise up through the star and then fall back down. The star can't fuse the helium, but the hydrogen that makes it back to the center is just more grist for the mill. Even after a long time, these stars can still shine as the hydrogen mixed throughout the star eventually makes it down to the center. So how long can a really low-mass red dwarf last? 1 trillion years. 1 trillion! The universe itself is less than 14 billion years old. So even the oldest red dwarf stars are basically infants. They're just barely getting a start in life, and they'll look pretty much the same for the next, 990 billion years or so. Eventually, though, they do run out of fuel. When one does, the star itself will be nearly pure helium, plus whatever heavier elements it was born with, and fusion will cease. It'll then cool, which will take many more billions of years. Finally, it'll be a cold, black, dead star, and for them, that'll be pretty much that. Or so we think.
Probably
the universe
made
is
of
far
diamond.
too young for any of these red dwarfs to have run out of fuel yet. That's true for stars at the lower end of the mass scale, up to roughly 1/3 of the mass of the Sun. But stars with more mass than that, stars more like the Sun itself, work a little differently. Their cores are bigger and hotter and denser. The different conditions inside them means the material in them doesn't convect. The hot stuff doesn't rise away from the core. What's in the core stays in the core. Outside the core, there's a very deep and active convection zone, but that doesn't interact with the material in the core itself. This means that not only do stars near the Sun's mass use up their fuel more quickly than red dwarfs, they have relatively less fuel to work with as well. Depending on their mass, their lives aren't nearly as long. For the Sun, that total lifespan is about 12 billion years, give or take. The Sun is nearly 5 billion years old now, so it's approaching middle age. Its life is similar to other stars of similar mass, so let's take a look into the far future. Will our Sun go gently into that good night? Ever since the Sun was born, it's been fusing hydrogen into helium in its core. The helium is trapped there, unable to be used as fuel, and it's building up in the core like ash in a fireplace. As it does, the density in the Sun's core slowly increases. When you compress a gas, it heats up. That means every day the Sun's core gets a wee bit hotter. That extra heat works its way out through our star, heating up the outer layers too. A hotter gas shines more brightly, so the Sun has been steadily increasing in brightness too. It's an incredibly slow but inexorable process. The Sun's increased in luminosity by about 40% since it was born. And it's not done. Helium is still building up in its core, and eventually it'll run out of hydrogen to fuse. Without fuel, fusion in the core will stop. Helium can be fused into carbon and a little bit of oxygen and neon, but it has to be incredibly hot to do so, and the Sun's core won't be anywhere near those conditions. Still, half the Sun's mass is bearing down on the core, so even though fusion stops, the core will continue to contract and heat up. It'll get so hot that the temperature outside the core will get to hydrogen fusion temperatures. Like igniting a match by holding it near a flame, the hydrogen outside the core will start to fuse. That'll occur in a shell surrounding the core, adding its heat to the outer layers of the Sun as well. When you heat a gas, it expands. The Sun's outer layers will do just that, and our star will grow to well over twice
once
its
it starts
current
giving
size.
the iron in there,
A star like this a subgiant. Not only will it grow, but its color will change. The Sun will be giving off more total energy than it does now, but its surface area will increase so much that the amount of energy radiated per square centimeter will go down. There'll just be a lot more square centimeters. This means, ironically, that the surface will actually cool. The Sun's temperature will go down. Cooler stars are red, and so the Sun will be too. But the core still isn't done. The details are complicated, but the core continues to contract and heat up. It gets so hot that the outer layers swell even more, and the Sun can bloat up to a fantastic 10 to 150 times its present size. It will then be a red giant. Red giants are fantastically bright because of all the energy percolating up from their interiors, coupled with their enormous size. When it turns into a red giant, the Sun will increase its luminosity by an incredible 2,000 times. That huge increase in luminosity does more than just make the Sun bright, though. As a red giant, the Sun will be so swollen that the gravity at its surface will drop substantially from what it is now. The force of gravity holding it down is weak, but the force from all that light blasting out from below is strong, easily overpowering gravity. Material on the surface will get blown off like a leaf in a hurricane. Think of it as a super solar wind. That means the Sun will shed mass a lot faster than it does now. While it's a red giant, it'll lose fully a third of its mass. At some point, the core contracts and heats up so much that the conditions will finally be primed for helium fusion. Suddenly, helium is converted into carbon, releasing a lot of energy. In a weird twist, due to a lot of very complicated physics, the core itself winds up expanding, absorbing most of that energy. In the end, less energy is pumped into the outer layers, so the Sun's outer layers contract. The Sun shrinks. The outer layers get dense again, which warms them up a bit, and the Sun turns from red to orange. It's still pretty big, more than 10 times its current day size, and puts out 20 to 50 times as much energy as it does now. But then we see a sort of reboot of what's happened in the core before. This time, though, helium is fusing in the core, and the carbon is building up like ash. Once again, the core starts to contract and heat up. This dumps more energy into the outer layers, they expand and cool, and the Sun turns into a red giant again. This time, it's even brighter and bigger and loses even more mass, shedding over half of what's left. In the meantime, helium fusion isn't very stable, to say the least. It swings wildly, increasing and decreasing its rate by huge amounts on very short timescales. The Sun will probably undergo a series of tremendous paroxysms, epic eruptions as the helium fusion spikes, creating huge surges in energy production. It'll lose even more mass each time. Finally, though, we approach the end game. The Sun doesn't have enough mass to squeeze carbon atoms enough to fuse them. They build up in the core until there's no more helium and fusion stops. On top of that, well, there's nothing on top of that. By this time, the Sun will have literally blown off all its outer layers. It's essentially a naked core, a hot, intensely bright, super compact ball, not much bigger than Earth. We call this a white dwarf.
Is this guy
its
done?
fate is sealed. It can't generate energy, so it'll cool and fade over the next few tens of billions of years. At that point, we can safely say the sun is dead. But that's not always the case for all stars. Some with more mass than the sun still go through another phase before dying. They form what are called planetary nebulae, and these are so amazing and beautiful that they rate their own episode, which, along with more fun stuff about white dwarfs, we'll get to next time. So, that's it for the sun. But what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried.
Oh yeah.
The average temperature on our planet will be so high that it'll melt rocks, and in a sense, it'll look much like it once did so many billions of years before, when it first formed. A molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands and will avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by that time. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the sun had more mass, it could avoid this fate. A star with about 8 times the sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high-mass stars have a much different and far more explosive fate than lower-mass stars like the sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low mass stars live a long time, fusing all their hydrogen into helium over 1 trillion years. More massive stars like the sun live shorter lives. They fuse hydrogen into helium and eventually helium into carbon and also some oxygen and neon. When this happens, they expand, get brighter, and cool off, becoming red giants. They lose most of their mass, exposing their cores, and then cool off over many billions of years. Crash Course Astronomy is produced in association with PBS Digital Studios. Really, go over to their YouTube channel, check it out, lots of cool videos there. Hey folks, Phil Plait here. In the last episode of Crash Course Astronomy, I talked about the eventual fate of the sun and other low-mass stars like it. After a series of expansions and contractions, they blow off their outer layers, become white dwarfs, and fade away over billions of years. The end. Except not so much. First, white dwarfs are pretty awesome objects and worth investigating. And second, when a star becomes a white dwarf, it produces what is, quite simply, one of the most gorgeous objects in space. To recap, when the sun ages, it undergoes a series of changes in its core. It's fusing hydrogen into helium now, today, and will eventually fuse helium into carbon, and it'll make a dash of oxygen and neon too. But when it runs out of helium to fuse, it's in trouble. It doesn't have enough mass to squeeze the carbon nuclei together, so they can't fuse. Fusion is the sun's energy source. Once the core is nearly pure carbon, that power is switched off. By this time, nearly 8 billion years from now, the sun's outer layers are gone, expelled by all the shenanigans going on in the core. What's left of our star is just its core, exposed to the dark of space. Over the next few billion years, it'll cool and fade to black. That might seem like the end of the story, but I skipped a step, and it's a beauty. When helium fusion stops, the sun's core will have about half the mass of what the sun does today. The rest will have blown away into space around it. What remains is basically composed of electrons and carbon nuclei mixed with a small amount of a few other elements. So what kind of an object are we left with here? You may know that light charges repel. Electrons have a negative charge and repel each other. The tighter you squeeze them, the stronger that pressure. There's also a second force called electron degeneracy pressure. It's a result of some of the weird rules of quantum mechanics. For you QM nerds, it's the the Pauli exclusion principle. This describes how subatomic particles behave on teeny scales. One of these rules is that electrons really hate to be squeezed together, above and beyond simple electric repulsion. This resistance is phenomenally strong and becomes the dominant force in supporting the core of a star once helium fusion stops. By the time this electron degeneracy pressure balances the core's immense gravity, the core is only about the size of Earth, 1% the original width of the sun, and it's called a white dwarf. Listing its characteristics is enough to melt your brain. Ironically, everything about it gets amplified as its size shrinks. It becomes ridiculously dense. A single cubic centimeter of it, the size of a six-sided die, has a mass of 1,000,000 grams, 1 metric ton. An ice cream scoop of white dwarf material outweighs 60 cars. Because it's so dense, the gravity at the surface of a white dwarf screams up, easily topping 100,000 times the Earth's gravity. If you have a mass of 75 kilos, you'd weigh 7,500 tons if you stood on the surface of a white dwarf. Not that you can. Stand there, I mean. You'd be flattened into a greasy smear. But not for long. Newborn white dwarfs are hot. They can glow at temperatures of upwards of 100,000 degrees Celsius. If you were on the surface, you'd be a vaporized and ionized smear. Their intense heat makes them white, and they're small, hence their name. They're so hot, they also glow in the ultraviolet, even in X-rays. Weirdly though, because they're so small, they're actually quite faint. The closest one to us, Sirius B, can only be seen with a telescope, even though it's 9 light years away, one of the 10 closest known stars. Over 10,000 white dwarfs have now been found in our galaxy. Still, any gas near a newly formed white dwarf is likely to be affected by the intense radiation pouring out of it. And hey, wait a sec. When a star like the Sun is in its final death throes, it expels its outer layers as a gaseous wind. You don't suppose? Yep. By the time that white dwarf forms, the gas blown off hasn't gotten very far from it, at most a light year or two. That's plenty close enough to get zapped by the white dwarf radiation, causing that gas to glow in response. What does something like that look like? Why, it looks like this. This object is what we call a planetary nebula. It's a funny name, and like so many other names, it's left over from when these objects were first discovered. The astronomer William Herschel, the same man who discovered infrared light and the planet Uranus, gave them that name because they appeared like small green disks through the eyepiece. The first planetary nebula was discovered in 1764 by the French astronomer Charles Messier, who spent years scanning the skies looking for comets. He kept seeing faint fuzzy objects that he mistook for comets, so he decided to make a catalog of them, a sort of avoid these objects list. That list is now a staple of amateur astronomers, because ironically it contains some of the best and brightest objects to observe. Among them is M27, the 27th object on Messier's list, one of the biggest planetary nebulae in the sky, and one of my favorites. I love seeing it through my telescope when it's up high in the summer. Planetary nebulae can be a bit tough to observe. Most are small and faint. On film, even with long exposures, they can appear to be little more than disks. For a long time, they weren't thought to be terribly complicated. When a star becomes a red giant and blows off its outer layers, it's rotating very slowly, so the wind should blow away in a sphere surrounding the star. Many planetaries, as we call them for short, are round and look like soap bubbles, pretty much what you expect when you look at an expanding shell of gas. But with the advent of digital detectors, their fainter structures became clearer, and the true beauty of these phenomenal objects was revealed. Some are elongated, some have spiral patterns, some have jets shooting out on either side, some have delicate tendrils streaming away from them. In fact, only a handful of the hundreds known are actually circular. Clearly, there's more to planetaries than meets the eye. If the wind from a star blows off in a sphere, how can planetaries come in all these fantastic shapes? It turns out the real situation is more complicated, as usual. When a star is a red giant, it spins slowly and blows off a dense but slow solar wind. If there's nothing else happening to the star, then that wind will blow outward in all directions, spherically. However, as those outer layers of the star peel away, they expose the deeper, hotter part of the star. The star starts to blow a much faster, though far less dense wind. That wind catches up with and slams into the slower wind. When that happens, you get that idealized soap bubble nebula. But some stars are binary, two stars that orbit very close together. We'll go into detail on them in a later episode. But If the dying star has a companion, they may circle each other rapidly. That will shape the wind, forcing more of it outward in the plane of the star's orbits due to centrifugal force. The overall shape of the expanding gas is flattened like a beach ball someone sat on. When the fast wind kicks in, it slams into that stuff in the orbital plane and slows down. But there's less stuff in the polar direction, up and down, out of the plane. It's easier for the wind to expand in those directions, and it forms huge lobes of material stretching for trillions of kilometers. That's a very common shape for planetary nebulae. But to explain many of the shapes we see, the two stars would have to orbit improbably close. Most binaries aren't that tight. So what can cause these shapes? When I was in graduate school, my master's degree advisor, Noam Soker, came up with a nutty idea. Maybe the stars had planets like in our solar system. If the star expanded into a red giant and swallowed them, it would take millions of years or more for the planets to vaporize. And for all that time, they'd be orbiting inside the star, moving faster than the star itself. Like using a whisk to beat eggs, the planets inside the star would spin it up, causing it to rotate faster, fast enough to explain the shapes of planetaries. That was in the early 1990s.
Really?
A few years later, the first exoplanets were found, and we saw that massive planets orbiting very close to their stars were common. I suspect this is why we see so many weird and fantastic shapes in planetaries. Their progenitor stars swallowed their planets. So planetary nebulae really may owe their existence to planets. And we come full circle. The glow in a planetary nebula is due to the hot central white dwarf exciting the gas. Most of the gas is hydrogen, which glows in the red. However, a lot of the gas is oxygen. There's not nearly as much oxygen as hydrogen, but kilo for kilo, oxygen glows more brightly than hydrogen due to the atomic physics involved. This oxygen glows green, giving planetaries their characteristic hue. Funny. When this green glow was first analyzed spectroscopically, astronomers couldn't identify the responsible element making it. They dubbed it nebulium, but eventually figured out it was just extremely tenuous oxygen. Other colors can be found too. Nitrogen and sulfur glow red, and oxygen can emit blue as well, all adding to the beauty of these celestial baubles. But these aren't just pretty pictures. The structure, color, and shape of a planetary nebula tells us about the life of the star that formed it. We learn even more about stellar evolution by studying how stars die. Mind you, the gas in a planetary nebula is still expanding, cruising outward from its initial momentum of being thrown off the star. Eventually, the gas expands so much it thins out and stops glowing. That takes a few thousand years, so when you see a planetary nebula, you're seeing a very short snapshot of the life, the death, of a star. And that's why we don't see many. Though there are billions of stars in the galaxy that die this way, this phase is very brief. Enjoy looking at them while you can. And what of the sun? Will it one day in the distant future be at the center of a planetary nebula it expels as it dies? Probably not. When the sun becomes a white dwarf, it most likely won't be energetic enough to make the surrounding gas glow. Most planetaries start off as stars more massive and hotter than the sun. When our sun dies, it'll go quietly and without a lot of visible fanfare. Alien astronomers, if they're out there in 8 billion years, may not even notice. But more massive stars do make quite the spectacle. And if they're really massive, more than about 8 times the sun's mass, they really and truly make a scene when they die. They explode. But that's for next week. Today you learned that when low-mass stars die, they form white dwarfs, incredibly hot and dense objects roughly the size of Earth. They can also form planetary nebulae, huge, intricately detailed objects created when the wind blown from the dying stars is lit up by the central white dwarf. They only last a few millennia. The sun probably won't form one, but higher mass stars do. Crash Course Astronomy is produced in association. Stars are in a constant struggle between gravity trying to collapse them and their internal heat trying to inflate them. For most of a star's life, these two forces are at an uneasy truce. For a star like the sun, the balance tips in its twilight years. For a brief, glorious moment, it expands, but then blows away its outer layers, leaving behind the gravitationally compressed core. It goes out with a whimper. Well, a whimper from a 2 octillion-ton, barely constrained, nuclear-powered fireball. But more massive stars aren't quite as resigned to their fate. When they go out with a bang. A very, very big bang.
High mass.
In the core of a star, pressure and temperature are high enough that
gonna
atomic
see some
nuclei
black holes?
can get squeezed
Ooh.
together and fuse.
Where is
This
black
releases
holes?
energy and creates
I want that
heavier
one.
elements.
Black
Hydrogen fusion
holes.
makes helium. Helium fusion makes
Neutron.
carbon. And each
Oh,
heavier
33.
element, in general, takes higher temperatures and
Spaghettification.
pressures to fuse.
I
Lower
see it.
mass stars like the Sun stop at carbon. Once that builds up in the core, the star's fate is sealed. But if the star has more than about 8 times the Sun's mass, it can create temperatures in its core in excess of 500 million degrees Celsius, and then carbon will fuse. There are actually a lot of steps in this process, but in the end you get carbon fusing into neon, magnesium, and some sodium. What happens next harkens back to what we found goes on in the Sun's core as it ages. Fuse an element, create a heavier one, then that heavier one builds up until the core contracts and heats up enough to start fusing it. So carbon fusion makes neon, magnesium, and sodium, and those accumulate. The core heats up, and when it reaches about 1 billion degrees, neon will fuse. Neon fusion creates more magnesium as well as some oxygen. These build up in the core, it shrinks, heats up to about 1.5 billion degrees, and then oxygen fuses, creating silicon. Then that builds up until the temperature hits about 2 to 3 billion degrees, whereupon silicon can fuse. Among a pile of other elements, silicon fusion creates iron, and that's trouble. Big, big trouble. Once silicon fusion starts, the star is a ticking time bomb.
That's what
But
I was
before
looking
we
for.
light that
Iron.
fuse,
Once
let's
the
take a step
iron
back.
gets in there.
What's happening to the
This
outer layers of
wrong
the star?
star.
What do we see if we're outside, looking back at it? Because the star was born massive, it spent its hydrogen fusing days as a blue main sequence star. Stars like this are extremely luminous and can be seen for tremendous distances. Like the Sun, though, a massive star changes when hydrogen fusion stops. Its core contracts, and then helium fusion begins. It swells up just as the Sun will, but instead of becoming a red giant, it generates so much energy, it becomes a red supergiant. These are incredibly huge stars, some over 1 billion kilometers across, and they are luminous. For example, Betelgeuse in Orion is a red supergiant and one of the brightest stars in the sky, despite being over 600 light years away. From that distance, you'd need a decent telescope to see the Sun at all. And that's nothing compared to VY Canis Majoris, the largest known star, which is a staggering 2 billion kilometers across. We even have a special term for it, a hypergiant. As the core switches back and forth from one fusion reaction to the next, the outer layers respond by contracting and expanding, so a red supergiant can shrink and become a blue supergiant. Rigel, another star in Orion, is a blue supergiant, putting out over 100,000 times as much energy as the Sun. Okay, let's go back to the core. It now looks like an onion with multiple layers. Iron is building up in the center, surrounded by fusing silicon. Outside that is a layer of fusing oxygen, then neon, then carbon, then helium, and finally hydrogen. You might think massive stars would last longer because they have more fuel than lower mass stars. But the cores of these monsters are far hotter and fuse elements at far higher rates, running out of fuel more quickly. A star like the Sun can happily fuse hydrogen into helium for over 10 billion years. But a star twice as massive as the Sun runs out of hydrogen in just 2 billion years. A star with 8 times the Sun's mass runs out in only 100 million years or so. And each step in the fusion process happens faster than the one before it. In an extreme case, like for a star 20 times the mass of the Sun, it'll fuse helium for about 1 million years, carbon for about 1,000, and neon fusion will use up all its fuel in a single year. Oxygen lasts for only a few months. Silicon fuses at a ridiculously high rate. The star will go through its entire supply in, get this, a day. Yes, 1 day. The vast majority of a star's life is spent fusing hydrogen. The rest happens in the metaphorical blink of an eye. Silicon fuses into a bunch of different elements, including iron. That inert iron builds up in the core, just like all those elements did before. And just like before, the iron core shrinks and heats up. But there's a huge difference here. In all the previous fusion stages, energy is created. That energy transforms into heat, and that helps support the soul-crushing amount of stellar mass above the core. But iron is different. When it fuses, it actually sucks up energy instead of creating it. Instead of providing energy for the star, it removes it. This accelerates the shrinking, compressing the core, heating it up even more. Even worse, at these temperatures and pressures, the iron nuclei suck up electrons that are whizzing around, which are also helping support the core. It's a double whammy. Both major means of support for the star are removed in an instant. Silicon fusing into iron is happening so fast This literally takes a fraction of a second once it gets started. The core gets its legs kicked out from under it. It doesn't shrink, it collapses. The gravity of the core is so mind-bogglingly strong that the outer parts crash down on the inner parts at a significant fraction of the speed of light. This slams down on the central core, collapsing from several hundred kilometers across down to a couple of dozen kilometers across in just a few thousandths of a second. The star is doomed, because all hell is about to break loose. Now, at this point, one of two things can happen. If the star has less than about 20 times the sun's mass, the core collapse stops when it's still 20 or so kilometers wide. It forms what's called a neutron star, which I'll cover in the next episode. If the star is more massive than this, then the collapse cannot be stopped by any force in the universe. The core collapses all the way down to a point. The gravity becomes so intense that not even light can escape. A black hole is born. We'll cover black holes in a future episode as well. But for now, what happens when the core collapses and suddenly stops? The core of the star, whether it's a neutron star or a black hole, is now extremely small with terrifyingly strong gravity. It pulls on the star's matter above it hard. This stuff comes crashing down at a fantastic speed and gets hugely compressed, ferociously heating up. At the same time, two things happen in the core. While this stuff is falling in, a monster shockwave created by the collapse of the core moves outward and slams into the incoming material. The explosive energy is so insane, it slows down that material substantially. The second event is that the complicated quantum physics brewing in the core generates vast numbers of subatomic particles called neutrinos. The total energy carried by these little neutrinos is almost beyond reason. In a fraction of a second, they carry away 100 times as much energy as the sun will produce over its entire lifetime. That's an incredible amount of energy. Now, these little beasties are seriously elusive and hate to interact with normal matter. One single neutrino could pass through trillions of kilometers of lead without even noticing. But so many are created in the core collapse and the material barreling down on the core so dense that a huge number of them are absorbed. This vast wave of neutrinos slams into the oncoming material like a bullet train hitting a slice of warm butter. The material stops its infall, reverses course, and blasts outward. The star explodes. It explodes. This is called a supernova, and it is one of the most violent and terrifying events the universe can offer. An entire star tears itself to shreds, and the expanding gas blasts outward at 10% the speed of light. The energy released is so huge, they can be seen literally halfway across the universe. They outshine all the stars in the rest of the galaxy combined. The expanding material, called the supernova remnant, forms fantastic shapes. The most famous is the Crab Nebula, from a star we saw blow up in the year 1054. The tendrils form as the material expands into the gas and dust that surrounded the progenitor star. As remnants expand and age, they become more tenuous. Some have bright rims as they push into material between the stars. Others form complex webs of filaments. I'm often asked if there are any stars near enough to hurt us when they explode. The quick answer is
a beautiful
no.
place.
Even though supernovae are incredibly violent, space is big. A supernova would have to be at least as close as 100 light years from us before we start feeling any real effects. The nearest star that might explode in this way is Spica in Virgo, and it's well over 100 light years away. I say might explode because it's at the lower mass limit for going supernova. It might not explode at all. Betelgeuse will certainly explode someday, but it's too far away to hurt us. We're pretty safe from this particular threat. I'll note that after all this, there is another kind of supernova involving white dwarfs, which we'll cover in our episode about binary stars. Happily, we're probably safe from them too. Breathe easy. As terrifying and dangerous as supernovae are, there's a very important aspect of them you need to know. Supernovae are capable of great destruction, but they're also critical for our own existence. When the star explodes, the gas gets so hot and is compressed so violently by the blast that it undergoes fusion, what astronomers call explosive nucleosynthesis. Literally.
Is this a painting or a picture? Doesn't say anything. I'm inclined to believe that it's a picture. Hubble.
Creating heavy elements explosively. New elements are produced in quantities that dwarf the Earth's mass. Calcium, phosphorus, nickel, more iron. all made in the hellish
You
forge of the
head on over
supernova
to
heat
NASA?
and flung outward into the universe. It
Website,
takes millennia or
for the Hubble
longer, but this
Space
material
Telescope
mixes with
pictures.
the other gas and dust
You see
clouds
some true
floating in
beauty out there.
space. Sometimes these clouds will be actively forming stars. Sometimes the collapse of the cloud to form stars may
Supercomputer
even
rendition.
be triggered by the supernova slamming into it. Either way, the heavy elements created in the supernova will become part of the next generation of stars and planets. Supernovae are how the majority of heavy elements in the universe are created and scattered. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all created in the heart of the titanic death of a star. That star blew up more than 5 billion years ago, but parts of it go on in you. Today you learn that massive stars fuse heavier elements in their cores than lower mass stars. This leads to the creation of heavier elements.
Neutrons. Ooh, I want to get the black holes, so we might finish it up at black
When
holes.
an 8 to 20 solar mass star ends its life, it does so with a bang. A supernova. And when it's all over, there's a couple of octillion tons of superheated plasma expanding away from the explosion site at a fraction of the speed of light, a whole mess of energy released in the form of light and neutrinos, and a bizarre little ball of quantum nastiness in the center, composed almost entirely of neutrons. The properties
Especially
of this neutron star are almost as bizarre as things get in the universe. And if it all seems rather alien to you, well, that's okay. For a little while, astronomers wondered if aliens really were behind what they were seeing. No, I'm not saying aliens.
I'm gonna keep bringing that up. Neutrons.
When we last left the core of a high-mass star, it
They're
was
not my
in a
favorite
bad
star.
way. Milliseconds ago, it was fusing silicon into iron, but now it's collapsing under its own immensely powerful gravity. The collapse takes a fraction of a second, but a lot happens in that fraction of a second. In lower mass stars, the core supports itself via electron degeneracy pressure, the result of a rule in quantum mechanics that says electrons vehemently resist being squeezed together. But even electron degeneracy fails to stop the collapse if the core has a mass more than about 1.4 times the mass of the Sun. That's just too much of a load to bear, and the collapse continues. Under these huge pressures, a funny thing happens. Protons, electrons, and other subatomic particles get smashed together, and they merge to form neutrons. And this happens to almost all of them. When the core collapses down to about 20 kilometers in diameter, it's essentially a ball of neutrons with some protons and electrons here and there that survived, and a crust of normal but highly compressed matter on top. When this happens, yet another effect comes into play. Neutron degeneracy. Like electrons, neutrons resist being squeezed too tightly together, but this time the strength of the pressure is far, far stronger than for electrons. If the core is less than about 2.8 times the Sun's mass, the collapse runs into a wall. It stops. This generates a huge shock wave, which, along with a flood of energetic subatomic particles called neutrinos, blasts outwards, blowing up the star. What's left of the core after the metaphorical smoke clears is a neutron star, one of the most bizarre objects in the universe. Such a star would be extremely weird, or really just extreme. Its mass would be more than that of the entire Sun, all packed into a sphere maybe 20 kilometers across. Now, let's just stop there for a sec and let that sink in. The Sun has a mass 300,000 times the Earth. Imagine packing that all into a ball the size of a small city. Too mind-boggling? Okay, think of it this way. You are mostly empty space. Every atom in your body has a nucleus made of tightly packed neutrons and protons, and electrons whizzing around outside them. If you could magnify an atom to be 100 meters across, the nucleus would be roughly the size of a marble. Imagine all that empty space between the nucleus and the electrons. That's a normal atom. But in a neutron star, all of that space would be filled with neutrons. All of it. Every nook and cranny inside the neutron star has matter in it, all the way down to the scale of an atomic nucleus. This is what gives a neutron star its mind-crushing properties. I'm now going to barrage you with very large numbers, so take a deep breath and you might want to sit down. Neutron stars are ridiculously dense.
I'll give you a moment. You heard the man. I'll give you a moment to take a seat down. Here we go. We got some math coming up. Y'all sitting down? Everybody got their pencils and papers and there's the recorders out? Shit, here we go.
Cubic centimeter of neutronium, as neutron star stuff is usually called, has a mass of about 400 million tons. Want some perspective on that number? Well, very roughly, that's the total mass of every single car and truck in the United States. Imagine a couple of 100 million vehicles crushed down until they could all fit inside this six-sided die. That's neutronium. It's so dense that, as far as it's concerned, normal matter is a slightly polluted vacuum. If you set it on the ground, it would fall right through the Earth. Now, anything that dense has a huge gravitational pull.
Now, he said, I feel like, right here.
If you set it on the ground,
If you set it on the ground, it would fall right through the earth. I don't think that's correct. I feel like if you set it on the ground, it would fall to the center of the earth and become the new core of the earth. Probably destroying us all, pulling us all into itself, and like really fucking whacking up the gravity. Yep, it would not be good. I don't think it'd fall right through. I think it'd go right to the center and become our new core.
it would fall right through the Earth. Now, anything that dense has a huge gravitational pull. If you were on the surface of a neutron star, well, you'd be very dead, obviously, like immediately, flattened down to a thickness of just a few atoms. And that's because a typical neutron star has a surface gravity 100 billion times stronger than Earth's.
You would be flattened into a paste about an atom thick and spread across the entire star. 1 atom thick. It's so much gravity.
I have a mass of about 77 kilos, and here on Earth I weigh about 170 pounds. On a neutron star, I'd weigh 17 trillion pounds. That's 23,000 times the weight of the Empire State Building. But wait, there's more. In our introduction to the solar system, I mentioned that when you take a spinning object and shrink it, the spin will increase. The usual example is an ice skater drawing in his arms, increasing his rotation until he's a blur. The same is true for the star's core when it collapses into a neutron star. It may have had a very slow spin.
You know, now that I think about it extreme, I think it would go through the core, keep its momentum up, slow down eventually, and then come back through the planet and eventually settle in the core. Because if you remember what he said, the dice, it's only like X amount of cars, so it's not like an entire planet. It's only just a dice size. So the Earth itself still has more mass. It would still settle in the middle somehow, or most likely it might wobble us through space a bit as it's bouncing around inside of and just fucking everything up.
Before the supernova, maybe even taking weeks to spin once. But when it shrinks down to just 20 kilometers across and becomes a neutron star, that rotation will increase by a huge factor. A freshly minted neutron star might spin several times per second. The magnetic field increases as well. A star like the Sun has an overall magnetic strength not too different from the Earth's, but when that core collapses, the strength of the field skyrockets, and a neutron star can easily have a magnetic field several trillion times stronger than the Sun. That's strong enough to erase your credit card from 100,000 kilometers away.
Marvel?
See? Ridiculous. All of these properties are brain-melting.
Yeah, DC.
But are they real? Could an object like this really exist?
Powered by
neutronium. My, yes. The first neutron star was detected in 1965, though not recognized for what it was at the time. A couple of years later, another one was found, and this time was correctly identified as a neutron star. But then things got weird. In 1967, Jocelyn Bell was a graduate student helping build a radio telescope. There was a persistent noise in their data they couldn't seem to fix. Bell studied it night after night,
radiation.
Finally figuring out that the pattern wasn't a problem with their data. It was from an actual astronomical object. She had discovered the first known pulsar.
Cool.
What's a pulsar?
That's how they found the background radiation as well.
Stars.
By mistake.
In a nutshell, their rapid rotation, coupled with their incredibly strong magnetic fields, launch twin beams of energy away from the star, like the beams from a lighthouse. The beams sweep around as the star rotates, and from Earth, we see this as a pulse, a blip of increased brightness. This pulse can be detected in visible light, radio waves, and even X-rays. The spin of a neutron star is amazingly stable, making these pulses act like a very accurately timed cosmic clock. In 1967, no one could believe a natural object could do this, and this object was half-jokingly given the name LGM-1,
down through the Earth.
Little Green Men 1. Now we know of over 1,000 pulsars in just our galaxy alone. And we know they're the leftover cores of massive stars that exploded. Some spin with periods many seconds or even minutes long. Some are in binary systems. Another normal star orbits them.
Cool
if they're close enough together, the neutron star can rip material off the other star and feed on it. This increases the pulsar's spin And we know of a few that have incredibly rapid rotation
Pulsars are
rates.
so
Some
cool.
spin
They're
hundreds
not my
of
favorite
times
star.
per second. These are called millisecond
But I do love
pulsars.
them.
And if they spun much faster, the centrifugal force would rip them apart, despite their tremendous gravity. Even after 1,000 years, a pulsar can still be a force to reckon with. There's a pulsar in the center of the Crab Nebula, the remains of a star that exploded to create that supernova remnant.
Oh,
a
that's
substantial
cool.
fraction of the light emitted from the nebula
Hold on. Yeah, this is an actual telescope view of
is
a pulsar.
powered by the pulsar
Look at that.
itself. Its
Look at
fierce
that.
output
That's like
energizes the
an
nebula,
entire
causing
solar
it to glow
system.
brightly,
Our solar
even
system
after
like
a
would
millennium.
orbit that
I'm
motherfucker.
telling you, thinking
Oh,
about
shit.
neutron stars makes the hair on the back of my neck stand
That's
up.
crazy.
And I haven't even mentioned magnetars yet. Neutron stars
Oh,
are more than
magnetars, my
just
favorite.
weird little balls of neutrons. They have a crust,
He actually
probably
said
a
it.
few centimeters thick, made of highly compressed but more or less normal matter, squeezed into a kind of highly stiffened crystal state. The magnetic field of the star penetrates this crystalline crust and stretches out for quite a distance. In some neutron stars, the magnetic field is even stronger than usual and can be, get this, a quadrillion times stronger than the sun's. These uber-powerful neutron stars are given the
elaborate a
name
little more?
magnetars.
Oh,
They're
wait,
relatively rare.
just hold on, my
Maybe
favorite.
10% of all neutron stars
favorite
are
star.
born as magnetars, and they have short lifetimes. The magnetic field is so strong it acts like the brakes on a car, slowing the neutron star's spin. That spin helps power the magnetic field, so the field weakens as the star slows. But while they're around, magnetars are the most magnetic objects in the universe. And with great power comes great responsibility. If your responsibility is to be one of the scariest objects in the universe. Why? In a
Even more
neutron
scary than a
star,
black
the
hole,
crust
baby.
and magnetic field are locked together, so a change in one affects the other. The crust of the star is under incredible strain due to the intense gravity and rapid rotation. If the structure slips, it can snap, creating a starquake, like an earthquake, but just a wee bit stronger. In an earthquake, huge amounts of energy are released when the Earth's crust shifts and snaps, enough to destroy buildings and quite literally move mountains. But in a neutron star, this effect is multiplied hugely. Remember, the crust is phenomenally dense and the gravity is enormous. If the crust strains and snaps, dropping just a single centimeter, the resulting release of energy is vast beyond imagining. This energy is released as a tremendous explosion in the crust, shaking it. This also shakes the magnetic field, which reacts poorly? When the sun's magnetic field throws a tantrum, we get a solar flare, which can be as powerful as billions of nuclear bombs. A magnetar flare dwarfs that into insignificance. It can be trillions of times stronger than a solar flare. In a fraction of a second, a magnetar can release as much energy as the sun gives off in 250,000 years. In 2004, astronomers
Holy
were stunned
shit,
when a
yeah.
huge blast of X-rays slammed into orbiting satellites.
Ah,
One of these
so cool. I
satellites,
love
named
magnetars.
Swift, actually had its detectors saturated with X-rays, even though it wasn't even pointing at the source at the time. The X-rays literally came right through the side of the satellite with such intensity that Swift, which was designed to detect powerful X-ray sources, was momentarily blinded by them. The source of this X-ray burst was quickly determined to be a magnetar called SGR 1806-20, and the effects were incredible. It actually compressed the Earth's magnetic field and partially ionized the Earth's upper atmosphere.
Holy fuck,
did I
that's
mention that this
powerful.
magnetar is 50,000 light years away?
50,000,
That's halfway across the
holy
galaxy.
shit.
That's incredible.
Yeah,
In a
it
distance
is.
of 500 quadrillion
Wow.
kilometers, its effects were felt more strongly than a powerful flare from
That's
the
why
sun.
I love the
good
magnetars.
news is that there are very few magnetars like this in the galaxy.
A black hole
Probably
couldn't
fewer
really
than a
affect us
dozen.
that way,
Also,
but a
catastrophic
magnetar
explosions
can.
like the one in 2004 are rare. If one had happened
In a
any other
different
time in the past 40
galaxy.
years or so, we would have detected it.
Yes.
And frankly, it's really cool that we had astronomical satellites orbiting the Earth which could study it. We've come a long way in understanding neutron stars since they were first discovered, but there's much about them we don't understand. Every time we find out more, we find out they're even weirder than we first thought. And yet, for all that, they're not the weirdest things in the sky. Not by a long shot. That place is held pretty securely by the other type of object created in a supernova, a black hole. Stay tuned. Today you learned that when a
the good
star
stuff.
between 8 and 20
One
times
more,
the
guys.
sun's
We got
mass
one more in
explodes,
us.
the core
We're gonna watch
collapses
some
to form a
black
neutron
hole.
star.
Baby, this is my favorite. love this stellar phenomenon.
As we've
Who doesn't
seen
love
over
a
the
good black
past few
hole, huh?
episodes, a lot of
Who doesn't
really
love a good
epic
black
stuff
hole?
happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force can possibly stop it now? It turns out
Gravity.
None more force. There is literally nothing in the universe that can stop the collapse. The core of the star is about to go bye-bye.
Yep, is there going to be our last episode for today?
Way back
I
in
am
episode
enjoying
7,
this
I
series
talked about
quite a
escape
bit.
velocity, and it's about to become a major player in the unfolding events of the collapsing core of a high-mass star. In brief, it's the velocity at which you need to fling something off the surface of an object to get it to escape. For the Earth, the escape velocity is about 11 kilometers per second. Get something moving that quickly,
Pretty
and it's
fast.
gone. It'll never fall back. The Sun, which has much stronger gravity than Earth, has an escape velocity of over 600 kilometers per second. A neutron star, with its immense gravity, can have an escape velocity of 150,000 kilometers per second. That's half the speed of light. Keep that in mind, and let's go back to the collapsing core of the star. As it shrinks, its gravity gets stronger and stronger. That means its escape velocity gets higher and higher. When it's neutron star size, the escape velocity is half the speed of light. But if it's more than 2.8 times the mass of the sun, the core will keep collapsing. When its size drops just a little bit more, down to roughly 18 kilometers, an amazing thing happens. The escape velocity at its surface is equal to the speed of light. And, well, that's a problem, because in our universe, nothing can travel faster than the speed of light. Not a rock, not a rocket, not even light itself. Once the core of the star shrinks down smaller than that magic size, nothing can escape. No matter can come out, so it's like an infinitely deep hole. And no light can come out, so it's black. We should come up with a snappy name for such an object. A black hole is the ultimate end state for the core of a high-mass star. Whatever happens in a black hole stays in a black hole. That region of space, that surface around the black hole where the escape velocity is the speed of light, is called the event horizon for that reason. Any event that happens inside can't be known. It's beyond the horizon for us. Black holes mess with our concepts of space and time. The math and physics of black holes is incredibly complex. So much so that even after several decades of study, physicists still argue over a lot of their properties. This has led to a lot of misconceptions about them too. All right, let's get this out of the way right now. The sun cannot become a black hole. It takes a stellar core at least about 3 times the mass of the sun to overcome neutron degeneracy pressure. That means the original star must have something like 20 times the sun's mass or more. So we're safe from that particular sci-fi scenario. Here's another misconception. A lot of people think of black holes as cosmic vacuum cleaners, sucking in everything near them. But that's not really true. They have powerful gravity, yeah, but only when you're very close to one. The power of a black hole comes from its mass, certainly, but just as important is its size, or really, its lack of size. If you could turn the sun into a black hole, which you can't, but let's pretend you could, then the Earth would orbit it pretty much exactly as it does now. From 150 million kilometers away, the Earth doesn't care if the sun is big or tiny. We're so far away that it doesn't matter. It gets to be a big deal when you get close. Remember from episode 7 about gravity, the strength of gravity you feel from an object depends on how massive it is and your distance from its center. The closest you can get to the sun is by touching it, being on its surface, about 700,000 kilometers from its center. If you get any closer to its center, you're inside it. The material outside of your position is no longer pulling you down, and so the gravity you feel will actually decrease. But if the sun were crushed down to about 6 kilometers across, it would be a black hole. You could get much closer than 700,000 kilometers.
Okay, a little off topic of what he's talking about here, but I have a feeling Planet X, there's something happening out in the outer solar system that's disturbing rocks and suggesting that there should be a planet there. And every time we look for it, there's nothing. It should be at this spot, we look, nothing. It should be this spot, we look, nothing. And scientists have that shit pretty well down. It's the moment you look at an area that it should be in, it's pretty close by for the most part. So I feel like maybe this outer object that's rotating around our sun might be a micro black hole that's disturbing stuff. Who knows? We'll see.
To it. And as you did, you'd feel a stronger and stronger pull as you approached it. So, from far away, a black hole with, say, 10 times the sun's mass would pull on you just as hard as a normal star with that same mass. You can orbit a black hole too, as long as you keep a safe distance between you and it. Orbiting a 10 solar mass black hole would be just like orbiting a 10 solar mass star, except not so hot and bright. Black holes are weird enough without the misconceptions. Black holes also come in different sizes. The kind of black holes I've been talking about have a minimum mass of about 3 times the sun's, and might get as high as a dozen or more times the sun's mass, if the parent star was big enough. We call these stellar mass black holes. If it happens to gobble down more matter, it gets more massive, and the event horizon grows as well. The black hole gets bigger. The idea that huge black holes could form in the centers of galaxies was first proposed in the 1970s, and it wasn't much later that the first one was found in the center of our own Milky Way galaxy. We've measured its mass at a whopping 4.3 million times the sun's mass. And now we think every major galaxy has one at its heart too, and in fact may be crucial in the formation of galaxies themselves. I'll discuss those more in a future episode. Here's a fun thought. What would happen if you fell into one, say a stellar black hole with 10 times the sun's mass? You'd die. But what happens in the few milliseconds before you leave the known universe forever is actually pretty interesting. As we've seen many times in our own solar system, tides are important. They arise because gravity weakens with distance, so a big object like a moon gets stretched by its planet's gravity. The far side of the moon is pulled less than the near side. A black hole has incredibly intense gravity, so the tides it can inflict are serious indeed. They're so strong that if you fell into a stellar mass black hole feet first, the force of gravity on your feet can be millions of times stronger than the force on your head. Remember, even the meager tides of a planet can rip moons apart. When you multiply that force by 1,000,000, you're in trouble. As you fall in, your feet are pulled so much harder than your head that you stretch, pulled like taffy. You'd become a long, thin noodle, kilometers in length, but narrower than a hair wide. Astronomers call this, and no, I'm not kidding, spaghettification. This would happen pretty close to the black hole, just a few dozen kilometers out. If you fell in from a long distance, you'd be moving pretty near the speed of light by that point, and you'd only have a millisecond or so before it killed you anyway, so yay? Note that this is only for stellar mass black holes. Supermassive black holes are far bigger, millions or billions of kilometers across. Compared to that size, the distance between your head and feet is small, so the tides across you aren't nearly as severe. You'd fall in pretty much intact, if that makes you feel any better. But compared to either flavor of black hole, a star still has substantial size, and one that gets too close to any black hole can be disrupted via tides. In March 2011, astronomers witnessed just such an event. In a distant galaxy, a star apparently got too close to a black hole and was torn apart by the ferocious tides. As the star was disrupted, it flared into brightness, momentarily blasting out 1 trillion times the sun's energy. That's how we were able to see it, even though it was several billion light years away. But I've saved the weirdest thing for last. One of Albert Einstein's biggest ideas is that space isn't just emptiness, it's an actual thing, like a fabric in which all matter and energy is embedded. What we perceive as gravity is really just a warping of this space, like the way a bowling ball on top of a bed warps the shape of the mattress. The more massive an object, the more it warps space. Not only that, but space and time are basically two parts of the same thing, what we now call space-time. You can't affect one without affecting the other. Einstein calculated that when a massive object warps space, it also warps time. Someone deep inside the gravitational influence of an object perceives time as ticking more slowly than someone far away from that object. I know, it's bizarre. We think of time as just flowing, and everyone should see it move at the same rate. But the universe is under no obligation to obey our preconceptions. Einstein was right. He was right a lot. This slowing of time is stronger the stronger the gravity of the object is. So your clock ticks a bit slower than someone far away from Earth, for example. The effect is tiny but real, and we've actually measured it on Earth with extremely precise clocks. However, if you get near a black hole, the effect gets a lot stronger. In fact, black holes warp space-time so much that at the event horizon, time essentially stops. You'd see your clock running normally and you'd just fall in. Bloop, gone. But someone far away would see your clock ticking more slowly as you fell in. And this isn't a mechanical or perception effect. It's actually woven into the fabric of space. To someone outside looking down on you, your fall would literally take forever. But then they wouldn't be able to actually see you. The light you emit would have to fight the intense gravity of the black hole to get out. And to do that, it would lose energy. This is very similar to the Doppler redshift I've talked about in earlier episodes, and it's called a gravitational redshift. When you're right at the event horizon, just when an outside observer would see your clock stop, they'd also see the light coming from you infinitely redshift. Your light would lose all its energy trying to leave the vicinity of the black hole, and you'd be invisible. And from your viewpoint, buckle up, because this is wow. You'd see the universe speed up, and just as you hit the event horizon, all of time would pass. All of it. And all that light coming at you from the universe would be blue shifted, becoming such high energy that you'd be fried. But since you're about to fall into a black hole, you probably wouldn't care. See? Like I said, wow, black holes are so strange, with such fiercely complicated math and physics to explain them, that scientists are still trying to figure out even basic things about them. For example, some scientists argue that the event horizon as we understand it may not actually exist, and that when you apply quantum mechanics to black hole physics, you find particles can slowly leak out. We're still new at this, and struggling to understand what may be the most complex objects in the cosmos. Black holes, as bizarre and counterintuitive as they are, keep popping up from here on out as we poke our noses into more and bigger astronomical objects. While
what he's talking about there for radiation leaking from a black hole, I'm pretty sure he's talking about Hawking radiation.
they may seem scary and weird, and let's be honest, they are, they have literally shaped most of the objects we see in the universe. Today you learn that stellar mass black holes form when a very massive star dies and its core collapses.
Yeah,
the core has to be more than about 2.8 times the sun's mass to form a black hole.
We got next, binary and multiple. I'd like to see if we get some trinary systems here.
We have one star in the solar system.
I know binary system works just fine.
Sure, it has a lot of planets, moons, asteroids, and comets it schleps with it as it moves through space, but no other star is part of our family. The sun is alone. Based on that, you might naturally think that, like the sun, stars are single too. They sure look that way by eye. But when you point a telescope at the sky, you find that this is not the case. A lot of stars travel the universe with companions, and sometimes more than one.
I think that trinary systems do exist.
With so many stars in the sky, some appear close together just by coincidence, even though in space they're actually very far apart. We call these optical double stars. By the 18th century, astronomers were starting to recognize that many stars that appeared close together really were physically orbiting each other. We call these binary stars to distinguish them from the coincidentally close together double stars. Although the numbers are a little bit uncertain, something like a third to half of all stars in the sky are part of a binary or multiple star system. One such binary system is visible to the naked eye and has been known for thousands of years. You may have seen it yourself. The star marking the kink in the handle of the Big Dipper is actually two stars, one called Mizar and the fainter one called Alcor. They're close enough together that you need decent eyesight to separate them, and they were actually used as an eye test in ancient times. Binary stars almost certainly formed together, near each other in the gas cloud that was their original stellar nursery. Instead of a single clump collapsing and forming a star like our sun, there are two such dense lumps, and they both collect material until they become true stars. There are lots of different kinds of binary stars. If the two stars can be seen separately using a telescope, they're called a visual binary. This is kind of a fluid classification. As telescopes get better, stars that are closer together can be resolved. These kinds of stars are fairly common. The brightest star in the night sky, Sirius, is a visual binary. It's a luminous blue star about twice the mass of the sun, orbited by a smaller, much fainter white dwarf. It's funny, too. As I mentioned in an earlier episode, white dwarfs can be very hot and energetic and emit light at much higher energy than normal stars. When you observe Sirius with an X-ray telescope, the white dwarf is by far the brighter of the two. Visual binaries are important because if you observe them long enough, you might be able to see their orbital motion. If we can measure their distance from Earth, then the actual size and shape of their orbits can be determined, and in turn, using the math and physics of gravity, this can be used to find the masses of the stars. In fact, the only way we know to get accurate measurements of stellar masses masses is when they're in binaries. And once we know the masses of the stars, as we saw in episode 26, we can learn everything else about them. How big they are, how brightly they shine, and even how long they live. It's no exaggeration to say that observing binary stars opened up the new scientific field of astrophysics, applying physics to astronomy. And that led to us understanding everything we do about the universe today. Not bad. Not all binaries are visual binaries, though. Some stars orbit so closely together that we can't split them even with our biggest telescopes. So how do we know they're binaries?
Spectroscopy.
As the two stars orbit each other, over time, one will appear to be heading toward us while the other circles away, and vice versa as they switch sides. While we may not see that motion directly, if we take spectra of their light, breaking it up into individual narrow colors, we can see the Doppler shift in their spectra. On their merry-go-round path, one undergoes a red shift as it moves away, and the other has a blue shift as it moves toward us. These kinds of stars are called spectroscopic binaries. Remember Mizar and Alcor, the Big Dipper eye test stars? I said they were a binary system, but I lied.
Well, that's what that
well,
was.
I understand.
I wasn't sure what that last picture
In even
was.
a small telescope,
the
you can see that
clarification.
Mizar is actually a visual binary. But it turns out that both of those two stars making up Mizar are actually spectroscopic binaries too. Mizar is a binary star. Even better, Alcor is a spectroscopic binary too. Since Mizar and Alcor orbit each other, it turns out they make up a sextuple star system. 6 stars, all gravitationally bound to one another. Obviously, stars can be in
6 of
bigger
them.
groups than binaries. There are triple star
Okay.
systems, quadruple, and more. Polaris,
Cool.
the North Star, is actually a pentuple system composed of 5 stars. It's possible
Yeah.
lots of stars are
Cool.
born in multiple systems.
Learn
However,
something new.
it's pretty hard to get a stable system like that. If the orbits aren't just right, some of the stars will tend to get ejected from the system. What we see today are the ones that coincidentally got things just right. Even then, they may not be stable in the long run. Was the Sun born in such a multiple system? We don't really know. It's certainly possible, and one way to find out would be to look for stars that have a very similar elemental composition as the Sun. But the Sun was born billions of years ago. Plenty of time for any stars born with it to wander off. Even at relatively slow speeds, 4.5 billion years is a long time, and for all we know, they could be 50,000 light years away and completely invisible to us. If
Thinking
there are
of
long-lost
astronomical
siblings to the
time
Sun out there, they
just
may
gives me a
remain
headache.
lost. Just like planets
Billions
orbiting the
of
Sun,
years. Oof.
binary star orbits can be short or very long. Some stars, separated by tens or hundreds of billions of kilometers, can take centuries to orbit each other, while some are so close they may only take days. One binary star, the most bizarre I know of, is called 4U 1820-30, and it's composed of a neutron star and a white dwarf. Their gravity is so strong and they're so close together that they orbit each other in 685 seconds, 11.4 minutes, roughly the length of this episode. Like exoplanets, binary star orbits are tipped every which way to our line of sight from Earth. But for some of them, we see their orbits edge on, or very nearly so. For these binaries, that means that every orbit we see each of these stars pass in front of each other, blocking it from our view. We call these eclipsing binaries. Eclipsing binaries are interesting because as one star blocks another, the total light we see from the system dips, just like in a solar eclipse when the moon blocks the sun. Over the course of one orbit, we see 2 such dips as the first star blocks the second, and then half an orbit later when the second passes in front of the first. If the 2 stars are similar, say both like the sun, then the 2 dips look very similar. But if one star is much brighter than the other, then the 2 dips look very different. The brighter star dominates the total light we see, so when the fainter star goes behind the brighter star, the light hardly drops at all. But when that fainter star blocks the brighter one, we see a bigger dip in the light. By carefully examining the sizes and shapes of the dips this way, a lot of interesting information can be gleaned from the system, including the sizes, masses, rotation rates, temperatures of the stars, the size and shape of the orbit, and even the distance to the system. Some stars, like humans, enjoy cuddling. They get so close together they become contact binaries, literally 2 stars touching each other. These are very strange objects. The stars can be stretched out into teardrop shapes due to the mutual tidal effects. If they get very close together, they merge into a double-lobed stellar peanut shape, like 2 stars cocooned in shared material. This can make things really weird for them. Imagine 2 stars born at the same time, perhaps a few million kilometers apart, tightly orbiting each other. One has, say, 5 times the mass of the sun, so it's a hot blue star, and the other one just 1/2, so it's a red dwarf. The red dwarf doesn't do much. It just slowly fuses hydrogen into helium, glowing feebly. The bigger star, though, goes through its nuclear fuel rapidly and becomes a red giant. It blows off a wind of matter and loses mass. Since the star's gravity depends on their masses, as the big star loses mass, the orbits get a little wonky, becoming more elliptical. But when the massive star swells, it gets so big the two become a contact binary. A lot of the material leaving the higher mass star gets dumped on the red dwarf, which starts to grow. Eventually, the big star loses most of its mass and becomes a white dwarf, while what used to be the lower mass star has grown and now might be more massive than the other star. It's a bit like Robin Hood taking from the rich and giving to the poor. If he gets too enthusiastic about it, then the poor become rich while the rich become poor. When we look at that binary system, we see a white dwarf star that is clearly more evolved than a high mass one, the opposite of what we expect. This is called the Algol paradox after the contact binary star Algol in Perseus, which shows this effect. Mass transfer between two stars can yield even more dramatic results. Imagine this same system a couple of billion years later. The high mass star has lost its outer layers and is a dense white dwarf. The other star eventually runs out of hydrogen fuel and swells into a red giant. This material then flows onto the white dwarf. White dwarfs have cruelly strong gravity. If the hydrogen flowing onto its surface piles up enough, the gravity can squeeze it so hard it fuses into helium. If the flow rate is just right, it piles up on the white dwarf and then undergoes fusion in a single colossal flash, erupting in a huge explosive flare. Some of these explosions can be incredibly violent, tens of thousands of times brighter than the sun. When this happens, a previously invisible star can suddenly flare into visibility in the sky. These have been seen historically and called stellar novae for new star. I love the irony. These stars actually have to be old near the ends of their lives to go nova, but the name stuck. The explosion can blow out the stream of matter falling from the other star, but when things settle down after a few weeks or months, the matter stream can fall back on the white dwarf and the whole cycle repeats. These are called recurrent novae. If the matter stream is slower, the material can fuse steadily, never piling up, so it never explodes. However, the mass of the white dwarf still increases. If it reaches a mass of around 1.4 times that of the sun, it gets compressed by its own gravity so much that its temperature soars upwards. It gets so hot that carbon fusion initiates, and that is a big problem. In a normal star, it would just expand due to all the extra energy being generated, but a white dwarf can't. It's ruled by electron degeneracy pressure. The extra energy just goes into fusing more carbon, and what you get is a runaway thermonuclear event. All the carbon everywhere inside the white dwarf fuses all at once. All of it. Basically, a solar mass of carbon will instantly fuse, releasing all that energy all at once. It's like setting fire to a dynamite factory. The star explodes. You get a supernova, and it's a completely different process than what we saw when a high mass star explodes. But coincidentally, it releases about the same amount of energy. The star tears itself to vapor and gets so bright it can be seen literally most of the way across the universe. Ooh, this makes them very, very important indeed, as you'll see in a future episode. Today you learned double stars are stars that appear to be near each other in the sky.
I learned
But if
quite a
they're
bit there on that one, I
gravitationally
must
bound
say.
together, we call them binary stars. Many stars are actually part of binary or multiple systems.
Clusters, okay. I didn't know, I thought only binaries could be
In the
really
last
existed.
episode,
Like
I
up to like
talked about
6 of
stars
them.
that are orbiting one
That's
another.
pretty good.
When it's two stars, it's called a binary. 3 stars would be a trinary system, and so on. But what happens if you
Yeah,
have 10 stars?
I would think that it would be in
1,000,
there.
a
The amount of
million?
pressure
What
that's
do you call
exerted.
it when stars cluster together?
Sounds like it would be something, yeah. I agree. Probably balls of diamond floating around out there somewhere.
It's likely that some stars are born individually, but astronomers think that most stars are born in groups called clusters, sometimes hundreds and sometimes hundreds of thousands at a time. There are 2 kinds of clusters, open or galactic clusters and globular clusters. Open clusters are loosely bound collections of dozens or thousands of stars, usually in an irregular shape. Some are big enough and close enough to us that they can be seen by the naked eye, faint fuzzy patches in the sky. Galileo was the first to discover, or at least record, the fact that they were actually composed of many stars so close together our unaided eyes couldn't resolve them. As we'll see in next week's episode, clusters are formed from gigantic clouds of gas and dust. Depending on local conditions, like how massive they are, these clouds can form dozens, hundreds, or thousands of dense clumps, which then contract to form individual stars. These stars can be bound together by their mutual gravity, forming an open cluster. Unlike the solar system, where the
without
sun
a doubt.
dominates and provides
Without
a
a doubt, it's
singular
true.
central source of gravity holding the planets under its sway, in a cluster, All the stars contribute to the overall gravity, so there's more general gravitational schmear. The stars all orbit the cluster's center of mass, even though there may not be anything at the very center. Not only that, but the stars don't all orbit in a flat plane like our planets do. Instead, their orbits are tilted in all different directions, more like the way long-period comets are scattered around the sun. Typically, an open cluster is a couple of dozen light years across, with stars much closer together than they are in interstellar space. The nearest known star to the sun is over 4 light years away, while stars in an open cluster are typically a fraction of a light year apart. Some clusters are very young, well, in an astronomical sense. They're a few million years old. Others are far, far older,
tiny chunk
billions
of
of
it
years in age.
Just
How do
a
we
little
know?
piece
By
of it.
looking at the stars
They're so
themselves.
huge.
Remember, hot blue massive stars don't
Probably
live long
diamond
before
planets
exploding.
out there,
If a
I'm
cluster
thinking.
has those kinds of stars, it must be pretty youthful. If all it has are much lower mass red dwarfs, it must be much older, all the more massive stars having died off. In fact, clusters are pretty useful this way. If you assume all the stars in them were born at the same time, a reasonable starting guess, then the age can be found by looking at the most massive stars still on the main sequence, still fusing hydrogen into helium like the sun is.
Yeah, I
The
got
most
you,
massive
Extreme. Don't
stars
worry
can
about
be
it. I
identified
got you,
by their
buddy.
spectra, which
Yeah, I
gives
got
us
you,
their
buddy. Don't worry.
mass, and then
It's
that
okay.
can be used to
I
get the
got you.
cluster's age. You might expect the distribution of cluster ages to be all over the place, with some young, some old, and some middle-aged. But in
I'm a
fact,
violent
most
offender
clusters
of
are young,
spells.
and very few are older than roughly 50 million years. That's because they evaporate. All the stars in the cluster interact with each other via gravity. That means they constantly tug on one another, changing each other's
Is
orbits.
that an
You
actual-
may remember
hold on.
from our episode about gravity that the kind of orbit an object has
It is.
depends on the amount of
Oh, that's
energy it
cool.
has. Give it more energy and the orbit gets
That's a time
bigger.
lapse.
Give it enough energy
actual
and it will
time
achieve
lapse.
escape velocity and
That's cool.
fly away. In clusters, the stars are always passing by each other and exchanging energy via their gravity. If a low mass star swings past a higher mass star, it can get
Something
a
like this is
relatively
pretty
big
obviously
kick to its energy
an
and get
animation,
flung into a
but
much
some of these
higher
are
orbit in the
actual
cluster,
pictures of
while
things
the high
happening.
mass
It's
star
really
loses
cool.
energy, dropping it down toward the center. Over time, these interactions tend to flick the lower mass stars out of the cluster completely, and the cluster loses stars. It starts with the lowest mass stars, but as they leave, even higher mass stars can be lost this way. Eventually, only the most massive stars are left, and those tend to blow up. Even then, the remaining neutron stars and black holes interact and fling each other away. This process is aided by collisions with gas clouds and the tidal forces of the collected stars in the galaxy itself. Given enough time, the cluster just disappears. The individual stars are left to orbit the galaxy on their own. About 1,000 open clusters are known, but their days are numbered. Eventually, over millions of years, they'll go away, their stars scattered across tens of thousands of light years, merging with the population of other stars in space. So, better observe them while you can. One of the most famous and beautiful open clusters in the sky is the Pleiades, about 500 light years from Earth. They appear as a small, tightly packed
They could
collection of
also
6
get
or 7
flung out.
stars to the eye, and a lot of people call them the Seven Sisters. Through binoculars, several dozen
If they
stars
have
can
an
be seen.
unstable
Most
orbit?
of them look blue, but that's what we in the science business call a selection effect or selection bias. The blue stars are the brightest, so we see them more easily. Through a telescope, redder stars are apparent. Long exposures of the Pleiades reveal a surprise. The stars are embedded in a dust cloud, which glows blue from reflected and scattered starlight. When I was younger, it was thought that this was the leftover stuff from which the stars formed. But now we know it's a coincidence. By sheer happenstance, the cluster is colliding with an unrelated cloud of dust. It's like driving a car through a dust cloud thrown up by a truck that went past you earlier. By another coincidence, the Pleiades are located in the sky next to the Hyades, the only other cluster with stars resolvable by the naked eye. The Hyades are much closer and appear bigger. In fact, they form the distinctive V shape of the horns of Taurus, the bull. As someone who enjoys taking out a telescope and observing the sky, I'm a fan of open clusters. A few are favorite targets whenever I'm outside. I love looking at the Pleiades with binoculars, and M35 at the foot of Gemini is another must-see for me in the winter through my telescope. But as much fun as they are to find, and as beautiful as they are to see, they can't hold a candle to globular clusters. These are clusters of not thousands, but hundreds of thousands of stars. They form a roughly spherical shape, hence the term globular, and generally have a well-defined core with stars scattered around them in a halo that fades away with distance. Most globulars are bigger than open clusters, with diameters perhaps 100 light years across, though size is a bit hard to measure since they don't really have an edge. Like open clusters, find core with stars scattered around them in a halo that fades away with distance. Most globulars are bigger than open clusters, with diameters perhaps 100 light years across, though size is a bit hard to measure since they don't really have an edge. Like open clusters, the stars in them orbit every which way, like bees around a beehive. Unlike open clusters, though, globulars are old, very old. Most are over 10 billion years old. We think they were among the first objects to form after the universe itself did. We know this because in most globulars, the most massive stars are less massive than the sun. They've been around so long that even stars like the sun have had enough time to become red giants and die. And that takes a long, long.
And also, like I said too, the colder the atmosphere, the less distortion you'll get from star viewing too. You want to get on a nice cold, like northern Michigan would be way better than Chicago for sure, because it gets quite a bit colder there. 100% colder is good. Cold is good for stargazing.
Long time. The stars in globular clusters tend to have less heavy elements in them too, which you expect if they're old. Massive stars explode and scatter their heavy elements into the universe, and
Andromeda's
that
not
takes
too far
time.
off.
It took
You can
billions
see
of years for
Andromeda in
stars
the
like the
sky
sun
with
to
your
form,
naked eye.
the ones with more heavy elements.
On a nice clear night.
Old stars formed before the universe was seeded with those elements, so they have more lighter elements in them than later generation stars like the sun. Despite being larger than open clusters, globulars have more stars and are denser, which is one reason they live longer than open clusters. Another is that they tend to spend most of their lives outside the galaxy on long looping orbits, and there's nothing out there to interfere with their solitary existence. Globulars are great laboratories for stellar astrophysicists. All the stars in them are born at the same time, and so they're the same age. They're also the same distance from Earth. So if you see one star in a globular that's twice as bright as another, it really is twice as luminous. That's handy if you're comparing stars for other characteristics. Because globulars are so old, they contain a lot of dead stars. We see quite a few white dwarfs, as well as neutron stars and black holes in them. If they have stellar companions, they strip off their material, which falls in and emits X-rays. What normal stars are left are low-mass red stars, so globulars tend to look red. Weirdly, there are some blue stars in globulars, called blue stragglers. And they were a mystery at first, since they shouldn't be there in such old objects. But astronomers figured out they're actually stars that have physically collided and merged to form a single higher mass star. Such collisions are extremely rare in space, but the stars are so tightly packed in globulars that collisions are more common. We know of about 150 globular clusters orbiting the Milky Way galaxy, our own local collection of stars that we'll dive into in more detail in an episode very soon. But other galaxies have more. Many hundreds or even thousands. Globulars are among my very favorite objects to observe with a small telescope. They're bright, compact, and their fuzziness due to so many stars packed so closely together gives them an illusion of activity, again like bees swarming a hive. They are incredibly beautiful, and that's the view from tens of thousands of light years away. Imagine what the sky would look like from a planet orbiting a star inside the cluster. The sky would be filled with stars, some so close and luminous, there could be dozens brighter than Venus appears in our sky. At night, you might be able to read by starlight. Sadly, though, this fantastic sight is probably more science fiction than science. Because globular stars lack heavy metals, it's unlikely they would have formed planets like Earth. And the stars are so closely packed that nearby encounters might eject any planets that did form. Such a scene would be amazing, but unfortunately, it's probably one that exists only in our imagination. Today you learn that open clusters contain hundreds or thousands of stars held together by gravity. They're young and evaporate over time. Their stars
taken from a bunch of different spectrums.
Globular clusters.
They don't get pictures like that with just regular cameras.
Astronomers have it pretty
easy
easy when we talk
and
to
put
the
something
public.
together.
I may be biased, but I think astronomy is the most beautiful of all sciences. Sure, other fields of science have lots of eye candy, but all I have to do is pull out a shot of Saturn and I win because Saturn. It's all gorgeous.
I win,
Planets,
Saturn.
moons, stars, clusters. But of all of them, you just can't beat a nebula.
Oh, look.
Why? Because nebulae.
Oh, beautiful. The universe is beautiful.
Nebula is Latin for cloud, and for once in astronomy, we have a name that actually describes the object accurately. Nebulae are clouds of gas and dust in space. I've already talked about them a bit. For example, stars form from nebulae. Our sun did about 4.6 billion years ago. When a medium-sized star dies, it blows off winds of gas, then lights them up as the white dwarf core of the star is revealed, creating a planetary nebula. Also, when a high-mass star explodes, it catastrophically vaporizes itself, becoming a violently expanding cloud of gas. Nebulae are literally part of the births, lives, and deaths of stars. So, besides being beautiful, they're also pretty versatile. There are a lot of ways of categorizing nebulae. One way is by how we see them. For example, if a cloud of gas is blasted by light from a nearby massive star, the gas in it becomes excited. The electrons in its atoms jump up to a higher energy level. When the electrons drop back down, they emit light. The gas glows, and we call this an emission nebula. The color of an emission nebula depends on the gas in it and how hot it is. Hydrogen, for example, glows most strongly in the red, and we see that color in most emission nebulae. Oxygen tends to glow green, but to a lesser extent it gives off blue light too. Other elements span the spectrum in colors they give off, and these colors aren't limited to visible light. Hydrogen can emit infrared and even radio light, and if it's energized enough, it'll emit in the ultraviolet too. That's true for many elements. Although most emission nebulae look substantial, they're actually incredibly tenuous. A typical density in a gas nebula is only a few thousand atoms per cubic centimeter. Mind you, in the air you breathe, there are about 10 to the 19 atoms per cubic centimeter, 1,000 trillion times denser than a typical nebula. Really, a nebula is barely more than a vacuum. The reason they look so cloudy is that they're big. Really big. A decent sized nebula is several light years in diameter, and that's a lot of centimeters. That much gas adds up, and so some nebulae can be pretty bright. While emission nebulae glow due to their own light, reflection nebulae are bright because, can you guess? They reflect the light of nearby bright massive stars. In this case though, the nebula isn't made of gas, but is instead mostly dust. And I don't mean like the hair and skin flake dust bunnies you find under your couch either. When astronomers talk about dust, they mean tiny grains, a micron across. Just so you know, a human hair is 100 times wider than that. These tiny grains contain things like silicates, aluminum oxide, and calcium. And in many cases, this dust is laced with complex molecules called polycyclic aromatic hydrocarbons. While I love that fancy name for them, you might know them better as soot. Yep, when you light a match, you're pretty much making some of the same stuff that lurks between the stars. Dust doesn't emit visible light, but it can affect the visible light from stars if they're inside the dust cloud or nearby. Turns out, dust is very good at scattering light. That means that when light hits it, the light gets sent off in some other direction. This scattering is highly wavelength dependent, so blue light is scattered very strongly, while red light can go right through. We saw this in the last episode. The dust surrounding the Pleiades star cluster is a reflection nebula. The light from the stars in the Pleiades is scattered by the nearby dust, and the blue light gets sent in every direction, including toward us. The red light doesn't scatter nearly as well, so we don't see it. It never gets sent toward us. Thick dust is also very good at absorbing visible light. If a star is embedded in enough dust, the light from it is dimmed considerably. If the cloud is dense enough or big enough, the dust can completely extinguish the light seen from a star. At the same time, if the dust is at the right density, the blue light from a star inside the dust cloud gets scattered, while the red light can get through. This effect reddens starlight, and in some dust clouds it provides a striking view. Stars outside the cloud look normal enough, but closer in they get redder and then fade out entirely. The result is a fuzzy red-edged hole in space. Pretty cool. You can see that effect in Barnard 68, a small dust cloud, just half a light year in size. These are also sometimes called molecular clouds. They're cold enough that atoms can stick together to form molecules. Their cores can be hundreds of degrees below 0 Celsius. Some dust clouds like this are relatively small, but others can get downright huge. We call these giant molecular clouds because why not? These can be incredibly massive, with thousands or hundreds of thousands of times the mass of the sun, and stretch for hundreds of light years. And that brings us to one of the most glorious objects in the sky, the Orion Nebula. This is an emission nebula located just below Orion's belt. It's actually a naked eye object, visible in modestly dark skies. It looks like a star by eye, but even binoculars reveal it to be fuzzy, and through a telescope or with long exposure images, you get unmitigated majesty. The Orion Nebula is a star-forming factory. A bunch of stars have been born in it. Some of them are very massive and incredibly luminous. The entire nebula is lit by 4 stars located in its heart, collectively called the trapezium. These are 4 brutes, Huge, brilliant stars that are each far more massive than the sun. Their light is so fierce it illuminates the entire nebula, which is about 20 light years across. And here's a funny thing about Orion. What you're seeing is not just a gas cloud in space. It's actually just a bubble sitting on the edge of a much, much larger molecular cloud, hundreds of light years across. That cloud is cold and dark, and so we don't see it by eye. The trapezium stars formed inside that cloud, very near the edge. When they turned on, fusing hydrogen into helium, they started blasting out a mind-numbing amount of ultraviolet light, which began eating away at the gas and dust. Eventually, they blew a hole in the side of the cloud, like a weak spot in a bicycle tire blowing out. What we see as the magnificent Orion Nebula is just a dimple, a cavity in the side of the cloud, filled with gas heated to glowing by the stars. There are still stars forming there today, too. I mean, literally, right now. We can see it happening. In episode 9, I talked about the solar system and how it starts off as a flattened disk of gas and dust. When we look at the Orion Nebula with Hubble, we see those disks. They're called protoplanetary disks, and they're so dense that they absorb almost all the light from the stars forming inside them, so they're dark, and we see them in silhouette against the brighter gas of the nebula, unless you look in the infrared. That kind of light can pierce the dark disk, and when we use infrared telescopes, we can see the protostars forming in the centers of those disks. Take a good look. Those are baby stars. Literally stars that are forming right this very minute. They're still hot due to their contraction, but in a few million years they'll ignite fusion in their cores and become real stars. They'll blow away the remaining material around them, revealing themselves, and perhaps any planets orbiting them as well. In fact, once stars start forming inside a nebula, its days are numbered. The Eagle Nebula is another star factory with active star birth going on inside of it. Some of these are massive luminous stars and give off so much ultraviolet light it erodes away at the surrounding nebula in a process called photoevaporation. However, dense knots of material forming new stars can resist that erosion better and protect the material behind them, in essence shadowing it. This results in long fingers of material we see in silhouette against the hotter gas, like sandbars in a stream. Observing their infrared light, we can also see the stars embedded inside them. There are several of these giant towers in the Eagle Nebula, 3 of which have been called the Pillars of Creation. Stars are forming at their tips. Eventually, though, the light from the massive stars will win, zapping away at the structures, dissolving them. There's also some very hot gas in the nebula that might be the result of a star that has already exploded. If so, then the pillars really don't have long to live. In a few thousand years, they won't be eroded away. They'll be blasted away. In a lot of nebulae, there's no sharp edge. They just kind of fade away. Sometimes that's because the gas thins out, so there's not enough stuff there to get lit and see. Other times it's because there's just one or maybe a few stars lighting up the whole cloud, and at some distance from them the starlight fades and can't illuminate the gas anymore. But sometimes nebulae do have sharp edges. That usually happens when a gas cloud is expanding, like in a planetary nebula or supernova. The gas slams into the much thinner gas that is strewn between the stars, what we call the interstellar medium. The expanding gas piles up like snow in a snowplow, getting denser and glowing more brightly. Gas inside a nebula can be in turmoil too. Winds from stars compress the gas. Shockwaves form when stars explode and when they're born. These can create lovely sheets, tendrils, and filaments in nebulae as well. All of these factors can come together to create great beauty. Not too far from the Orion Nebula in the sky is another dark nebula, superposed on a bright emission nebula. By coincidence, the dense dark material is shaped...
I'm pretty sure this... Yeah, this is an actual picture. This isn't a rendition of any kind.
like a gigantic chess piece, and it's called the Horsehead Nebula. It's being eroded by a star called Sigma Orionis off the top of the frame here, and that's also making the gas behind it glow in that sharp ridge.
Same with this
one of my favorite nebulae in the sky is Barnard's Loop, a huge arc of material that's formed either by the expanding gas from supernovae or the winds of all the massive stars being born in the Orion complex. It's also the outer edge of a huge bubble surrounding a substantial amount of real estate in the constellation Orion.
I just want to look at it for a little bit. This is an actual picture, not a rendition. The universe is gorgeous.
In this image, you can see both the Orion and the Horsehead Nebulae. The loop is so big, you could fit 25 full moons across it. One more thing. I've been talking about bright and dark nebulae, But that's an old-fashioned way of thinking of them. I've also mentioned that infrared light can get through them, but remember from episode 24 that the kind of light an object gives off depends on its temperature. Clouds of dust that look dark to the human eye are actually glowing if you observe them in the far infrared, while outside the colors our eyes can detect. But we have telescopes that can see at these much longer wavelengths. In Orion, there's a reflection nebula called M78. Between M78 and Earth are long filaments.
I'm sorry, guys. I love to look at these pictures. They're just beautiful. I really need to get into the Hubble
Of very cold and dark dust,
collection.
blocking the light from the reflection nebula behind and looking like dark
I'm gonna change
rivers
the
running
filter
through
now.
it. But when you use a telescope that can see light with a wavelength of a millimeter or so, that dust glows brightly, threading through M78 like ribbons of fire. Like so much else in life, what you see really depends on how you see it. If there's a life lesson there, feel free to take it. Today you learned that nebulae are clouds of gas and dust in space. They can glow on their own or reflect light from nearby stars. When they glow, it's usually predominantly red from hydrogen and green from oxygen. And when they reflect and scatter light, it's from massive hot stars, so they look blue.
I would love to get
Stars are
to
born in some nebulae
deep time
and create new ones as they die.
I have no
Some
idea what
nebulae
deep
are
time
small and
is.
dense.
This is something I'm
Others can be
interested to see
dozens
what
or
that's about.
hundreds of light years across.
Look away.
Also,
Well, guys,
they're
do one more?
incredibly-
I think we can do one more. I've been loving this series lately.
Over the past few weeks,
We'll call
I've
this the
talked
late
about
one
our
if you want to
sun, the planets and other
start
objects
looking
in our
around
solar
for
system,
another
stars,
streamer.
both big and
That's
small,
absolutely fine.
brown dwarfs, exoplanets, supernovae, and clouds of gas.
Let me just get through this. I don't plan on raiding out today. Usually I'll raid into somebody that's doing whatever I'm doing. Mostly I do retro. Today I love the solar system and how its beauty and its secrets, and I've been looking through most of my life looking through this stuff, and I thought I'd just share it with everybody else. My passion. There's quite a few episodes here if you guys want to go. Crash course in astronomy.
Gas and dust. What
If
do
you
all
wanna
these things
continue
have
on
in common? Well,
or catch up.
we all live in the same town. It's a big town, and it's called the Milky Way Galaxy. Let's cut to the chase.
We'll call
The
this
Milky
the
Way
last one
Galaxy
for
is a
today.
vast, flat, disc-shaped collection of gas,
Beautiful.
dust, and stars.
Yeah, this is an
a
artist
sprawling
concept.
megalopolis that's a mind-crushing
It'd be impossible to get a
100,000
picture. It'd be impossible to get a picture of the Milky Way from this angle. You know how far our tiny little planet's like out here somewhere.
light years across and several thousand light years thick. The sun is but one of hundreds of billions of stars in it,
beautiful
and we're
conception,
located
though.
halfway out from the center in the suburbs. The disk has two major spiral arms in it and two minor ones. These come together more or less in the middle of the galaxy. Located in the center of the disk is a bar, an elongated, roughly cylindrical collection of old red stars. I know, this is a lot to take in. I'll go over it piece by piece. And how we know all this, like with so many other such deep astronomical discoveries, begins simply enough, going outside and looking up. If you happen to be in a dark spot on a moonless night, you'll see a faint fuzzy glow stretching across the sky. It's brighter in some spots than others, and if the constellations of Sagittarius and Scorpius are visible, you'll notice the stream broadens there, forming a bulge apparently bigger than your outstretched hand. This glow's resemblance to a pathway or river is strong, and many ancient cultures saw it that way as well. Because it glows a dull white, the ancient Greeks called it galaxious, or milky. Over the millennia, that name stuck, and now we call it the Milky Way, or redundantly, the Milky Way Galaxy. But what is that glow? It was thought to be nebulous, cloudy, until one day a guy by the name of Galileo pointed his newly crafted telescope at it. He was astonished to see that it was actually made up of stars, thousands of them. They were so close together and so faint that our naked eyes couldn't see them individually. Instead, they blended together to create that glow. Clearly, there were far more stars in the sky than the 6,000 or so visible to our unaided eyes. But how many more? And what overall shape did they form? Astronomers reasoned that counting stars in different directions might reveal the shape. If the galaxy is longer in one direction than others, you should see more stars in that direction. Over the centuries, maps were made this way, and they generally showed the galaxy to be oval-shaped, or a flattened disk, with the sun near the center. This star counting method is a good idea,
They're so
but it's
innovative
fatally
back then.
flawed. It doesn't
Yeah.
account for interstellar dust. As we saw in our episode about nebulae, dust
But they didn't
absorbs
know about
visible
that
light
back
from
in the
stars,
time.
hiding them from
They
our
did
view.
really well.
It's like being
really
in a
good
smoky
job
room
for
where you
what they
can't
had.
see the walls. It looks like the room is smaller than it really is, and you look like you're in the center, even if you're near one of the
This
walls.
is an actual
Globular
picture
clusters
too.
were a
I'm
good
sorry, guys.
clue that they're
I
smaller
want
than
to
it
take
really is. And
a closer look at this beautiful screen capture. This is most likely a Hubble capture. I'm pretty sure I saw this one before. Beautiful. Look at our universe. Look at this beautiful universe scape. This is a picture. This isn't a rendering. Beautiful.
And you look like you're in the center, even if you're near one of the walls. Globular clusters were a good clue that there was more going on. These spherical balls of stars orbit the galaxy well outside the main body of the galaxy itself. There are more of them on one side of the sky than the other, which you wouldn't expect if they were evenly distributed in space. The simplest explanation was that they actually were evenly distributed in space, but it was we who were off-center. Measurements put the sun about 25,000 light years from the galactic center, which was in the direction of Sagittarius. Hey, that's where the glow of the Milky Way in the sky gets brighter and broadens out, too. Coincidence? So at this point, things were coming together. The Milky Way must be a flattened disk with a bulge in the middle. That was the Pleiades. The sun is in that disk.
Let me go back.
The Milky Way must be a flattened.
Damn it. I'm sorry. I'm sorry, everybody.
Glow of the Milky Way in the sky gets brighter and broadens out, too. Coincidence? So at this point,
Pleiades, I think.
Things were coming together. The Milky Way must be a flattened disk with a bulge in the middle. The sun is in that disk, far from the center. From inside it, we see it as a broad line in the sky. And when we look toward the center, toward Sagittarius in the sky, we see that bulge as a big blob. The disk is thinner than it is broad, so we see more stars looking into the disk than when we do looking up or down out of it. But what about the disk itself? Does it have structure in it, or is it more like a smooth, flat plate? That's hard to determine using visible light. Dust severely restricts our view. Looking into the disk, we can only see about 1,000 light years before dust blocks everything behind it. But with the advent of radio astronomy, we figured that out too. Star-forming gas clouds emit a very narrow wavelength range of radio waves, and this could be used to measure their Doppler shift, how quickly they were moving toward or away from us. Making a few other basic assumptions, their rough distance could be found as well. An amazing result was found. The locations of these nebulae indicated that the disk of the Milky Way was divided into spiral arms, huge, sweeping, curving arms that were tens of thousands of light years along their lengths. Interestingly, all the young, massive, bright stars appeared to be in these spiral arms too, with none in the apparent gaps between the arms. But that makes sense. Like all stars, these massive ones form in giant nebulae. But unlike most stars, they don't live very long before exploding as supernovae. If most nebulae are in the arms, then these massive stars will be too. They don't live long enough to get very far from their nurseries before they explode. Here's where things get a bit weird. You might want to think of the arms as structures, huge collections of stars and nebulae moving together around the galaxy's center. But that can't be right. If that were the case, they'd wind up like string on a spool, since the stars and nebulae closer to the galactic center orbit faster. But we know the spiral arms have been around a while and aren't wound up. That's because they aren't actual structures. They're traffic jams. Think about a highway with heavy traffic on it. For some reason, one car slows down a little. The car behind it slows, and the car behind that one hits the brakes too. It's like a wave that moves backwards through traffic, slowing everyone down. Where they slow down, they tend to clump up too, so you see more cars and trucks in the jam. The funny thing about traffic jams is they tend to persist for a long time, even as cars move out of them. The car at the front might slow for a moment, then accelerate away, but the cars behind it are still moving slowly, and more cars are piling up in the rear. For every car that leaves the jam at the front, another enters from the back. Even though the actual individual cars come and go, the jam persists. Spiral arms are the same sort of phenomenon. The initial wave, the jam, may be started by some sort of disturbance in the disk, perhaps an overdense region created when a couple of giant molecular clouds smash together. Once created, this effect propagates outward like a ripple in a pond, and gets sheared into a spiral wave pattern by the rotation of objects in the disk. Stars and nebulae enter the wave, pile up a bit, move through it, and then resume their merry way once they leave it. Our sun takes about 250 million years to orbit the galaxy, which means it's made about 20 orbits since it was born. It's moved in and out of spiral arms many times over its long life. That's why spiral arms don't wind up. The arms are waves made of objects in them, but the objects themselves are transient. However, there's more to it. A nebula entering a spiral arm might hit another one already in there, a cosmic fender bender. But when that happens, the nebulae can collapse, forming stars. Some of them are massive, luminous, blue, and hot. These stars are very easy to spot at great distances, making the galaxy's spiral arms look blue. They also light up the gas around them, accentuating the spiral arms. Spiral arms are where the majority of starbirth occurs in the galaxy, which helps maintain the spiral pattern. They're the ultimate crowdsourced projects. After all that, it's actually hard to say how many spiral arms the Milky Way has. It's been thought to have 2 for a long time, but a recent study of the locations of star clusters seems to indicate there are actually 4. Milky Wayologists are still arguing about it, but either way, there are also short spurs that stream off of the major arms as well. Our sun is located just outside one of these smaller arms called the Orion Arm. Mapping the galaxy's spiral arms is ongoing work, and it's kind of a mess. It's like being inside a hurricane and trying to figure out its structure. But we're doing pretty well so far. In the center of the galaxy is the bulge. Recent observations indicate this is actually a cylindrical bar of redder stars that's pointed nearly directly at us, so it looks more circular to us. This region is very old. All the starbirth in there happened long ago and ceased when the gas ran out. Unlike the spiral arms, where stars are still actively being born, all the blue stars in the bar are long dead, exploded, leaving behind billions of lower mass, redder stars. The bar is probably about 20,000 light years long. This odd structure is due to the weird gravity of the galactic disk. Unlike our solar system, where the central sun dominates the gravity of the galaxy is spread out over a huge area. This distribution of stars and gravity means weird structures can pop up and self-maintain, like spiral arms and central bars. Unlike the arms, though, the bar rotates as a single unit. Stars near the edge make one orbit in the same time as the stars closer in. In the very center of the galaxy sits a very massive black hole, one with 4 million times the mass of the sun. This might seem huge, but remember, the galaxy has hundreds of billions of stars in it. The central black hole is actually just a teeny tiny part of the galaxy by mass, but we'll learn more about it in a future episode and see that it may have played a very big role in our galaxy's formation and evolution.
I think that's
the
it,
last
guys.
component of the Milky Way is its halo.
We got
a
one
vast
more
spherical
thing
cloud
here.
of stars surrounding
About a
it out
minute
to
and a
great
half.
distance,
You guys want to
more than 100,000 light years. We don't know
fine.
much about
I
the
have no
halo,
problem. We're not
but we
gonna
know
be
the
raiding
stars
out
in it
today.
are old. No star formation
to
occurs
have,
there, so any stars we
an
do see
educational
would be old.
video.
It's possible
to
some
read
stars
out
in the
to,
halo formed
I
there,
just don't.
while others were flung out
Sorry,
into the
guys.
halo after collisions with other
I
stars
usually
and
do
clusters.
love to spread the
Speaking of
love
which,
around,
most of the
especially
globular
if I have a
clusters
little bit.
orbiting the Milky Way are in the halo.
It's
There
a
are more
Twitch
than
way.
150 in total. So there you have it, our local galactic town. But like any denizen of a small town, it's natural to wonder if this is all there is. What else is out
Oh, no.
there?
There's
And
a
at the
lot
beginning
more.
of the 20th century, astronomers started to ask the same
The
thing.
same
Is the Milky
thing.
Way the galaxy or a galaxy? Oh, we're about to take a big step here with Crash Course Astronomy. A really big step.
Oh, but we'll
Better
have to wait
strap
for that
in.
tomorrow.
Starting with the next episode, the universe is about to get a lot bigger. Today, we learned the
Okay,
Milky
now
Way
we're
is a
starting to get
disk
into the good
galaxy.
stuff. Finally, that's going to be it for me today, you guys. We're going to be just shutting her down. I like to raid out into other people that are doing the same kind of types of thing that I am, unless there's a pre-affiliate. Then we all love pre-affiliate meat. Num 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 num. And otherwise, I appreciate everyone for being here. Extreme, thank you so much for all your beautiful hanging out, and Shadow Man as well. You had Henry pop in for a little bit. Had Mr. Flex pop in for a little while. Had a whole bunch of good company today. I'm looking over everything. Yes. Excellent. Good stuff, you guys. Until tomorrow, I must say bye-bye.